Okay, let's get to it. Samsung's recording. Okay, cool. So last night I had some ideas, so I just drew out some diagrams. And I'm not going to do any of this today. This is like a far future thing. But I was thinking, okay, well, how do we do a Metroidvania kind of level map thing if we're going to always use like 512 by 512 textures? And the original idea was to have like a whole bunch of layers and a whole bunch of parallaxing and stuff. But then I realized that design would require like a 1024 by 1024 texture. So I'm thinking to myself, okay, let's try to slim down that design a bit so that we can get, you know, all the levels we want packed into a 512 by 512 texture. So in terms of loading levels into a texture, we really want to, this is how levels should work in the Metroidvania kind of layout of the engine. We have the room that you are in, then we have a room to the left, we have a room to the right, we have a room above you, we have a room below you, and then we also have a top left room, bottom right corner room, bottom left corner room, and a top right corner room. So if you zoom the camera all the way out, you're going to be able to see the next rooms that encircle you. And then we're going to have a reused room style where it's a horizontal connector and a vertical connector. And those connectors are going to just always be there. So every room potentially has a vertical and horizontal connector. For now. Now I am thinking that, well, maybe you don't always want to be able to go directly to the right or directly to the left, right? Because that makes it so in the game design you have to always have, you know, one entrance and 3 exits, which could be a problem. But let's not worry about that for right now. Let's just worry about the fact that we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 unique rooms, and then a redundancy of this room, a horizontal room, and a vertical room that are kind of cut and pasted here. So you got 9, 10, 11. You got 11 rooms, and I'm thinking of packing them into the 512 by 512 texture like this. So each one of these segments is 128 by 128. Yeah, this is 128 by 128. And so we can see 9 here, and then we see 10 and 11 right here at the horizontal and the vertical. Now I don't know what these slots will be used for yet, so there's no harm in just saying I don't know what it's going to be used for yet, and then we have some free space to do stuff with in the future. Okay, so we've decided that for each level we want to use a chunk of 128 by 128 pixels. Here's our rooms kind of like laid out. Right here's the codes for all the different room styles here. We'll check some, making note that I have 9 basic rooms, plus, you know, 10 and 11 for horizontal and vertical. So you might want to make a note of that. You know, horizontal is horizontal connector reused. Right. Right, horizontal connector room, 10. And a vertical connector room, that's number 11. Okay, but anyways, let's go up and look at, well, how are we going to partition this? How are we going to make use of all those bits? How are we going to lay things out? So, we have a chunk of 16 rooms, right? 4 by 4 is 16. We don't know what all the room data is going to be, or if even maybe some of that data isn't even going to be rooms. But after we take this 128 section, right, this is one cluster of room data. This is one room's worth of data, one level worth of data. We can subdivide it into these 64 by 64 sections. And the actual level design is going to be 64 by 64 tiles because the last game almost did everything it needed to with 32 by 32 tiles. But, 30 by 30 tiles is what it used. but sometimes it felt kind of short where it just needed a few more. And so by going the next power of 2 up, we double the size, which means that it's four more times the work, right, for a level, right? Instead of roughly 32 by 32, we have 64 by 64. All right, so 64 by 64 is 4 times as many pixels as 32 by 32, right? Because you can fit 4 32 by 32s within a 64 by 64. So we're adding a little bit more work. Now we can still make smaller levels and just put like ornate designs, right? So we could still make a 30 by 30 level, but just center it within a 64 by 64, right? So there's enough space to recreate the old levels, but that extra space we can also use to make more intricate levels. So, okay, so we got this 64 by 64. How are we going to use this? Well, what I'm thinking is we separate it into layers. So this will be a background layer that scrolls. This will be a background layer that's static, meaning that it's glued to the level map. So it scrolls with the level, right? So you could use this to make a backing wall, right? So let's say your character, you could make, let's say the character is on a bridge and there's some cables that are holding up that bridge, right? Maybe it's like a suspension bridge of some sort. Well, you could use this layer to draw like those suspension cables that are still connected to the foreground bridge that you're on, but they're kind of behind you, right? So a static background, right? So you could call it the background midground, if you want to call it that. You could call static BG the background midground, and then you could call static FG the foreground midground, right? And then here's the maybe that's not the best way to call it. But anyways, these layers are in order, right? So from front to back, or back to front, right? So this is the furthest back. We have some scrolling parallax kind of stuff. And then further up, we have a static BG that kind of is snapped to the actual tile map that the gameplay is done on. And then over here, we have the actual tile map that you can interact with. And then over here, we have a foreground to give like foreground details, right? So we can put like little details in front of the character, right? So these are details behind the character, details at the same level of the character, and details that are in front of the character. Now, in practice, I find that in terms of how we're going to actually render this, this will be behind the character, this will also be behind the character, but it will impede the character, and then this will be in front of the character. And that will give the effect of this being on the same layer as the character, but we can't really draw the character and the tiles on the exact same layer, or at least if we're going to draw tiles and then we're going to draw a character, we can't draw them at exactly the same time. We have to actually take a choice. So logically, this layer is going to be on the exact same layer as the character, right? This is going to be behind the character, and this is also going to be behind the character. So less layers than I had originally designed for. But the idea is that I can get be a little bit less ambitious and try to get more bang for my buck is kind of what I'm trying to go for here. So after we've decided on these different layers, we can start to split up the bits. So what I'm thinking is, right, we got R, G, B, and A. So I'm thinking that for the red channel, we have geometry and bombs. So we have 16 different types of geometry tiles and 16 different types of bombs, right? Then for the green channel, we have sprites and light tiles. So 16 different kinds of sprites, 16 different kinds of lights. And for the remaining channels, we got these leftover B's and A's. You're like, well, what do we do with the blue and the alpha? Well, the blue and the alpha are going to be used to create sub-details. So sub-tile details where we want some more granular details so that we can... sorry. We want some more granular details so that we can give we can give the how do I say this? I'm thinking here. Granular details are necessary to make the level design look less childish. Fine-grained details are those little extra touches that really make something look professional. I don't know how to describe it any more than that. But let's say we have some tiles and we want to create like a railing, right? So let's say we have let's do things in sets of 3 here. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay. And there's a reason I'm dividing this into 3 here. That's a little bit high there. Let's just take it and roll with it. Okay, so let's say that we want... Let's say this is the normal tile size, and we're thinking, hey, it would be really nice that after we stack these tiles together, and the character is like walking on this, it'd be really nice that if we could have like a railing, right? So how would we make a railing? Well, to make a railing, what we really want to be able to do is to make tiles that are smaller than this and draw with them, right? So what we're going to do is we're going to create a way to create smaller tiles that are, we want to like divide, we want to be able to divide these tiles into thirds. I want to be able to divide any tile into thirds by using that bit scheme I was showing. And we want to be able to use that to create railings if we want to, right? So if we want to create like a railing from here to here, we can create like a little railing, right? And right, like if we want to create like a railing like this, we can kind of subdivide up the tiles and we can use them to create like a railing. Right, so that's the, right, so this is one tile, right, and then here we're kind of like making these sub-tiles that we can use to draw kind of these very like micro features that just give the level design a little bit more flair. That's kind of like what I'm hoping for here. So let's make a note here. You know, at what time? Is it one? Yeah, at vid IID 0135. Time 13, and let's do 42 to keep it with the conspiracy. Subtile features allow for things like railings and other fine details that make the level design look less childish. So now the next thing is that I'm looking at here. Yeah, that's good and all, but where is my... If we do it this way, where's my allocation for tiles that are larger, right? There's no like mip-map kind of structure here, so I would like to... I was thinking originally that we would have like very large, right? Since we have this fractal aspect, I was thinking we could have, you know, different tile sizes on the main tile map. But maybe we don't want to do that. I don't know. I'll think about it. Or I could just use another rendering level to do that. I don't know. Now this is just a thought for how to do things, right? So this is just a thought for how I want to do things in terms of the level rendering, and I'm not sure if this is how I'm going to do it, but it was just a thought I had, right? So then I had another thought for how I was going to do like the fractal auto tiles, and I was thinking that within the 512 by 512 canvas, we could divide everything into patterns like this, 32 by 32, and this could be 16 different tile values, and these could all be terminal tile designs, right? And then we could use like 2-bit values. So this tile here could be drawn using 2-bit tile values that would select from one of these tiles here. Then if we're looking at this tile design, it's drawn with 2-bit values that select from one of these tile designs, and then one of these tile designs selects from here, etc., all the way down to 16 depths, right? So we have 16 tile sets. These are 16 terminal tile sets. These are 16 outermost nesting level tile sets, and we go down 16 nesting depths, which will give you a lot of zooming capability, right? So if we think about the level of zoom, each time we do this, each time we do a jump, right, we're going from one tile to another tile to another tile, that's 1/32nd, right? If this is a 32 by 32 tile, and this is also a 32 by 32 tile, that means that each pixel of this 32 by 32 is drawn with another 32 by 32, right? So that's one, so we have, so we'll just say that, this is 1 unit. How about this 32 is 1 unit here, right? So 1 divided by 32, divided by 32, divided by 32, all the way to 15 times would give you the zoom level. So I don't even know what that would be. Let's open up a calculator. Actually, no, let's just go and go over here and say, like, okay, 1 divided by 32, divided by 32. I don't know math very well. So if we divide by 32, 1, 2, 3, 4 times, 5 times, 15 times, right? So we're talking about just a ridiculous level of zoom, right? So, yeah, I think that's plenty of zooming level for getting that kind of fractal kind of feature that I would like to get. So that's what I want to try to get going. But that's a far future thing, but I just wanted to document what I was thinking about there. Also, the video number is now 135, so I should change that on the video. Okay. I have a headache and a slightly sore throat, so today is not a good day for me. And I wish it wasn't on coffee day, but oh well. So yeah, I don't know exactly where that's going to go, and we'll try not to worry too much about that. Let's just try to close some of this stuff, and okay, so we have some of these diagrams. Yeah, but those are just some thoughts, right? So, actually, hold on. I'm going to open this up again and say, this is a half-baked idea, but let's put it in the README, right? So let's go into our README file, and this is where I've been kind of like duplicating diagrams. So we're gonna say like right. So label this diagrams, and we're gonna say it fract 16 fractal auto tile sets, right? So fractal auto tile sets rather than the auto tile sets where we're doing different layers and things, right? So let's take this and throw that diagram, that half-baked diagram in there, because the thought is that a lot of my stuff is just going to get very scattered, I think. Like, I have all these notes that are kind of like all over the place, so I think by just kind of duplicating some of this stuff, by duplicating some of these notes, even though they're not like the complete notes, it's going to help me, I think. So I'm going to paste that in there in my notes, so that it is in the kind of like the main README. And then also, let's go look at the level 16 or whatever, and just write a problem we have here. Problem, maybe. Do you want extra large this system count for extra large tiles that okay. So I'm thinking, yeah, I kind of like this design, but the problem here is that if we subdivide everything into kind of these different layers, then we have a problem where, well, now we don't have enough room for the different tile sizes that we would like, right? So we would like, now if we're lucky, maybe the fractal nature of the tiles will just remove a lot of that redundancy, and we won't have to worry about that. Right? It'll just work itself out naturally. But I would like to not have to rely on that. Another thing we could do is we could the different tile sizes could be a rendering feature, right? So, wait. Right, like we could have an auto tiling method where we just detect where there's big clusters of tiles and just make, like, we set like a larger tile. I don't know, I think that would just make things harder. I don't know, I think that, just think something doesn't work. You know what? Let's just make something, right? Let's not worry too much about it. Right? We have these ideas for what we need to make interesting levels. Let's not get too pessimistic and be like, waterfall this all out too much, right? Let's not waterfall it out to the extent where we're like, okay, we need this and we need this and we need this. Let's just try to create some upfront designs and be like, okay, here's an interesting way to lay out the memory, and then we'll do that, and then, you know what, if it doesn't work, if it does not end up working out how we thought, it just doesn't, the rendering scheme just does not look good, then we'll scrap it, right, or we'll use it for something else. And maybe if we're lucky, what we can do is, since we have all these different memory layouts, and one, so the base tiles that we're going to create in PAINT5D, we're going to use those to draw the terminal tiles. These terminal tiles right here will be drawn with those base tile designs here. So these terminal tiles will get rendered with the PAINT5D tile designs, and then the second tiles from terminal, these tiles will all be drawn with these tiles here, and then this column of tiles are all going to be drawn with this column of tiles, etc. So So this data set here is going to plug into the PAINT5D data set, right? So even if we completely hate one of the data layouts that we're using, if we design the renderer to create this pipeline where we plug in one data set to another data set to another data set, we can get to the point where we could mix and match things, or we could scrap things depending on if we like what we see or not. So let's not get too discouraged with thinking about how this is going to work. I think it's good to think about, but let's not worry about it too much. Okay, so let's close the README, and let's close PAINT5D, and let's make a note here. Let's do 23 to keep with the conspiracies. This is where data sets for PAINT5D are loaded into the rendering engine. PAINT5D is responsible for creating the terminal. They designs are not fractal, as once you get down to this depth, you cannot dive any deeper. However, okay, so just a note here, and I just want to make a note of, what this section of code does, so that I can find it again in the future. At tile loading, right? So we could make a little note here. So maybe we want to, well, like if we want to query like where all the tile loading or data loading is, maybe we want to do like little @ symbols here. I think that could be helpful. And then in the hashtag documentation, right? So in our documentation, we can go into our hashtag file, and we can just make a note of what we mean by @tile loading and @data loading, right? So, but yeah, let's just kind of make a note of this. @tile loading, a section of code responsible for loading the data for a tile set of some sort. Using this tag, I can easily find things in the future, hopefully, right? So it's not a guarantee here, but I'm just trying to leave little breadcrumbs in the code base so that I can find kind of things that I am looking for. So data loading. Data loading is basically going to be loading like tile loading, like a at tile loading, but more generic. At data loading. At tile loading is but square right, so it's a square rectangle problem, right? So data loading is like tile loading but more generic. Tile loading is data loading, but data loading may or may not be tile loading, right? So we're just making a note of that. And then let's keep a note of what do we mean by like a square rectangle problem, right? So what do I mean by that? So let's put that in here. Okay. A square is always a rectangle, but a rectangle may or may not be a square. I tend to use this comparison a lot. So, making a hashtag for this analogy. Right, so I'm just making a hashtag for this analogy. So, as I tend to frequently quote it, I can now uncertain if this comment tag fits more under or okay, so just making a note here. So we're going to say that this is correct. This is a correct tag. Correct tag, but these are incorrect. So these are wrong. I'm going to call it a wrong tag. Incorrect and correct. I do not like how incorrect and correct, the words are too similar. I do understand that in proper English, yes, it would be incorrect and correct, but I just hate the verbiage there. I would like there to be more difference. So I like to use wrong and correct, or wrong and even right. Like, even though that's not totally grammatically proper, I just prefer it. So that's what we're going to go with. So square rectangle problem is how we're going to identify that. And then down here, you know, at square rectangle problem, right? Example of, right, so, right, data loading is an example of the square rectangle problem when we compare it to tile loading. Okay, cool. So how much stuff do we have in here? Don't we have like thousands upon thousands of comments yet? No, only 6,000 lines of commentary. But still, like, a lot of stuff kind of off-boarded into the comments section, you know? Before we kind of figure out how the memory view editor, or the memory view, yeah, I guess it's technically an editor. Before we figure out the GPU view, right, the GPU memory view, before we figure that out, we got to just make sure we can compile, right? So let's compile, make sure that we are working in a non-broken state, and then we'll kind of figure out what to write on top of that. Okay, so if I press 0, we get the memory view editor, which is just kind of blank right now. And I see that once we went over to the PAINT5D system, we ended up with this, like, we have these little white pixels right here, right? And that makes sense because this is the bottom 32 by 32 section, and these white pixels are the uniforms, right? Are uniforms that have been set within this 32 by 32 block. So that actually makes sense that I'm seeing this right here. It kind of looks like an ellipsis almost, like a random just ellipsis or a little artifact, but that actually makes sense. We're actually viewing the texture memory. So that's so does that mean that our editor already kind of works for what we need it to do? I think that actually does. I mean, we could add some features, right? We could add some features to we could hard code it to zoom in on this 32 by 32 block for a little bit, just so that we can have a better look at what's kind of there. I think that might be good. Because really we don't care what's all around here, we just care about this, so that we can kind of debug what's going on over here, right? Because right now, like, things are doing things, but the variables don't, like, reload properly if we do, like, a subtexture push. And we gotta figure out, like, why that is, and we want to inspect the memory, right? So if we can get this 32 by 32 chunk to snap to this 512 by 512, we're going to have, like, a nice zoom factor. Now, I don't know what the exact factor is, but 512 divided by 32. So 512 divided by 32. And that is 16. So for every pixel will be displayed using 16 pixels, right? So that's a pretty decent zoom to kind of inspect the memory region and kind of see what the hell is going on. So let's go add that shader code, I guess. Yeah, close the program. So we don't really have to do really much to get this working now that I realize it, because it's already mostly there, right? We just need to, we could add fancy controls and stuff, but really all we need right now is we just need to inspect that one memory region. And so the hard coding that is in the shader code right now is perfectly fine for now. We can't even, yeah, it's fine. So let's go in here, and let's go into the lib folder, and we want to look at GPUView. But in GPUView, well, also GPUWire, we're going to use that as well. In GPUView, I'm actually surprised that GPUView just works. I thought we'd have to wire some... I don't know. Whatever. Let's not worry too much about it. Oh, you know what it is? It's working just because it's the 0th texture slot. So GPUView right now is kind of coincidentally working because the texture sampler hasn't really been set up, but by default it's set to 0, and that's why it's sampling the correct texture. It's actually, so we're actually seeing things work by coincidence. We're not actually properly set up here yet, but that's fine for now. Let's just take advantage of that bug that is making the code kind of work how we want it anyways. And what we want to do here is we just want to take alright, so if we're in this like 512 by 512 section, right? So this is, if we're inside the 512 by 512, so inside 512 by 512, Right, here's where we are. And we want to just remap some things, right? So so what we're going to do is we're going to say so it's 16, each tile would be 16 pixels in size within a 512 by 512 area. So we got to divide by 16 to figure out where you are. So we're going to say, like, I don't know, int32 tile x equals cov ix divided by 16. And these are all integers, so we should be able to do that fine. It'll automatically truncate, I think. int32 ty, take iy divided by 16, right? And then we want to offset, right? So we want to offset to the last 32 by 32 chunk. And let's go look at the tau system. So tau depot, I believe, tau depot data, and figure out how that works here. So this last 32 by 32 chunk, well, how many 32 by 32 chunks are there? There's this, and then we subdivide this into this. Well, we'll just divide 512 divided by 32, right? And we see that there's 16 different chunks. So if we want to get to the last chunk, tx equals, you know, tx equals 16 minus 1 times 32. Yeah, so we want the origin of the last cell, right? So 16 minus 1, 15. 0, 15 times 32, it's 32 by 32. And then we want plus tx, right? And then ty is going to be kind of similar. Ty is going to be this. So zoom into the bottom left. Now, is this correct, though? Is that correct, or is our math off here? Because we're in here, yes. But then for... Oh, maybe that's what's going on here. Let's not even zoom in. Let's not even zoom in, because the PAINT5D system, we're expecting those pixels to be over here, and we're seeing white pixels not over in this section. We're seeing them kind of like down here, right? So that tells me that the math is off, right? Because we're expecting to see values over here, and that's not where we're seeing them, is it? Yeah. So yeah, hold on. So let's close this. Let's take a look at that for a second. So we're seeing okay, so what we could do okay, here's what we're gonna do. We're going to That is a horrible mistake if that's the mistake I've made here. Or hold on. Maybe that's just not as bad of a mistake as we thought. Hold on, let's look at this for a second. So, let's look at the diagram. So we know, first we kind of subdivide into here, right? So, that's why we're over in the rightmost section, right? And then, from there, so we're not all the way at the end, right? Because then we're kind of like in this 30, so we're in the, these are all 32 by 32 blocks, right? Each one of these is 32 by 32. So we're in the, so we're not in, so this is the index 31, index 30, index 31, index 30, index 29. So index 29. So actually this math is kind of like, 29th. Right, it says the 29th 32 by 32 on the X, and then over here, this is 31, this is 30, this is 29, and this is 28, right? So 31, 30, 29, and 28. So this would be the, on the Y, this is the 28th 32 by 32 cell on the Y. So if we want to zoom into that cell, that's actually where we are. So we're still close to that end, to that last corner. So the data still kind of like seems to make kind of sense, but we're going to use this to zoom in on this, right? So instead of using this, we're going to comment this out. So this is, you know, this right here is, you know, no zoom, full texture. And this right here, if we use the TX, TY, zoom in on PAINT5D variables. Right, so we're going to zoom in on only the PAINT5D variables. Right, there's a cluster of 32 by 32 pixels used to store those variables. So we're going to zoom in on that and see what is going on there, right, in the shader code. So that's our hope if we wrote that correctly. So let's go close this and give it another run. And I am hoping that, you know, we wrote this code correctly, right? So if we did anything that's improper, we'll find out very soon because, oh, well, hold on. I think my build system is now deleting the old shaders, I believe. So I would say that's not looking at what I was expecting to look at, right? Like it's completely black now, right? So we had those white pixels somewhere, but we're obviously not seeing them where we're expecting, right? So did we perhaps get our X's and Y's mixed up, right? Because that's something I do. I'm pretty good at doing that. So we're saying that, you know, we're in this last cell over here, and that there are 32 of these cells, right? So 32, or did I get the math wrong? So 512 divided by 32, right? 32 by 32 cells. And that gives us 16 by 16 cells, like all together. Okay, so if that's 16 by 16, yes, I did get the math wrong here. So this is this cell here. This is 15, 14, 13, and 12. Okay, so on the Y, it's going to be 12. And I used what? I used 32. That's completely wrong. So this is 12 over here. Okay. On the x-axis, right? This is the 15th slot, 14th, and 13th. So this is a 13 here. Oh, so I made the comment right, but then I didn't make the code correct. So 13 and 12. Right, so we're trying to look at how we subdivide all this right here. And so we know that we're at the very edge here. That's why I started counting at, 15, right? Because we're at the very edge. So right here is the 15th, 15th cell, right? And then here's the individual pixels within that allocation. So let's make sure that we have this correct, right? So 15, 14, 13, 12. So 12 on the Y, okay? 15, 14, 13, so 13 on the X. So that math looks correct. So let's give this another run and see if we can see like large white sections after we go into the editor, right? So let's just see what happens, and hopefully that is more correct. Okay, so if we go from here and then we go over here, I'm not really... P for pattern. Okay, now let's go over here. So yeah, I'm not really seeing it. So that is kind of... demoralizing a bit. Now, is the division by 16 correct, right? So we have... Ideas are 16 by 16 cells. Oh, but each cell is 32 by 32 pixels, right? So this division isn't right? We want to divide by the tile size. And the tile size is 32 by 32 pixels, right? Oh no, the tile size is 16 because, hold on. So we take 512 and we divide it by 16, right? We get like, we get 32 by 32, right? Yeah, we wanna map those 32 different things. That makes sense. Okay. And this TX here, we got 13 and 12 times... But this shouldn't be 16, right? This should be a 32, right? Yeah, because each one of these... We need to multiply these by the block size, and the block size is 32, right? So this is wrong. 32 and 32. Man, I just can't math. Okay, and then once we've multiplied by the block size, these indexes are 0-based, so we just have to multiply, and we get the starting address, right? So if we're on the first cell, it's 0. 0 and 0 times 32 gets 0, 0, which is the base. And then here's the offset into it. So that's what we actually... God, I'm just horrible at this. So, you think that, we would get it right the first time. This is kind of trivial math, but obviously not. And we're just trying to hard code this math in for now. We're not going to have any kind of camera. We just want to get, we want to be... There we go, much better. We just want to be able to inspect the data and be able to look at that. So that actually looks more correct. That looks pretty good for me. Now, if we go over here and we press some of the keys, I think if I press like the A key a whole bunch of times, then go over here, we might see a difference, maybe not. Let's use something that we know is actually working, right? So let's go O for output, or no, P for pattern. Let's go all the way up, right? And then let's go look at what we have over here. And it may not just look that different because there's really not much to show, right? But the point is that we can see this pattern, right? We can see this pattern. It's definitely there. And I don't know what all the other things are for. So how are we gonna test this out? I'm thinking one way to test this out is we set variables at this corner, this corner, this corner, and this corner, just because we can, just so that we can test that things map to where we think they're mapping, right? So zoom into 32 by 32 cell of pixels that holds PAINT5D system information, right? So that's what we're doing over here, right? That's what this formula is, and that formula is working right now. Let's make a note of where we are, right? So at vid IID, and we're at around 135, and the time is 56:42. Okay, so now that we've done that, I guess let's manipulate some of our variable mappings so that we can, reload this. Let's manipulate some of our variable mappings so that we can kind of see what's going on a little bit better. So in our tau depot, in our I believe it's tau depot data is going to have this. I could be wrong. So yeah, we have some mappings here. And we want to figure out what indexes can we use so that we can... Right, so we already have these variables, so it'd be nice to just say... it'd be nice to just remap them, remap some of these into kind of some extreme corners. And I don't think that all of these have mappings on the keyboard yet. Now, I could be wrong. Well, this is not keyboard binding. So I know that all these kind of have some bindings. So what we could do is say, let's go into the keybind and see what our keyboard bindings are, and say, could we kind of choose, what could we choose that would make things kind of easy on us? Camera control, left, up, down. I'm thinking we just forget about that and we make like debug. We make debug values. We make we reserve. We just gotta reserve like 4 locations for debug in the corners. And so what we could do is say, like, you know, debug for debug variables. Right, so if we run out of room, we can get rid of these debug variables later. But right now we need, like, to define something like define AAC 2020 tau depot. I don't know why I called it sub. Oh, because of the subsection, right? Because there's tau, sub, and var. Oh, subsystem to PAINT5D, variable, etc. Okay, I see what's that. I see what we're doing here. So, tau depot, subsystem PAINT5D. Var is debug 1. That's actually going to be set to 0. We're going to set them to the correct locations for the respective corners. So, we're going to move things down here over here, though. So the debug variables are going to be 0. And then we have all the way over is the, it's an arrangement of, every cell is 32 by 32 pixels. So 512 divided by 32, I just want to make sure I have that right. I think it's 16 by 16 subdivisions. Yeah, so 16 divided by 16. So that means that, but that's not really where that is, though, is it? It is, it's in a 32 by 32. But that 32 by 32, there's 4 pixels for every variable, so that would still be 16 by 16, huh? Yeah, so that would still be 16 by 16. So that means that so this is the top left, this is the top right, and this right here, we want to do like a bottom right, and then a bottom left, or a bottom left and then a bottom right. I want to go in like scanline order here. Okay, so to get all the way down here, let's start over here. Let's just start at the last one. The last one we know is going to be 31, and then to get over here, we just need to subtract 16. Or do we need to subtract 15? Well, if we're on the 15th slot, which is the last slot of something, like if we're going for, if we just have a strip of 16 cells and we're on the 15th, which is the last, and we subtract 16, we end up negative, right? So we want to take the 31 and we want to subtract 15. Or we could say subtract 16 plus 1, right? So, so 31 minus, that's not even correct though, is it? So it's 16 by 16 cells, right? So 16 by 16, 16 times 16 is what? It's 256, so this is actually 255. It's the 255th cell. And then we want to just subtract 15, right? So we want to subtract 15 from that. So 255 minus 15 gives us 240, right? So this is the bottom left, is 240. So these are the numbers we're going to need to get those extreme corners, right? So, you know, we can make a note of that, right? So we can say, you know, at vid IID, and Corner debug vars help us visualize that tau sync texture pushes are correct. Right, so help us visualize that tau sync texture pushes correct. Now, obviously, the grammar is a little bit weird, but the idea is just to write enough to where we know what's going on without going over our column. And so, help us visualize tau sync texture pushes correct. So, the idea is we want to verify that the texture pushes are correct, and if we use these numbers, we're going to be okay. Now, because of that, these numbers here are no longer sequential. So, in order to fix that, what we're going to do is we're just going to go over here, and we're going to make a note that the this right here is the 0th slot already, right? So we could actually redefine this, right? We could actually go define, right? And then we go 1, 2, and 3. And then we've got to slide all this up here, right? So this is all the way up to 9. This is 10 now. And the next slot that's used is 15, and we're not going up that high yet. So if we've successfully... Okay, so now the problem here is that in the code, in the shader code, I believe we hard-coded some slots, didn't we? Specifically the offset decks we hard-coded. So if we run this, we have broken some of the hard-coding. So we're going to have to fix that. But at least I remember the hard coding I wrote, so I know exactly where I'm breaking things. So the keyboard will probably be the renderer. I do P for pattern, and then I go like Y to go through here. So we actually get an assertion fail, huh? And that was what I was expecting. So let's go look at line 2939 for a second in PAINT5D.F. 2939. Do we hard code something? Okay, yeah, because we hard coded this. This is just an assertion, and now this assertion is incorrect. So if, right, because now this got changed to 9. Error. Did you refactor right, so if this gets tripped, we're going to have to make sure to refactor in the lib. We have P5D fragment shader code right here. And this has a hard coding that will need to be refactored. So I'm not sure exactly where it is. It's like down here somewhere, I believe. I think it's hard coded near the end. Let's just look for OSDEX. Looking for where we're assigning it. Man, we have a lot more stuff that says OSDEX in it than I thought. Right here. Right, so these are hard-coded right here. So we have to change that. So, so we'll make a little tag there so we can find it a little bit easier. P5D 1OGL dot fragment. Control F for this, right? So we want to Control F for this to find it. And the file we want to look in here, this is the actual file, right? So we have the file we want to look into, and then we have what we want to Control F for, right? So we're just making this kind of nice little note to help us narrow it down, what if we get this error, right? So if we get this error, we want to know how to rectify the problem. And that is going to be part of rectifying the problem, right? So, okay, so we changed this to a 9 because everything got shifted down, right? So if we look in here, right, this is now a 9 because this thing here is defined over here as 0. And we're just going to keep the sequentiality of this by just saying, you know, 0, 1, 2, 3. We kept the sequentialness, so we'll duplicate these definitions as we hit them, right? So once we hit the 15th, we're going to duplicate this and paste this down in the sequential strip of numbers, just so that we can, just to make sure that we don't accidentally stomp on any memory. I think that will be helpful. So we still need to remove the hard coding here, change the hard coding to 9. But before I do that, I want to verify that I can still get things running and that I can see it not behaving properly. Where I want to see it where I try to like get it working and it just doesn't work. So the error message here, I'm guessing that it's well, let's look at where we were. Where did we write that code? Did we write that in shader code, or did we write that in? So in PAINT5D, it looks like, for whatever reason, there's no air macro. Wherever we are, there's no air macro in this section. We have a log, but we don't have an air. That's fine. That's easy enough to fix, right? So we'll define ERR as, you know, AAC 2020, PAINT5D, and then halt, right? Because it's the halting situation. And then we'll just do keyboard handler to get down to the next section. So keyboard handler key in, and then down here we'll just undef and undef ERR, which is the 6th macro, and then we'll give that a run. And then once we have the shader kind of being able to inspect the memory, even though there's like more things we could do, I'm not confident in the shader being correct because... Oh, no, it's because we already removed it and the compilation failed. That's why I'm seeing that message. So if we go P for pattern, and then we go like Y and N, refactor P5D AD value, right? So we have a little message here. And that's kind of what I didn't expect that. I thought that we were gonna... did we not change the code? Is that what happened? So let's copy this. Let's go into where we wrote that code. Did we, like... Oh, sorry. Wrong thing. So if 9... Right, we changed it to, like, assert equal, and then if 9 is not equal to what it needs to be, then we're going to throw error. So my bad with that assert. Okay, so P for pattern, And then if we do like y and n, I'm going to expect just not to see anything. Yeah, y and n, we just don't see anything. If we do 0 to look at the memory, we can see here, oh, here's some memory, right? But for whatever reason, we don't see anything working, right? And the reason for that is because now the variable slot has been shifted over to this 9 here. So if we change that, then we're going to expect everything to work properly. Now, if it doesn't, then I'm going to be kind of scared, because I don't want to break more things, right? We're trying to fix things, not break more things. So I'm hoping that's the one slot where the hard coding is going on for that variable, right? Because that's the one variable that we can kind of confirm is doing stuff for us, right? So P for pattern, and then Y and N, right? So there we go. So Y and N to kind of like go back and forth through this tile set. Excellent. There it is. Cool deal. We can go to 0. We can see the variables that are stored in here. So you'll notice we got this kind of tooth comb pattern. That's because we use 4 pixels to store one variable, which is a little bit wasteful. But that's the way we decided, because we have a lot of variables that need 4 pixels worth of data. Maybe that'll come back to bite me later, but for now, that's the way we're doing it. And, yeah, so now we just want to get something here, 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 and here, just to debug with, right? So to do that, let's add some stuff in our key bindings for that. So go into key bindings, and in the PAINT5D system, let's just add some key bindings for debug, right? So, so @vid IID, and it's video number 0135, and the time is 1 hour and 17 minutes. Debug vars. Alright, so these are debug vars. Okay, and we're just gonna do like ./P5D debug1, right? So we're gonna name it kind of similarly to how it's named up here: D1, D2, D3, D4. So debug1, and that is going to equal I really don't know what key that's going to be used for. I know that on my left hand, I'm kind of reserving everything on my left hand for useful things. So I'm thinking maybe we do like JKL. How about JK, M, and N? Yeah, so like J. So JK, right? Keep it kind of in this quadrant kind of things. So JK, M, and N, or N and N. JK, M, and what's this? Okay, so that's not gonna fly. UIJK. U, I, J, and K. So they're kind of like arranged in a kind of a box pattern. That's kind of why I'm picking those letters. And let's just make sure that we don't see anything like that in the code already. So I is camera control up, huh? So how about U, O, J, and L, maybe? No, J and L is already. Well, how about this? There's probably, D is probably already used. You know what? Let's just do this. Let's just use one character to set all those variables. right? Because we want just a sanity check, right? Well, hold on. I think that being able to set individual variables is good, because then we can confirm that the texture kind of does it correctly when we're just updating 1 pixel worth of stuff, right? So let's just select values that are just not used, right? So I is already used. What about O? O is already used for output. P is for pattern. God, we use most of these things, right? So K. Well, we could just use it to cycle through these different variables, right? So you press U, and then... Oh, I see. How about, K's already been used, right? So JK, that's already used. K and J. Okay. So for now, let's just say... Let's take all these here. We're going to say, you know what, we really can't... We don't have enough keys for all this nonsense. So let's just call it P5D bug for debugging. And it's going to be the U key just because that's what we have available to us. So no other reason besides the U key hasn't been used for anything, right? So we can see if we have V for debug variables. No, that's probably not a thing yet. How about F? Yeah, everything is kind of... How about G? Yeah, let's just use U. Yeah, we're running out of letters, right? We got a lot of commands minded here. Fine, we'll just use the U key, that's fine. And it's for debugging. And then in here, in the system, right, we have different character keys, right? So P5D pattern, P5D output. Debug variable test. So over here, we're going to make like a debug variable test. Right? And that's going to be like, you know, if, I see we did like this extra indentation. I don't really think that was necessary. Because I feel like it's kind of like if char key equals, and actually if key P5D dot P5D bug equals CHR key, right? So we don't want to accidentally overwrite the character key. Oh, I see. Because these are both variables, it's less detrimental to overwrite the character key than it is to overwrite these kind of like bindings. So that's kind of why I wrote it this way, right? So there's no Yoda expression we can do. So now we could do like this. We could do character key, and then we could do this. We could do 0 plus character key to make sure that we can't accidentally overwrite the character key, right? Make sure that there's no accidental assignment. And with that, we'll use like the tau depot put command, right? So we can look at tau depot here, tau depot. And there should be I think there would be a notes file, right? I guess not in Tau Depot. Let's look at Tau Depot data. Maybe there's like a... Maybe the functions are... Nope. How about Tau Depot functions? Tau Depot? Oh, here we go. So here's our put command. So let's steal this for a second. And what we want to do is we want to put something that's going to give us an interesting color. So over here, we're going to steal this. And PAINT5D debug 1. And we're just going to say... you know, U32 right, we're going to actually use some values that kind of like give us something interesting. So we're going to just say, you know, I'm actually just going to make them like red, green, blue. Oh, sorry, blue. And then we can just make this all white on the bottom. Red, green, blue, and white, right? And we may want to do something different for each corner so we can verify those corners are what they're supposed to be. So we might want to rewrite this a bit. So we might want to glue that there, get rid of that, and then U32s, this is this and that, right? So there's the variables that we need. And over here, what we're going to do is we're just going to set them to some different things. So we could say CMYK, right? So we could do or we could say put bits before this, right? So red, green, blue. So we could go magenta and then put bits before this. And then put bits before... This is already a tertiary color. We screwed up there. And put bits before this. Right. So now we have magenta. And then we have red and green, which is yellow. And then over here we have red, green, and blue, which is cyan. And then we have, you know, we have white again, right? So we'll use that. And this is going to be D2. And then for the next section, we can do something like, let's do a macro for this kind of section here. So let's do like, you know, define put. As you know, this Tau Depot put, right? And then oh, now I can kind of see why we might have indented things like that. So these put commands, let's just call them put. And then, you know, define tau as this thing here, right? So tau, right? Define sub as this thing here. And then the variable, define D1 as this. D1, D2, D3, and D4, right? And we just want to do this to kind of shorten things up. And then define x0, x1, y0, y1, right? So we'll make these are the inputs. And if we do that, we can just make things a little bit shorter, right? So, because this is just getting kind of out of control in terms of the this code block here, it's like a lot of redundancy, right? So I just want to say, you know, I want to be able to say put, and then I want to say tau sub d1, and then the inputs, right? So, and the inputs, right, comma, this, and this, and that'll work, right? So, so now we can kind of shorten up these kind of commands here, right? Right, so red, green, blue, alpha. Right, so these are the 4 pixels for this corner here, right? And then 4 pixels for this corner here, 4 pixels for this corner here. So I'm thinking the top 2 can be bright, and then the bottom 2 can be kind of darker, right? So D3 and D4 can be, instead of Fs, we can just do 88s, right? So, or 80s. Let's just do 88. Just because if we do 80, it's kind of hard to see these chunks, right? So FF, right, we can easily see this chunk, and 88, we can easily see that chunk. So, and then 88 here, 88 here, because that's roughly, 80 is roughly half of FF, right? So then all these are going to be 8s here, except for the FF for the maximum channel. Alright, so this is like a dark white now. So it's the exact same stuff, but now it's dark, right? And D4, D3, D2, etc. Okay, so if we did all that correctly, then what we're hoping to see is 50. Hope to see colored pixels in corners when debugging PAINT5D tau depot memory. Right, so that's kind of what we're hoping for, right? We want to be able to see those colored variables. So let's hope that works. I don't know, we could have made some mistakes, so let's just try to compile, see what happens. And P5 debug, unknown field. Okay, so we gotta go back to our keyboard bindings, because we kind of like, this is an unfinished thought, right? So we're calling this P5 debug, and we're assigning it here. But then when we go up here, well, we have to define it up here as well. So, output and pattern. Let's just do a little division here and say, you know, character P5D bug. Invoke debugging variable. Alright, so just for the debugging variable is what we want that for. And now we'll kind of see what that looks like. So, P5D D1. Struct, blah, 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 probably doesn't exist, right? An expansion of macro. Yeah, Tau Depot public library struct has nothing called this P5D D1. And so we got to go back into into Tau Depot, into the data. So not in here, but we got to go open up the Tau Depot data. And we created the macros, but we didn't create the actual entries, right? So we have macros, but then we also have these bindings here, right? So we have to set those up somewhere. So Tau Depot dex sub 0015. So we have Tau, and then we have PAINT5D variables. So this is PAINT5D. This is all PAINT5D. So just in here, I want to say, you know, I want const U08. So rather than a character, we're using unsigned 8-bit integers. P5D D1. Okay. So D1, D2, D3, D4, right? And these are our debug variables 1, 2, 3, and 4. And they're just for visual debugging. So I might want to note that. Visual debug var 1, 2, 3, and 4, right? And then after we set them, we have to do the same thing. We have to set them equal to their macro values here. So PAINT5D, etc. variables. What's going on here? This is just a big comment. Yeah, it's a big comment. So now we're going to say, like, you know, dot P5D D1 is going to equal the correct variable. All right, so var D1, right? 1, 2, and 3, and 4. We're going to take all those, and we're just going to paste them here. And that should be good, right? That should be, oops. That should be the wiring up that we need to get this working for us. So let's take that for a roll, see if that is everything we need. Let's git bash here so that we can just keep the terminal consistently open, because it seems that it seems like this is just a task that we're going to do quite a lot, right? So okay, so now if we do 1, we can see this editor. If we do 0, we can see this. If we do P for pattern and we hit the Y key, we can kind of shift through these different patterns. That's cool. Now the question is, if we go to the PAINT5D editor, right? This is the PAINT5D editor. When we hit the U key and then we go back to here, we should see those 4 corners light up. So let's give that a shot. So let's hit the U key, and then let's go over here and say, hey, we're close. We're close, but something's off here, right? So we have the RGB, and then we have the CMY, but then down in the corners, that's not, something's missing in those corners. So either we didn't map it correctly, or the render is improper, right? So one of those is the case, right? The render could be off by 1, or possibly the actual location mapping is wrong. So we're going to have to figure out what that is, or maybe the code wired to that key is wrong, right? So there's like 3 different locations where this could be wrong. So the first thing is, let's kind of look at here. We're deciding that we're saying that there's 255 variables total, right? So there's a 32 by 32. So let's just say it's 32 by 32. And there's 2 pixels per axis grouped together. That's a 16 by 16. So what is 16 by 16, right? Like what is that max value when we take 16 by 16? Is that 255 or 256, right? So 255 here seems to be the proper variable. So we at least know that this bottom corner is correct, and it's set here. Okay. So now the next question is in the key bindings. When we actually use the key binding, are we doing... We got D1, we got D2, we got D3, and we have D4. And we see, you know, D1, we see D1, D2, D3, and D4. So that looks correct. So that's leaning me towards the idea that the renderer is off by 1, right? The renderer itself is off by 1, and that's why we're not seeing what we should be seeing. Like, it's registered correctly, but then the renderer, yeah, this looks like the renderer logic is just off by 1, and that's why we're not seeing those bottom corners. The other possibility is that the texture push isn't... No, I don't think that is... Because we're doing a full texture push. So I think that the problem is the rendering code down here with the offsets. Where are we? This is not... We want to look at the GPU fragment shader. So I'm thinking of this rendering code may be like off by 1, right? So... we're dividing the x location by 16, and then we're adding the tx to that's my best guess. My best guess is this. One way to test that out really quick would be to... We have like 16 cells. Something else in the renderer might be wrong too as well, though. So I'm thinking if we divide this by 32 and 32, just as a quick test to get more information, to like make all those debug things a little bit smaller, we might actually see the other colors. That's my guess. Now this is not going to be a correct render, because that really should be a division by 16 as far as I'm concerned, but I just want to get something in there where we can look at it. And I'm guessing, well, that's not really going to map very well, is it? That's kind of the opposite of what we want to do. So U for debugging. Oh, so dividing by a bigger number is actually giving us... Well, that makes sense, right? Okay. So actually we want to divide by like, instead of dividing by 16, we want to divide by 16. I think that's what we really want to do. But div 16. Well, let's divide by 15 instead, right? So we want to condense it a bit so that we can kind of see what's going on, right? So we want to see if we're possibly off by 1, and that pattern is on the texture, but the renderer is wrong. That's what I'm thinking. I'm thinking the rendering logic is wrong. So U, and then over here, yeah, so the rendering logic looks kind of off, right? Because we can see the dark kind of pixels there. And why is that? You know what it is? It's because It's because these clusters of pixels that we're trying to render, we're thinking of them as individual units, as individual cells. But we have to remember that it's a 2x2 pixel cluster, right? So that's what's going on. We have to account for that. So how are we going to account for that? I'm not exactly sure right now, but I think it's... So we're off by 1. Because it has something to do with that 2x2 cluster of pixels. It might be easier to think of it as God, why am I off by 1? I kind of know why, but I'm still kind of confused. So we know we're off by 1 in the renderer, and the renderer is wrong. And that's because each tile is 2 pixels. Are we accounting for the 2 pixel? No, we're not. 32 by 32 blocks. Now, I still can't understand why it's off by 1. I know it's off by 1. I know I'm making it off by 1 error. But I don't quite know why. Why the heck? So, like, each variable is kind of like a cluster of, 4 pixels, right? And we have 16 of these, right? So we have and so this is, dot, dot, dot. So there's something off by 1 here with the way this works. I don't know exactly what it is, but I know I've encountered this problem before and fixed it in my other code, but... right, so over here we got 30 and 31. Then over here we have 28 and 29. And then over here we have 26 and 27. Right, so 26, 27, 28, 29, 30, 31, right? And why is this off by 1? So this is an initial offset here. It would seem that the cell size calculations are off, right? If it's not mapping correctly, that would be a sign that the TX/TY, the cell size is off for some reason. So we're dividing by 16, and we should be dividing by something else. So we have a 32 by 32, and 32 divided by 2 to figure out how many cells we have. Right, we have 16 cells, right? So that's why. But if we have 512, we have 512. How many pixels per cell, though? So if we have 512 pixels, and we have 16 cells, right? 512 divided by 16 gives me 32. Right? If we're dividing by the cell size here, right, to get the TX/TY, then should this not be a 32 and a 32, not a 16? And then 32 times, right? That would make sense, right? But that would be... I'm not sure if that's right, because everything was rendering pretty close to how it should have rendered, and I don't think that's going to get me... Okay, well, let's just go over here. Let's go here. Let's go back here. Let's press U. That's way too zoomed in. So 512 divided by 16 to give us a tile size of 32 pixels doesn't quite work, but maybe this is actually correct and something else is going on. So... what are these 13s and whatnot, right? Those are, we're looking at kind of this cell over here, right? So we're trying to get the base pixel for... Uh-huh. So the TX is a local. The TX is a local coordinate, right? It's a local local X. Right, we're trying to get a local X and a local Y. And then, int32, let's just do int32 TX, local X. And then do a local Y. Let's do LX, LY. And then we'll do like a global. And then over here, let's just rename this. All right, so we're saying that the local X, local Y is this. And then we add the local X, local Y to this to get a global X, global Y. And that's what we use to sample from over here, right? And something about this is incorrect. Um, yeah, so whatever. Let's just try to give this a run. Let's give this a run, make sure it gives us the original result we were getting, and then try to figure out why we have that off by 1 error. I know it's an off by 1 error in the rendering, I just don't know. I know kind of why it happens, but obviously not enough to fix it, because I don't have a good grasp of the math. But I know it has something to do with each one of these cells being 2 by 2. So this should be really kind of easy. Right, so we got it correct on the thing that's kind of concerning is we got it correct on the X, and then it's the Y that isn't correct, right? So the X, it's fitting on the X, but it's not fitting on the Y. That's a clue. So what are we doing on the Y that's not correct? Well, on the Y, we have this different mapping here. And we were kind of certain of ourselves that that was the correct way to go. Are we perhaps... We know we're off by 1, but we could be off by 1 in terms of the cell we're looking at, maybe, huh? So the X is 13 because... Why is it 13? Because 15, 14, 13, right? Okay. 15, 14, 13, 12, right? Is that why that's a 12? Yeah. So we know it needs to be just compressed by... We know if we just add a 17 that it'll probably work correctly. But we got to think about, like, why would that be, right? Like, I'm guessing just adding a 17 will get it to render correctly, but I don't know why that is, right? So, or actually, was it a smaller number or a larger number? Either a smaller number or a larger number is what we need, and I'm not sure why that is. So, if we do this, so not 8. So now we're off by 1 to the wrong in the wrong direction. We need a 15, right? So we need a 15. And if we do that, we divide by 15 instead, then we're over here, we press U, we go over here. Yeah, if we divide by 15, yeah, we can start to see everything. But I'd say that's not the math, right? Like, everything's not correctly snapped now. I'd say the division by 16 over there was correct. Right, this division by 16 is correct. And the mistake I think we're making has something to do with these offsets here, where... we're not trying to render individual cells, right? So I think what kind of is going on here, because we're not trying to render individual cells, is that once we know where we are here, this is actually like the top left. This math, I think, gives us just the top left pixel. of what we're supposed to be rendering, I think, huh? I think. Yeah. And alright, so I think what's happening with the math is that we're getting this top left pixel here, we're getting this top left pixel here, top left pixel here, top left pixel here. That's what we're mapping to. That's how the math is working. But then we have to figure out if we need to offset by 1 or not, right? So to figure that out, we have to figure out what section of the tile we're in, right? So if this is the local tile, right, we're dividing by 16. Then we want to figure out what well, here, let's just +1 to all this, right? So my thought is that sometimes we need to +1, right? So I'm thinking if we +1, we might see kind of a rendering that looks... it's still not going to be correct, but it should have the lower bounds. The lower bounds should be visible if we add a +1, I'm thinking. And so we have to kind of figure out what segment of that... of the cell, of the variable cell we're in, right? So I'm thinking that's what the problem is. So let's look at this. So that's kind of still not correct. I'm thinking that what we really need is like a +8 to get that really in view, don't we? Like, is it a +8 we would need? Or actually like a +7, right? Well, +7, because 0 plus 7 is... 0 to 7 is 8 locations, right? So that's why I'm saying 0 plus 7 for the proper offset, or maybe even a 16. So that's like way too far in. Yeah, I don't know what the hell I'm doing. So we're so close to getting this, but I just don't know. What do we really want to do here, right? We really just want to... We just have a... Maybe we're thinking too hard about this. We have a 32 by 32 section of pixels, and we just want to map that correct selection area over here, right? So what we really want to do is we want to create like a selection rectangle, and then correctly map that selection rectangle to this sampling coordinate, right? So if that's the case, then yes. So let's think about that, right? So that's actually going to account for the off by ones. Is that the if we want to think about how that selection rectangle works, I think what's happening is we're getting an area like this, and we need to like just add one more pixel to this to get the correct selection area, right? So instead of divided by well, let's think about it, right? So in 32, x0 equals, and the x0 is going to be, right, we have this, you know, we have this kind of, this 32 times 13, right? Plus 0 because it's this corner right here, right? But the x1, the upper bound for the x1, though, is a +1 because we're not here, right? It's not, you know, 32, it's not, oh, crap. All right, oh, crap. Yeah, so yeah, I can describe really quick what's going on here. I'm just trying to debug some, let me comment this out for a second. I'm trying to debug the memory by just printing out the texture memory to a shader and looking at what it looks like. So right now, when I do a partial texture push, I'm not seeing, when I do a partial texture push, things are not working correctly. So over here, what I'm trying to look at in this area, these white pixels are actually variables, right? So I have one texture that I use to store a whole bunch of variables. And I'm kind of zoomed in on a 32 by 32 section of pixels where the variables that I'm interested in are being stored. And so if we go over here and do like P for pattern, and then we go up through here, we can see you can see like our data set that we're kind of scrolling through, and that's all good and well. If I press the U key, I can put some debug variables into the system, and then I can look at them. And so my debug variables, oh crap, and then my debug variables are right here, but then there also should be some debug variables in this lower corner, and my shader logic is off by 1, so I'm trying to fix that. Since we do have kind of like a whole bunch of people showing up, I might as well kind of, hey, how's it going? So since I do have some new people showing up, I guess I'm gonna give a quick tech demo. Let's do a quick tech demo. Let's do a quick tech demo of what is currently going on instead of what I'm debugging right now. Because since I do see new people kind of here, I might as well give you all a quick tech demo to kind of show off where we are currently within the state of the rendering engine. So let's go over here for a second in the keyboard bindings. Or actually want to look at the, want to go over here, and let me just put a breakpoint here. So P5D pattern, and I'm going to shove in the default data set that we were rendering earlier. So where are you? P5D pattern. I'm just going to comment this out, and I'm going to load this graphic. So I'll show you what this graphic is for a second. So if we go over to our assets folder, so in our library assets, we have this image. And you may have seen the actual ASCII data layout for this image before, right? So this is how I pack my tile sets, right? So there are 16 auto tiles encoded into here, and we split up the pixels, and we use 2 bits per pixel, 2 bits for each auto tile set. So this, what you're seeing here, is the actual memory layout for the diagram in PAINT5D data. So if we go and we open up the data file for PAINT5D, you'll notice that there's this data layout right here for this. So this is an actual piece of data for that, and we're going to render that. I'm going to show you what that looks like, so you can get an idea of where we're going here, and then I'll kind of explain that data a little bit better in terms of like what does that actually mean? What does that weird pattern that I drew in MS Paint, what does that actually mean? And it's going to make a lot more sense if we can actually just, you know, load it into the engine and just view it. So let's put this over on this side, and let's go over into the editor, and let's go P for pattern to load this in, and then we're gonna go through here, and we can see a few patterns, but let's look at this one for a second, and let's look at the image here. So this is an auto tile set, and auto tiles are usually done with 16 subtiles, right? So the 16 subtile auto tile set is usually known as a Wang tile auto tile set. We are doing a Wang tile layout, but we're going to auto generate the 12 remaining tiles, right? So we're going to create 4 tiles, like an upper left, upper right, bottom left, and bottom right, and then we'll auto generate the remaining missing tiles from these 4 tiles. So this upper tile here is the upper left tile of the auto tile set. Now it's not properly drawn, right? The asset really should represent a upper left corner, but this is just a debug tile set so that I can make sure the rendering logic looks correct. So I thought having something completely symmetric here would be a better debugging visual for me. So this image you're seeing in the top left here is coming from these pixels here. So this quadrant of pixels, we're taking 2 bits from every one of these pixels and using that to render what's over here in the top left. So you'll see that we have these different image sizes here, right? So the largest image size here represents the smallest tiles that we can draw with, and then down here we have tile sizes that are twice as big as these tiles, and then these tiles are twice as big as these tiles, etc., all this, etc., until we get down to here where we have just 1 pixel, right? And that 1 pixel is just a giant tile that fills this entire quadrant, right? So that's the whole idea behind what we're trying to render. And we're trying to create these base auto tiles for our fractal auto tile rendering. So that is what's going on at a high level. Also, since let's close this. My window code needs some fixing. Let's also look at the demos for a second. We'll throw the demos folder in here, or the demo. I know that some of you people have already kind of seen this, but I saw that Wandable, is that how you pronounce it? Wandable. Let me see if you're still in chat here. Wandable. Yeah, so you're still Wandable. So I don't think you've rated before, so I just want to show you the tech demos. So let's go over here for a second. So I made this game, it's kind of like a... Okay, so yeah, you are here. So I made this game, it's like a Bomberman game, but the bombs have different directions. So there's like a vertical, horizontal, and a 4-way. And the bombs aren't like Bomberman bombs in the sense that they don't block your path. They're like these... the bombs are like these proximity mines that you can pass by. And once you pass by a proximity mine, it kind of lights up for a little bit, and then it blinks, and then it explodes. Oh yeah, that's fine. That's fine. So yeah, so it's kind of like a chain reaction explosion bomb game, right? And one of the things that we need to really concentrate on when we're writing a new engine for this kind of game is auto-tiling, right? Because we want to be able to destroy the environment in a way that just looks aesthetically pleasing, right? So if we delete some tiles from the level, we want everything to latch back together in a nice way. We don't want it to just look like someone went into the engine and just like selected a few pixels and just deleted those pixels, right? We want it to actually look nice. So we want to preserve the nice defined edges around the different materials. And the way you're going to preserve nice edging around different material types is by doing auto tiles, right? So we're not just going to do like old school 8-bit graphics in this new engine, though. We want to take advantage of like shaders and just do some really crazy stuff. But we want to just take auto tiles to like a very extreme kind of level. So here's like a little proof of concept. And it's just like auto tiling done with shaders, right? So the final goal is to get this like fractal auto tiling engine that uses like crazy shader logic, right? So if you're familiar with auto tiles, you kind of understand how they work, right? They're just self-aware tiles that they know about their neighbor above them, below them, to the left, and to the right, and they will self-select the correct subtile to render correctly to get like nice smooth edges around whatever material type you're using, right? So when I say material type, I basically mean auto tile set, right? Because each auto tile set has 16 subtiles, and so you can think of an auto tile set as like painting in tiles using a specific material, right? So this is all cool, and then the other thing we can do, right, is we can kind of zoom into this, right? So if we zoom in here, we can go 256 to 256. And, right, we can see this nice detail still, right? So the idea is that we can use auto tiles, but then we don't have to do old school 32-bit or 8-bit graphics. We can actually do like crazy shader stuff, and then we can zoom in at like really extreme levels. And that's just because I want the engine just to look visually stunning, right? What else? So let's look at some of this. So also, I made this engine in ActionScript where the tile map has like different layers, and then we can apply rendering settings to the layers. So this is the same tile map rendered 3 different ways. This is the foggy morning rendering setting, this is the sunset rendering setting, and this is like starry night rendering setting. So the idea is that the artist only creates one tile set, and then you can reuse that asset 3 times, right? So you get 3 times the mileage out of one asset if you can just apply some rendering settings to it, right? So as a small indie development team, you got to figure out, well, how can we kind of like reuse assets because we have a very small team and we don't have hundreds of artists. So how can we kind of leverage the art that we already have and reuse it in ways where it doesn't look redundant, right? So I'm going to try to integrate this tech into the engine for the level editor, and then mix that with this kind of tech here, and then make a bomb kind of game with this. So I'm trying to take like all these different pieces of tech and mix them together. So this is like an old tile editor I did in like Golang. And so currently the system I'm working on is kind of going to be a tile editor like this, but this tile editor is for 16 tiles, right? And the current tile editor I'm going to work on only has 4 tiles that you can draw. So the reason we're only going to draw 4 tiles rather than 16 is because I find 16 tile auto tile sets are very redundant, right? You end up doing a lot of repetitive artwork, and that's wasting time. So if we only have to draw 4 tiles, and then we auto-generate the remaining missing 12 tiles to create a 16 subtile auto tile set, we have sped up our artist's speed by 4 times, right? Because they don't have to draw 16 graphics, they only have to draw 4 graphics, right? So that's a 4 times speed up, right? Because 4 times 4, 16? Yeah. So you might be asking, well, if you're going to do that, how are you going to get those extra 16 tiles? Well, what we're going to do is let's go run this again for a second so that we can look at the schematic diagram and we can look at the rendering. And then I'm going to get back to just doing my thing and just doing my debugging, which is not going to be that interesting, but I thought since it does look like there may be some new people, I thought, let's just show you what I have, right? Let's put this over here. And actually, let's just snap it. Okay. So over here, let's do P for pattern to load that in. And look at this pattern here. And then let's look over here. So the way we're going to generate the missing tiles, right? We have 12 missing tiles, right? We've drawn 4 of them explicitly, but we need 16 tiles total, right? So this upper left here, in this diagram here, corresponds to this upper left here. This bottom right here is corresponding to this graphic here, right? So if we want to create a top left edge tile, we're just going to subselect some of this tile here, and then some of this tile here, and that's how we're going to generate the top edge tile. If we want a bottom edge tile, we're going to take some of these tiles like this. If we want the center tile, you can see this kind of red section in here. So we're just going to take a little bit from each to generate that center tile, and so on, right? We're going to subselect from different tiles to create those missing tiles, right? So we're going to basically generate the missing tiles on the fly when we're rendering. Okay, so now that I've kind of gone over that, I'm going to kind of get back to just doing my thing. So that is the pitch of what's kind of going on right now. So I do not anticipate anything really interesting happening today, just because it's not... It's just me debugging, right? It's me debugging and writing a little renderer to like debug some textures and whatnot. So nothing really interesting is going on today. I'm just trying to figure out what I'm doing wrong to get with my texture pushes to right now my sub texture pushes, my GL text sub image commands where we update just a partial bit of a texture. That is, I'm calling the command wrong somehow. I don't know what I'm doing wrong, and I'm trying to figure that out. And so I'm debugging some of the texture. I'm writing this debug shader so that I can look at the texture, so that way when I do my partial texture pushes, I can verify what is getting pushed up correctly and what's not getting pushed up correctly. And right now, I'm just trying to fix some of the math in how I'm zooming in to a section of that texture. And I know I'm off by 1, and I'm trying to figure out why I'm off by 1. And I know it has something to do with, so this +1 here is going to help fix that. So let's talk about how I'm subdividing the memory, I guess. So I have this gigantic 512 by 512 texture, and I'm using it to store a whole bunch of variables. So instead of using uniform variables, I'm using a giant 512 by 512 texture to store different variables for different systems. So within this 512 by 512, I'm using this last cell here. This cell here is a 128 by 128 chunk of pixels out of this 512 by 512. I'm taking this 128 by 128, and I'm further dividing it into 16 subcells. And these are going to be numbered depending on what editor I'm looking at. So editor number 1 is PAINT5D. So this cell right here is a chunk of 32 by 32 pixels, right? Because this is 128 by 128, and this is a 32 by 32, right? Because 32, 64, 128, right? So within this 32 by 32 chunk of pixels, I'm storing a whole bunch of variables for the PAINT5D system, and each variable gets 4 pixels. So what I'm trying to do is I'm trying to zoom into this 32 by 32 section on the texture, and I'm trying to set a debug variable in this corner, in this corner, in this corner, and in this corner, and just verify them on the texture in my rendering. And what's happening is that I'm seeing up here and up here, but I'm not seeing down here and down here. So like I'm off by 1 somehow in my rendering logic, and I'm trying to fix that. So right now, I can comment this out and kind of show you what that's all about, right? So kind of show you what I have so far with the debugging and what I'm seeing versus what I'm expecting to see here. So okay. So if we go over here, you can see that white, this is some variables that are already set. If we go over here and you do the U key, the U key sets the debug variables in the corner. And then if we go back to the viewer for the texture memory, we see up here, this corner, the variable is set. This corner, this variable is set, right? Because each variable gets 4 pixels. So we see up here, but we don't see down here and down here. And I've already verified that the problem is that the rendering logic is off by 1 somehow, and that's why we're not seeing down here and down here. Like it's like these chunks of pixels are like just right off screen right now. So something is off with the logic, and I know it has something to do with the fact that when we're thinking about the region of pixels that we're trying to map to the screen, because it's a chunk of 2 by 2 pixels, right? Like each one of these cells is 2 by 2 pixels. We know that on the x-axis, on the lower bound inclusive range is going to be this cell right here. So we're going to go in here, but we're going to take this pixel here, right? And then in the upper bound for over here, it's here, but then we add 1, right? So the inclusive range that we're looking at, we need to account for that off by 1. And so if we want to create like the inclusive bounds that we're zoomed in on, this would be what we need to do, right? So we see this 32 by 13 and this 32 by 12. That's just some of the offsetting math, right? And so we can see this 32 by 12, this 32 by 13 and this 32 by 12 here as well. But this math here is not accounting for these off by 1s. And I don't know exactly how I need to account for them, so I'm thinking of just rewriting the math a little bit so that I can just map to the selection rectangle somehow. So I think that's what I'm going to do. So we want to take a section of 32 by 32 pixels and just map it into this selection rectangle. So I don't remember exactly what the math for that is, but let's just try to get it working, I guess. So the first thing is that this math is doing it in terms of 16 cells, right? So 1 cell, 2 cell, all the way up to 16 different cells. But really, we want to do it in terms of pixels to avoid confusion, because I think this math is just not doing us any good. So we want to take this value, which is between 0 and 511. These values are between 0 and 511. We want to remap them to 0 to 31, right? So we want to remap those to 0 to 31. So I'm thinking that the local x is going to be the local pixel x, right? So the local pixel x is going to equal the canvas user view integer x location, and we're going to divide that by, I believe, 32 will give us 16 unique cells, I believe. So if we look at, let's just get Google over here for us for a second. So if we do 512 divided by 32, we get 16 unique locations, but we actually need 32 unique locations, don't we? No, it's 16 here, right? So 512 divided by 16 gives us 32 locations, right? Now, is that... It gives us 32 cells, right? So if the tile size is 16 pixels, then we get a 32 by 32, and that's 1 pixel. Okay, yeah, so that's good. Okay, so hold on. Let's get a calculator up in here. So 512 divided by 16, right? Gives us 32. Okay, so this local x, and then this local y and divide it by 16, right? So this is, you know, local pixel location xy, right? So this is the local pixel location. And it's x and y. And we want to assert that, well, it's not really going to matter. We can't really assert in the shader code, so we're not going to be able to write an assert. But we're going to assume that this is between... we can just write the assert anyways, because eventually we might want to test this on the CPU side. We want to assert that, you know, Lx is greater than or equal to 0, and Lx is less than or equal to 16 minus 1, right? Because 0 to, or actually no, 32 minus 1. Right, because 0 to 31 for the addressing of this. Okay, so just assert macros for this, so they'll be removed when it's compiled as GLSL code. So once we have the local x, local y, we need to map local xy onto global pixel using the selection rectangle, right? So we want to use the selection rectangle to map this to a global coordinate. So let's just comment all this out for now and figure out how we're going to do that. So we have the global. So we're going to use this selection rectangle as the remapping. Okay. And the local x, the local xy should, the number of coordinates within this selection rectangle. So this is a global selection rectangle, right? So this is the global coordinate space selection rectangle to zoom into, right? So this is what we want to zoom into. So the first thing we want to do is... Okay, so the gx is going to equal the... We should just be able to take the... We could take the origin of this, and then we could add the local x, right? Now the problem with this math here is we're not accounting for the squashing and stretching that could be going on, right? So there's some squash and stretch here. And how does that... How do we remap that? I don't quite remember how I'm going to do that. So let's say that, you know, if everything's snapped correctly, we probably don't even have to account for those upper bounds. It'll just work. But we should think about the correct math for this. So let's just, we got LX, we got LY, or LX and LY. X0 and X1, GX and GY. And, let's just do, but if we do that, we're going to get, we need to make sure this compiles. So if we're not going to use these upper bounds, we're going to have to comment them out for now. So I'm thinking that since there's no squashing and stretching, that'll probably just work correctly. I don't know for sure. I'm still kind of uncertain about the math, but let's just try that out. But this is just going to be me debugging and not knowing how to do math. This is mostly what's going to be going on for the foreseeable future. And if we can't get this working, if this doesn't work, I'm going to have to think a lot more deeply about how that remapping math works. So yeah, something about this math is not correct. And so we're going to have to think about what that is. So boy. Okay. I don't know. Like, this is hard-coded. We should probably figure out... Well, I mean, these bounds aren't even correct, right? Because this bound is the same thing, but then, you know, plus 1. That's not correct in terms of the pixel bounds at all. Really what this would be a... if we wanted this upper bound to be correct, it would be... plus... if this is plus 0, if we add 1, we're over here. So this would be more like plus 31, right? Right, like this upper bound would really be... this upper bound would really be plus 31, right? If that's how we want to do that. So yeah, let's think about how we're going to remap the logic and come up with like a formula we can reuse. So we have a... so we want to remap a coordinate somewhere in here. So we have like a... we have 2 coordinate spaces, right? So we have something like... so we're going to have more variables than we actually need. But let's just try to think out this problem for a second, right? So we have... we have source x0, source x1, right? So this is the... we're doing this in terms of inclusive bounds, right? So, sorry, that's wrong. So, right, so this corner is defined by the lower x and y bound, and then this corner over here is determined by the inclusive upper bounds of what we're looking at, right? So this over here is the x1, y1, right? So we want to take something within this region, right? And we want to remap it to something somewhere else, right? So we want the source and destination rectangles to both be in the same coordinate system. So so DST, source and dest, right? So we want to map something, right? So we want to map a coordinate here within this selection here, and we want to remap it to somewhere in here where everything is completely proportional, and we don't want to be off by even 1, right? Like, we're off by even 1, then we're just kind of in a world of hurt, right? Like, we're off... the current reason why I'm having trouble here is because my rendering logic is off by 1. So we need to figure out the correct mapping algorithm, but we need to make sure that mapping algorithm is absolutely correct and we're not off by even 1 pixel. And so that's the thing that sucks kind of when you're writing rendering algorithms is, you know, the math is really easy until you realize that you have to be... you cannot be off by 1, because being off by 1 leads to these, like, catastrophic, well, maybe not a catastrophic failure, but if you're off by just one, it's not just, sometimes it's just, you know, you're off by 1 pixel, but when you're using pixels to encode tile values and you're off by 1, you could be off by an entire tile. Or if you're off by 1 and you're using blocks of memory, you could be off by an entire block of memory, right? So when you're doing tile-based math and you're using that tile-based math for different types of memory subsections, like blocks of memory or tiles, if you're off by 1, you can get just completely different results than what you're expecting, and that's kind of what's happening to me right now. So what I think would be best is to write some type of generic formula that we can reuse in the future, because obviously I can't pull this straight out of my head without thinking about it, and it would be nice to have kind of like a remapping algorithm that I can reuse. Like, for instance, I already have like a index to XY C99. Like, I already have like snippets for this kind of index to XY math, right? So I've already done it enough times where I can whip it out of my head, but this is not a calculation that I've done enough where I can just whip it out of my head. I have to think about it and do this, right? So it's basically like a percentage mapping calculation, right? Because we can take this x coordinate here, we can turn it into a percentage, and then we can use that percentage and turn it back into a pixel coordinate within this coordinate space. So we take this coordinate that's within these bounds here, and we convert it to a percentage. We take that percentage and we turn it back into a coordinate, and then we have our remapping, right? Now, the challenge there is that we would like to do that, but we would like to, if we can, avoid percentage math, right? We'd like to do that transformation, but avoid percentage math. Assume that everything goes into itself evenly, and therefore we don't need any floating point math. Like, all the math should be like evenly divisible. So let's I guess let's think about that. So the first thing is we need like a zeroed out input, right? So let's say that how about, so we have source, we have the source and we have the destination. So do you want to say like, how about source integer x, right? So this is the input x and the source input y, right? And we want to eventually transform the source input x and y to a destination integer x, integer y, right? So the first thing is we're going to take the source x0 or ix. We're going to take the source ix and we're going to zero it out, right? So it's somewhere within here. So if we're at the origin here, we want that to be 0, 0, right? So for that to happen, we have to take source ix and we have to minus source x0, right? Because it's inclusive, right? It's an inclusive coordinate, right? So if this coordinate here is exactly on top of this, then it zeroes out to 0, right? So the first thing we want to do is zero it out. And then after it's zeroed out, we want to scale it. There's some type of scale factor between here and here, right? So we have to figure out that scale factor and multiply it, right? So we want to say that it's the source, the scale factor is called source multiply to DST, right? So the scale factor would be, that's what we're going to call the scale factor. And then the source IY is the same thing, right? So we take IY, we zero it out by taking the origin, and then we multiply by the source scale factor multiplied to the destination scale factor. Now that's only going to work if all of our selection rectangles are perfectly square. But let's not count on that, right? Because we're doing things in terms of x's and y's. So source multiplied to dest, and we'll say, you know, so this scale factor could be a float value, right? Yeah, this could actually... So let's call it like float x and float y, right? So float x and float y. So these are the scale factors. And the destination ix, iy is going to equal this formula here, right? So do we have these in here? So actually, no. So this, once we, it's still zeroed out at 0, 0, right? But the origin is not at 0, 0. So we have to reapply the origin, right? So we have to reapply the origin. And so right earlier we had subtracted away this origin, right? So we had subtracted away this origin to zero it out, and now we have to reverse that calculation, so we have to add this on, right? So that would be, you know, destination x0 is the base, is like the origin of this new coordinate system, you could say, or this new coordinate space. And if anybody has like a better terminology for what I'm saying in terms of math, be welcome to correct me, because I know I'm kind of like just saying kind of stuff and some of it doesn't make sense. So this is kind of like a little bit too verbose, where it's kind of like going off screen. I don't really like that. So let's try to change some of these variables a little bit and make them a little bit more terse. So I'm thinking we have let's just call this source x and destination x, right? So source xy to dest xy. So let's make this a little bit more terse, just because when I'm looking at these formulas, I'm like, it's going off screen. I don't really like that. So the source x and y, and then we have the destination x and the destination y. Oh, hello, thank you. Oh, is this Kool-Aid?
I don't know, is it?
I don't know, maybe.
I don't know. Maybe you should open it.
So,
Get down here.
So I woke up with a headache and a sore throat, so I don't know what
I
that's...
heard, yeah.
Aha. Yeah, thank you.
So, see if you like that, and if you do, we can get more.
Okay. Alright, thank you.
Okay. We'll see you later.
Okay.
I'm gonna get close.
See you around. Stay out of trouble.
Stay out of trouble.
Okay, so source x, destination x, source y, destination y. Let's also try to shorten up these variables as well. So we have let's just say source x, right? So let's change what we name these. So let's just do sx and sy like this. Let's name them like this. I know it's kind of like more terse, but it's just, we want these calculations to kind of fit on the screen a little bit better. And right now the formula is getting a bit long. So lower bounds, upper bounds, right? Then down here, right, this will be dx0, right? So this is a y. And then over here, this is going to be dx1, and we'll change that once we right? So, okay. So now we have the lower bound of the source, the upper bound for the source, the lower bound for the dest, and the upper bound for the dest, right? So let's just change this formula around here. So we're just going to take these and change these, right? So we're just going to refactor here for a second. And then okay. So this thing is kind of like let's just call it fx and fy. Or we could say SD, right? SD for source to destination. Or factor x and factor y, I think makes, yeah, so float x or float y, but it's also a factor. That makes more sense to me. So yeah, we got to figure out, well, what is the multiplication, what's the scalar that we have to use to squash and stretch this coordinate space into this coordinate space, right? So if we think about that, factor x is going to equal we should just be able to take this range divided by this range, or that range divided by that range. One of the ranges divided by one of the other ranges, right? So if we take this and divide by this, we're going to get a number that we can... So A divided by B equals C. And therefore, we could times by B to get A, right? So we want destination divided by source equals the factor, right? So the factor times the source gets the destination, right? So we take the destination divided by the source to get the scale factor. And that means that algebraically, if we take the division by us and when we times it to get rid of it on this side of the equation, right, that means that D equals the factor times the source, right? So the source times this factor gives us the destination. So we want to take the destination divided by the source range, and then we'll get the scale factor, right? So let's do that. So that means we need to go dx dx1 minus dx0, right? The range, and plus 1, because this is an inclusive range here, right? So if this was 1 and this was 1, it would be 1 pixel. So it wouldn't be 0 pixels. So we need a plus 1. So we need this range, and this is the destination minus the source, right? So we're going to take this range, the destination range, minus the source range. So we have the source, and is there anything off by 1 here? I mean, I don't know if these calculations are off by 1 yet. So I might write a little bit of JavaScript to make sure this is correct, or write some tests or something. So float x is going to be everything. It's going to be y, right? So we're going to change these to y. Okay. So dest divided by source equals scale factor. Dest equals scale factor times source. or right, it's multiplication, so we can flip that around, right? But we know we have to take the scale factor. So this is the scale factor, and this is the local coordinate on here, and then we apply that scale factor, and then we apply the new origin, and then we get this new remapped dx dy, right? So this should be the correct math for what we're trying to do here. So well, let's create this as a final kind of snippet, right? So let's try something like so x's and y's. So we have source. Oops. So right here we have source, and then over here we have dest, D for dest. And then right, so this is top left right here. This is top left, and this is the bottom right pixel, right? So that's kind of the formula we need. And the question is kind of like, where can we put this code to where we could try to give it a test, right? So we have this mapping logic. Can we kind of throw it into this shader code and just write it as a function, so that way we can just reuse the function, and we could also write some type of test for it to make sure that this function is correct, right? So let's go over here and just write like a utility function, right? So we know that that we want like a ivec2, or you want an ivec2, right? Because we want to return an x and a y, and it's going to be in GPUView, and it's going to be source source convert to dest, right? Or it's we want to do source src source rec we could say source rec, or we could say rec src map to rec dst, something like that. And then in here we could actually do like a int vec4s, right? So there's 4 coordinates we're going to need for the different bounds. However, that's going to make things a little bit harder to understand. So I think we're just going to expose all the variables just to make it a little bit easier to understand. So we're just going to say, like, you know, int32 sx0, right? We're gonna just shove it all in there, right? So this is gonna be ugly. We're gonna shove them all in there and make this kind of signature kind of like very bulky. Because we know that we want the source locations. So this is the source, X's and then Y's. Do we want to do it like upper left like that, or do we want to do it? That's usually not how I write it though. Usually I write it X's and then Y's. So usually I do X's and then Y's. So and then zeros and ones like this, right? So it's the bounds, right? It's the bounding box of the source, right? The upper, the left and right bounds and the top and bottom bounds, right? The bounds on the X, the bounds on the Y. That's usually how I like to organize things. So let's organize it in the way I usually organize the code rather than doing it a different way that's going to be irregular for how I usually write this kind of code. So let's take that, and this is not source, this is the destination, right? So, and let's put some commas here. And rec src bound left, right? This is bound right. This is bound top, and this is, you know, bound bottom, right? So we could just make a little commentary as to what these things are, right? This is the rectangle source. This means this is rectangle dest, so rec dst, right? From general to specific. Generally, it's a rectangle. Specifically, it's either source or destination, right? So, and then what each specific attribute of the rectangle is, right? So this is conceptually a rectangle, and this is conceptually a rectangle, but we're not going to pass it as a IVEC4 just because it's going to be harder to understand what we're looking at. Okay, so now we're going to just steal kind of like the code we've written, right? We're going to take our notes. We could take our notes as well, right? So we have some notes. Maybe it would be good to put those notes in here. I'm not sure. It's probably better just to keep the notes in the source code because you're going to look at this a month from now and you're going to have no clue what the math is actually doing unless you have kept some type of notes, right? So we could try to compress this a little bit, right? So we could say, right, we could say, right, so we could get rid of the DST X1 and etc. We could actually let's go see if we can. I'm gonna get my clipboard stat going here, and I'm gonna steal all these variables really quick and create shortcuts for them. So let's go look at our big shortcut list thing here. Let's close our Newgrounds emails. I don't know what's on that thing. Hold on, let me move this over here because I have no clue what's on that tab. It could be anything. Okay, so over here, let's really quick dump the clipboard. So cs dump my clipboard stack. And let's see, do these variables actually exist in my documentation? Okay, how about dst x1? How about dst x1 properly? Okay, so I'm thinking that these variables are a little bit too terse. So if I see something like this, I want to change them around to what they would be, to the more correct versions of them. So if I type something like this, or dashed out like this, we're going to catch like many different ways that I could accidentally spell this and put it into my shortcuts just to canonicalize my variable naming conventions here. So all right, and then we can steal this. Then we can use an underscore instead. All right, so we're just going to do like all the different kind of permutations we can think of. We can also get rid of these spaces. So if we get rid of the spaces, we get something like that. What else can we do here? Also, we can type this out. So source x0, whatever the hex. So source versus dest. And then we can also underscore that as well. We're just going to make a whole bunch of synonyms. I know this is like I said, it's not going to be too exciting what I'm working on right now. It's just me trying to... So I like just to document my variables and exactly what they mean, so that when I'm doing my code, I know exactly what I'm looking at. So any of these, we're just going to say SX0 for this. And this is going to be SY0, right? And then over here, this is going to be SX1, right? And this is going to be SY1. So we got X's, XY, 0, XY, and 1. And this is going to be DX0. This variable here is going to be dy0. Okay, over here, this is going to be dx1. And then over here, we're going to call this variable dy1. Okay, now the other thing is, do we have the correct variables anywhere? So if we do xx0, do we have that doing anything? No. So if we type sx0 from now on, we're going to say that this is correct. That this is the correct variable name. And we want to do that for all of them, right? So x, y's, and z's, etc. So we have the source. We did x, and then y, and then 0 and 1 like that. So x and then y. And then zeros and ones. Okay. I'm going to make sure that none of these are the same. And so then we just want to copy this and do the destination, right? So destination variables are the same thing, except instead of s, we have d's. And I know this is kind of tedious, but the idea is that have you ever gone back to your code and you've looked at a variable and you're like, okay, the variable tells me what it means, but I don't know exactly what it means. And then you kind of get confused about the logic. I'm trying to avoid that kind of situation to where when I have a variable, I know kind of like exactly what it means in my code. So that does take a lot of upfront effort where, you know, a lot of times I'm going to spend like a decent chunk just documenting variable names. And the hope is that, you know, eventually you'd think that this would eventually end, but there's always like different variable names that you can come up with. But standardizing the variable name and saying that anytime I'm doing this formula anywhere in the entire code base, I'm always going to use these exact variables, right? So that's the idea, is just to standardize what variable names I'm going to use in the code base so that it's very easy to know exactly what code I'm looking at, because I don't have to even look at the whole formula. I can just see the variables that I'm using and know exactly what's going on. So with that, let's so now there are some like things that we could do wrongly, right? So we could say, if we do like something like dx or sx -1 or xx1 like that, or source x, so source x1. I don't know. So if we have something similar like that, we're going to do like, you know, sx1 And we'll make this for the y. Or actually, no, hold on. src x0. Did we do one of those? We already did that, didn't we? How about this? We already got that. And that's not going to work very well, is it? If we do sx0, sx0... Oh, I see, okay. Never mind. I'm just thinking all the ways we can type something close to what we mean, but not exactly what we mean, so that it corrects us and gives us the actual variable. So we want to kind of converge onto this variable, right? And we want to think about how many different ways we can kind of spell that. So source x or source sx dash 0, sx dash 0, 0, sx, right? And I'm kind of running out of ways here we can do this. Let's just copy this and paste it a few times. So this will be the upper bound for the x-axis. And now let's just copy all this and change these to y's. And then we'll copy it again and change the x's to... We'll change the s's to d's, right? So this is the source variables, typed in many different incorrect ways. And then we want to do the same thing for the destination variables, right? So where we're seeing s's, we're going to take any s that we're seeing in this code, and we're just going to replace it with a d's. And let's just move this over here for a second, right? And just say, you know, we're going to place the s's with the d's, right? So find next, and just kind of go through here. Find next. Let's match the case. Okay, so now it's just the source things. And now we're just going to replace like source with dest. Okay, now we'll put these over here. And now we have like a decent block of, right, this is a pretty hefty block of variables, right? And the idea is that there's like many different ways we could write a variable, and we just want to make sure that we converge onto these 4 choices, right? So anything that's not these 4 choices, we're going to make sure that we don't use the wrong, blah, I'm not explaining this well. We just want to make sure that we use exactly those variable names, that's all. So we're looking at this code. Now for this thing here, right, this variable name that's in the comments, that should remap, right, that remaps to dx1, right? So that's just so we can make this diagram a little bit more terse. We can get rid of these commentaries, and we can mash this together a bit. So I have these nice little diagrams, and Sx is here, right? So Sx is here. We have the source x, and then we have dx, right? And we're trying to map source x to dx, right? So we're trying to map the source x to the dx. Right? And So 1. Convert SX to local within S, X or Y, 0 or 1. Once we convert it locally, apply correct scale factor to make local to source a local to okay. Re-add the origin we took away to make local to the dest block, right? So this is the process of what we're doing here, right? So so when we're looking at this, right, the scale factor times source, right, so this is rec. This is rec src, right? This is rec src, and this is rec dst, right? So dst, dst, src, src, and this scale factor, or equals, right? And then we can put this into a big comment block. 1, 2, 3, 4. We gotta make sure we have a little bit of padding away from the right edge because we're gonna wrap this in comment characters. Okay, and then 1, 2, 3, 4. Does that all look good? Okay, that looks good. So let's move this over here. I don't know, like that. Okay, so we have a nice little diagram of what the heck is going on. And then we have the kind of like formula logic over here. But this formula logic is more of a snippet for us. Like we have this function here. We would like to keep like a snippet, this kind of a snippet version as well. So we're going to copy this and we're going to paste it into a snippet file. And we don't know if this logic is completely correct yet, so we're going to have to fix it up as we go. But we know that S is for source, D is for dest, right? So say this as shortcuts. Inclusive coord remap, right? So inclusive coordinate remapping is kind of what we're doing here. And so that's what we'll call this shortcut here. And we'll kind of like put it into some comments like this so we know where this snippet kind of ends and where it begins. Okay, cool. And it is a little bit bulky where it might be nice to make it so that we can indent it a little bit further into the code depending on where it's running, right? So we might want to do this. So that way 3 levels of indentation might be useful in some cases. So we'll write it like this. And let's save this. And we're going to put it into our AutoHotkey folder. We're going to put it under shortcuts. We're going to put it under shortcut files. We're going to put it under CXX for any type of C code. Snip. And we're going to say like new folder. And we're going to say inclusive coordinate remapping. What do we call it exactly? Inclusive chord remap, right? So over here, let's rename this. Inclusive chord remap. So we'll get this nice little name, and then we'll call the snippet file inclusive coordinate remap, so ICR._. And then we'll put this in our shortcut file so that we can reference it later. So inclusive chord remap. So let me put this over here. So right now we're going to go into our shortcut file. We're going to put that in a snippet. Paste file. We'll paste the file contents if you type one of these key phrases. Inclusive chord remap. Inclusive chord remap. Or inclusive chord remap. Or inclusive chord remap. Let's say that maybe we're not going to remember these exact phrases. Like we've come up with a lot of phrases, but maybe we're not going to remember them. So if we type remap, do we have anything, right? So remap we don't. So we'll say if we type remap, try inclusive chord remap C99, right? And then we'll put this over here. As something that we can kind of type, right? So using this is just, hey, how's it going? Yeah, so I'm just working on some like coordinate remapping logic. So it's just like I want to take a coordinate that is in a, so let's say I select some pixels, right? Like I'm working on an anime dude simulator. All right. So are we talking about like a 2D rig? Are we talking like you know how like in cartoons these days, they have a thing called a 2D rig? So once upon a time, there only used to be like 3D rigs, right? So you would do like 3D rigging in computer animation to like rig up the bones, like the joints of a character, so that the animator could animate them. And now in a lot of modern two-dimensional cartoons, you have a 2D rig. And I don't know much about 2D rigs, but that's kind of like what it's, I don't know if that's what you're doing. But on an anime dude simulator, I'd have to kind of see it. I mean, you know, show me when you're done kind of a thing, you know, because I'm sure, like, you know, when you're working on things, right, they tend to be in a very broken state. Like, the stuff I'm working on right now is completely broken because I'm coding it. It's a music game? Okay. Oh. So there is a person on Twitch that is doing a music game. Let me see if I can find them really quick. Let me see if I'm going to go through my shortcuts and see if I can find their Twitch. You might be interested in them if you don't already know who they are. I don't know if I'm going to be able to find them because I was like, here, I'm going to just look through here for a second, see if I can find it. I feel like they might have been on Team Live Coders. So let me see if I can find that for you really quick, since you said you're doing a music game, and I know one of these coders is doing something like that. I think they might be on Team Live Coders, but let's see here. So Team Live Coders, it was like this, man, there's more team members than I thought here. Geez, this is more people than I thought here. Yeah, but let me see if I can find this for you. Back to top. Actually, maybe it's Jessica Mack. Yeah, I think that's Jessica Mack that I'm thinking of. Okay, let's, we can just type Jessica Mack in here. I think it's Jessica Mack. Let's pause this. Yeah, this person. I think this is a music game. I make everyday shooter, co-directed sounds and shapes, C++, OpenGL, shaders, procedural graphics, synced to music. Yeah, synced to music. Yeah. So this is the person I'm looking for. So you might be interested in. Oh, you already finished it? Well, then, well, I'm gonna give that to you anyways because I found it for you. I'm also going to put them in my shortcuts so I can reference them later, next time somebody's doing something similar to that. But yeah, if you want to drop a link in for me, I'll take a look at what you're up to. So I just want to make a note of that though. So person working on music game, and here we can put your name in there as well. So oh, hold on. So let's make some, so Jessica Mack, and I can steal your name as well. Since you say you're working on a, copy that in there. Go back here, put your name in here as well. I might already have a shortcut for you. Hold on. Anime dude. 1, 2, 3, 4, 5. Okay. Working on okay, so let's put a little prompt in here to select either you or this person. Then if you have any links for me, I will take those links as well. What else do I want to put in here? So there's the possibility that I'm not going to remember these very long shortcuts, so we might want to say something like music game and have a prompt to tell us about that. So music game, and then pick person working on music game / PWOMG because this is quite a lot to type. And then we'll put that there. And then we can also make a note of, like, what does that abbreviation stand for, right? So okay. And let me go over here because I was doing remap, C99 remap, Okay, so made some entries here. Let me go check my chat again, see if you said anything new to me. Okay, so there's a link. Okay, let's see what we got here. I'll have to turn off my shortcuts because I know they kind of interfere with. What do you call it? My my shortcuts like interfere with games, like when I try to do keyboard things. So let's see. All right. So let's see. Are we like WASD? Okay, so we got one, and all right. So you're obviously familiar with Newgrounds. Or are you one of the people I messaged on Newgrounds by any chance? Okay. Okay, so I see what's going on here. So, let me see if I understand correctly. You don't have a Newgrounds account. Okay, weird. Because, like, when I look at that, that looks like the, maybe I'm wrong, but it looks like the Newgrounds guy. But I'm pretty old, though, so, like, Newgrounds is, like, kind of, like, I'm, like, 35, 36, 34, somewhere around there. I don't exactly remember. I had to check my license, 1986, so, but back in my day, we didn't have really fast internet in, like, high school, so we played, like, Flash games and things, and, yeah, but that just reminds me of Newgrounds. So, let me think if I understand what you're doing. You're like, okay, it took inspiration from Newgrounds, got ya. So you're trying to make like one of those like DDR kind of games, and what I'm looking at is kind of like your test rig for making sure like all of the animations are working correctly, and then you're going to make something where you have to like hit certain notes, and then the animation kind of like changes as you're like selecting the notes, and then if you get a note wrong, you get a miss. Right, like as these things are flying by the screen, you have to correctly select the keys, and then the character kind of moves around as you're selecting the correct keys, and if you miss and you hit the wrong key and it doesn't match up, it's one of those miss animations, and then there's just like little kind of, what do you would call it, not a taunt, but a kind of like a show-off animation, or like a idle kind of like show-off animation where it's like, it uses sprites from Friday Night Funkin'. So I'm not familiar, but let's go take a look at that. So okay. Let's turn off the sound just so I don't get any kind of copyright strikes here. Okay, yeah, this is what I was expecting. Yeah, this is what I was expecting, right? Like you have a whole bunch of keys that are going by, and you have to press them correctly. And if you don't press them correctly, then you get like that miss animation, right? So I do understand kind of like the idea of what you're up to. So I did interpret that correctly, even though I'm not familiar with this game. I kind of got from the little demo of what you're all about there. Okay, cool. And I think that's good to see something, right? To see something in a game or whatnot, and be like, how did they do that? And to try to code that yourself, all right? Because that's kind of the first step to like, right? When you're trying to make a game, right? You got to figure out how other people did it, right? Or like in art school, we did this thing called the artist study, where we would copy like paintings of like masters to try to understand how they were doing things. Same kind of thing, right? It's like a same kind of deal. And let's well, we can put this into my shortcuts as well. Let's go over here, and let's, I don't know, let's just put it over here. So anime dude simulator. And once again, this may not be something that I can remember, so we should say something like anime dude. And oh, also my shortcuts are turned off, so hold on. So anime dude probably is not a shortcut already, I don't think. Oh, dude, it's already a thing, huh? So let's just say, let's throw this in here for a second and see what we have in here. Okay, now is this, oh wait, did you already, hold on. Let's see, is this the same URL? Did I already see this, or is this another kind of thing here? Okay, now let's check out what this one was. So you showed me this a while ago. I think this was the, like, the camouflage game. Is that what this is? Hold on, I want to make sure I know what this is. Oh, yeah, it was the, oh, because I named it Anime Dude because of your name. Okay, yeah, okay, I remember. And this is the, like, revolving level kind of game, like on a spheroid. Okay, so let me just, I'm just gonna say, I'm gonna just make some notes here. And then I just make it so that I can find both of those links of yours. So if I do a dude game 001, I can find that first thing you showed me. And there's that other camouflage game you showed me a while ago. And down here, where do we put this? So we put this over here. Oh, we can keep that as Anime Dude Simulator, right? And then we can just name this as, you know, A Dude Game 02 over here. Give it the same link. Okay, and then got ya, A Dude Game. So now if we type A Dude Game, are we gonna get the? It's gonna okay, cool. It's gonna give me that. Okay, cool. How about anime game? And then try a dude. Okay, there. So now I have like enough synonyms in here in my shortcuts where if I want to find those things that you showed me, I have enough shortcuts in here where I'll be able to find those things that you showed me months from now. Let me close this. Yeah, so where is, you don't have a Newgrounds, you already sent this, inspiration from Newgrounds. I don't think the music is copyrighted, the game is true. Yeah, it's like, I want to be careful about it, but yeah, I just want to be careful, just because I hate it when, like, part of my streams get, like, muted when I try to go back through it, so I just try to be very, very careful, because you just never know. And Twitch is really good about finding the copyrighted music and whatnot. So I just want to be careful with that. Anyways, I'm going to put this back up on the top screen and get back to writing the code I was writing. So I got this little snippet for mapping ranges, and then I was kind of putting that code into the GPU texture view logic, and... these variables are already being loaded in here, so we're going to actually remove this. And we're going to say, you know, dx and dy. Okay, so we also need a source. So we need a rectangle, and we need a source location. So now I'm not sure how I want to order these parameters. So do we want the input to be, the location to be, want it to be like rectangle, coordinate, and rectangle, or do you want to be the coordinate and then the two rectangles? Well, let's say if we were doing this in terms of conversions, I think that source and dest would be here, and then the outputs would be at the end. The inputs and outputs would be at the end, I think. I don't know. Or do we want all the sources clustered together? Let's not think too hard about this. In32, source X, and then in32, source Y. Right? And so this right here, out is going to be dx, comma, dy. So destination X, destination Y is the output, and the source goes in, destination goes out. And so this in32 here, this frag chord thing, so in32 fx, or actually it's going to be a float 32 fx, and that's going to equal, that's not going to equal anything yet, float 32 fy, and scale factor src to dst x-axis. And then this over here is the same thing, but it's for the y-axis, right? It's a scale factor. And we have to remember that if we're mixing integers and floats together, GLSL code is going to not just let us do that on a whim. So if that's how we want to roll, we're going to have to change how we're doing some things here. So how can we do this? I'm thinking, just make this easier on ourselves. I'm thinking we say float 32. It's not the best way to do it. We could say dx1, right? So we could say, we can make everything capitalized. Equals make float 32 from an integer, and we'll say dx1, right? So, or actually not destination. We want source right, so it'll match exactly, which makes it a little bit easier to look at. And we got the x's and the y's, so x's and the y's for the source location. And then with this math here, we can do a plus, 1.0, because it needs to be floating point. And this is going to be a plus 1.0. And then this is going to be capitalized, right? So this is sx and sy, right? So, and then this sy, this is over here. So the largest y value minus the smallest y value plus 1 to get the number of pixels, on the Y, then the number of pixels on the X for the source rectangle, and then we want to do the same thing for the destination. And so we're thinking for the destination, we also want to convert it to float so that we can easily do this math without having to do any conversions. Right? We're going to do all our conversions up front here so that this gets not too so this doesn't get too crazy, right? Okay. And we'll have to kind of collapse some of this a bit. So let's move this over here. Let's this subtracted from this. Now, why do we have these extra parentheses, right? There seems to be some unneeded parentheses here. So let's remove one of those unneeded parentheses. Okay, so that looks good. So this is the range for the destination minus the range for the source, but this is the X. The range for the destination minus the range for the source, but this is the Y. And then the destination X and the destination Y, we can just keep dx and dy, but we can convert these calculations to back to integers after we're done with them. And this sx will need to be we'll need a float version of sx as well. So float 32 sx equals sx equals make f32 and then sx and then sy. Now the danger of this is that we use macros that are 3 letters, so this could lead us to some trouble later. But for now, let's just hope that this will be okay. And right here, we're going to change this for this. And then this y0 over here. This float x, float y is already correct, so we don't need to change that. Okay, then dx0. And this is dy0, so dy0. And then dx, the dx dy also is kind of being outputted, so we might just want to say, you know, int32 dx, int32 dy, destination x, destination y, dest x, and this is dest y. And we need to make this into a int32, right? So we're going to take the floats, right? So we're going to take this float with this float and all this float stuff, and we're going to convert it back the other way, right? And then we want to return the rec dst, right? So, ivec to rec dst, and rec dst dot x equals the dx, and then rec dst dot y equals the dy, and then we can just return rec dst, and then you can line everything up a little bit nicely. Okay, so we have this formula, and we're hoping that we wrote all that correctly, and we're not even using this function yet. We're just kind of stubbing it in and hoping that it still compiles, right? We're hoping that this kind of formula we wrote doesn't have any weird syntax errors, and we just want to see if it passes as valid C99 code, doesn't have any weird errors in it. So let's give that a shot and kind of see what happens, right? Okay. So we still have the editor kind of like doing its thing. So that tells me that that there's no syntax mistakes here. And the next thing we want to do is we just want to call this, right? So we have this mapping function. So we want to go down to where we're doing all this logic, right? All this crazy logic. And we just want to change this around where we go. We want to put this in here and just say GPU rec source dest, right? And we know the source is going to be so this is the right. So this is the location, and we're going to map it by using this is the source location, and then the source rectangle is, you know, x0, x1, right? It's the x's and then the y's, right? Lower bounds, x's and then y, so lower uppers. So then y0, y1. And this is the... is this the source or destination? This is the destination rectangle, I believe. We want to take a pixel that is conceptually it is conceptually it's a location. Yeah, I'm still getting my mappings wrong here. Well, hold on. We want to take the selection rectangle that we want to look at is... we're trying to figure out sampling coordinates. And this is where we want to sample from. And the bounds we want to use are 0, 0, and then so this is this is the source pixel bounds. So this is the bounds of the source pixel, right? It can be, we're expecting it to be, this value to be somewhere between 0 and 512. This is the bounds of the DST pixel, right? The destination pixel. We're trying to get that destination pixel out of here, right? So this max, we just want to define max as as 512 minus 1. And then right here we can undef that. And we'll just say that global. So IVEC for IVEC2 global, and then global equals a function called here. So I like that a little bit more. Global equals a function called here, IVEC2. This x0, these bounds here, we can unselect that. Okay. These kind of calculations here, we can get rid of these. And we can get rid of these for now. We can add more comment characters to this because this isn't what we're currently running. And we can say, you know, int32 gx equals global.x, and then, you know, int32 gy equals global.y, right? So kind of like really ugly code. We're kind of creating more variables than we need to. But right now we just want to get this working, right? So we don't really care too much about if it looks kind of ugly. So ivec2, and that's what's being returned from this function. And we think that that logic is correct, right? We think this logic is correct. We could be wrong. Maybe the logic is not correct. But we're taking the source. The source pixel is somewhere between this 0 to 512 inclusive range. And we want to remap it onto these bounds here. All right, so we want to take this coordinate here that's somewhere within this inclusive range here. We want to remap it to here. And if we do that correctly, then everything's going to render correctly. Now, if we're not doing it correctly, it could mean that these coordinates are wrong, right? That we have not selected this properly, right? But let's just give that a shot, try to make sure that it can compile, and then if it can compile and we can check out the render, we can just see if this looks correct. And then if it looks correct, then we can use this as a snippet in our code base. We might have to clean it up or something. But let's go use the U key and then go over here for a second and say, nope, we have royally screwed up somewhere, right? So this is even worse than before, right? So yeah, U key, and now it's just completely black. So that's great. So what are we going to do to kind of figure out what's going on here? Well, the first thing I realize is that the x's and the y's, that seems about right. 0 to 31, right? So the cell would be like that. That makes sense. I really have no clue, but we have to get this math working, right? We got to get this math working. We know that the problem could be with the rectangular selection area. We could be off by 1. Let's really quickly change these to 0s and 512s. And make sure that we can kind of see the whole thing, right? So if we remap it like this, well, actually, we can write some test code for this, right? We can write some test code for our transformations. So let's run this first. And then what we're going to do is we're going to write some test code for our transformation function to make sure that it works properly, right? So because we can do that. We can actually get away with that now. We have the means to make that happen, so we'll make that happen, right? So if we go U here, and then we go over here, yeah, we can't even see anything. So U, and it's just completely blank, right? And I expect to see like 2 little dots over here, or like a little series of dots. And I'm not seeing anything down here anymore, which I used to. So let's look at the code for a second. GX and GY equals the global X, global Y, and the global coordinate equals this kind of thing, and the cov, whatever the heck location, is set here. The max is between 0 and 512. So I'm thinking that somewhere in here we're not returning anything or something like that. Int32 SX and XY. Let's make sure that SX and XY is actually used. So making a float 32, that's used there. And then we have this dx, dy. This is the destination rectangle. We fill it out here. Dx and dy is int32. Okay, so yeah, all we're going to do here to try to figure this out is because since it can compile, we can write a test for it, right? So let's take this code here. This is the function we want to test. And let's open up, not this. So in GPUView dot functions, we don't have like a unit test section yet. So we have a init function. So let's create like a unit test, right? So unit test section. And in the unit test section, the one thing we want to test is that conversion logic, right? So we've written our logic so that it can compile both as C99 code and as C11 code, which gives us the benefit of being able to write some type of test code to make sure that we understand that the basic logic works. So we're just going to say something like, you know, U32 AAC 2020 GPUView unit test. Do we call it unit test? I think we call it unit test. And then here we're going to take like a U32 variable called U32, and then we're not really going to use it for anything. So if U32, and then just, you know, reserved for future use, which we're never actually going to use it for anything, but we just want to be consistent with the way we've been writing kind of like our other code. So we want to keep the same signatures everywhere. So then right here at the end, we'll just kind of return 0x00, and then we'll define U32. We'll define I32 as well, because we know we're going to use that. Define float32 as well. I know we're going to use some floats. And then we also are going to need an error message as well. I know we're going to need that. So ERR is going to be AAC 2020 GPUView halt. So we got these macros for the error messages. We'll take them. We'll paste them down here. And then we'll undef them, right? So undef. Okay. 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 So we want to create like a separate unit test function for this. So we're going to say like, you know, AAC 2020 GPUView UTC code, right? So unit test code for rec inc or for rec source map to rec dest, right? So that's the test code for this. And we want to create a forward declaration. So we're going to call this, you know, extern void this thing here. And then it's just going to take void in here. And then we're going to immediately call it. It also means that we need a define for extern void. So define ev extern void. That'll be our fifth define in here. Undef. Okay. And now down here, we'll just create that function, right? So it can be called extern void. Here's the function name. Give it void here as the parameters, and then the logic can go in here. And let's just set up some of these variables. So we need int32 dx0. So x's then y, zeros and ones. So we need variables for source and dest. So we can just steal this and say, hey, here's my variables. Right, so So source dest. Okay, so we have these source and destination variables. And we want to create like a unit test table for different things that we can test here. And then we also want to call this, right? We want to call this somewhere. So in the initialization code, we just want to say, we want to run the test if it's never been ran before, right? So, so we want to say that, if AAC 2020 GPU view if the unit test ran or running is less than or equal to 0, then we'll call the unit test, right? So we're not going to call the unit test if and then we'll have to extern void, void, right? So, actually the unit test is going to be U32, and then it's actually going to return a U32 as well. So U32, and 0x00, we'll just shove like a hex value in there. We don't really care what it is. But that also means that, well, we already have U32 here, U32 there, so that we're good. Then over here, what we're going to do is, within the unit test, ran or running is now equal to 1, right? The unit test is running, and then once we get to the end, it has ran, right? So ran or running. And that way we only need one flag rather than having a running flag and a ran flag. Right, so this is just a flag to avoid unintentional... two purposes. One, to help avoid unintentional recursion. If, like, one test calls another test that calls another test, there could be possible chances that you could get unintentional recursion. And the other reason is that we don't want to call this unit test all the time. We just want to call it the first time we initialize the system, we want to call it the test code. So let's go open up the GPUView data, right? So let's go open up GPUView data. And within here, we have, oh, not GPUView data, my bad. Not not GPU data, but GPUView data, okay? So we're going to open this up and we see, well, we have this extern const. We don't really have anything. So we have this ran or running. It doesn't really need to be anything special. We can just make a U08 variable. That'll be all it needs to be. And we can just say, misc, right? We can just call this misc_vars because we don't really have enough variables in here to really start categorizing them as far as I'm concerned. So we'll just call this section misc_vars so that we can at least put it in a section divider. And then we can define a U08 over here, and then we can undefine it down here. Okay. And now let's, I guess let's keep on going, right? Ran or running is right here. And this unit test, ran or running, we set it to 1 here. We can initialize this to 0, right? We can initialize this to 0, that's fine. And less than or equal to 0, we'll call this test. Cool. And we might want to make a log, right? So we might want to say log begin, right? So we're going to begin the unit test stuff. And then at the end, we'll log that we have kind of like, that we have ended the unit test stuff. And for log, we're also going to need a function for that. So we're going to define log as AAC 2020 GPUView info any. Now we have 6 macros. Okay. So we got the log message right here. We're going to have to put a null terminator here. Not a null terminator, but a void pointer. So we have enough room where we can actually say, like, you know, void pointer casted to 0. We can actually verbosely say what we want to say because we have enough room. So why not be kind of explicit about it? If we have enough room to be completely explicit, we might as well. Okay, so we're going to call this function. This function really has nothing in it right now. So let's make a test table. So we want to take a int32 table of unit test code, tab UTC, right? And it's going to equal, there's some number in here times some other number, right? Rows times columns. And we're just going to make a series of tests for the expected inputs and the expected outputs, right? So now we might want to say, like, this might be big enough to where, right, 4 values, it might get too big. We might want to make it. We might want to make an inputs table and an outputs table. But let's first start off with something kind of simple, right? So let's start off with making everything, you know, zeros. So here's the first rectangle, and then we have some space, and then we have the next rectangle, and then we have the input coordinate, right? So we have the input coordinate here. We decided to do the input coordinate as the first parameter. And then finally, we have the output coordinate, right? So we have a lot of stuff here to where it's kind of getting a little bit, right? Like that's pretty cluttered, right? Let's change this to like 1 space. Right, so we still have this kind of implied table here. Yeah, but we're going to have to do it like this, yeah. So we have this implied table. So this right here is source X, this is source Y, and this is SX0, this is SX1, this is SY0, this is SY1, right? And then over here, this is the destination, right? So these are destination variables right here. And then right here, this output is the dx and dy, destination x, destination y that we're kind of mapping to. So if we do all this with zeros, we're going to expect zeros in, zeros out, right? Because nothing's different, right? So let's say that right here, we're going to define num test, right? So number of tests right now is 1. Number of tests, define num number of columns per test, number of columns, number of elements might be better, right? But if we look at the number of columns, it's obviously not 2, it's actually, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And that's the number. We also might want to do the 0-based, right? zero base to keep track of what the actual indexes are in here. So, right, so this is, yeah, so we have 12 different things here. So we just say 12, right? So 12. Number of columns, number of tests is 1, right? And then in the code, we can go through here. We can say, you know, for the test index, right? So test index equals 0. Test index is less than or equal to the max index. And then a lot of times I say like MTI for max test index. And then test index plus plus. Right? So loop through tests. So we can also say, you know, over here we can say int32 test index. And then int32 MTI. Max test index. And then over here we can set MTI right above the loop. And MTI is going to be equal to the number of tests times, yeah, the number of tests minus 1, my bad. Right, so that's the maximum test index, is the number of tests minus 1. So the max test index is 0 in this case. We want to undefine these things at the bottom, right? So undef number of tests. We want to undef the number of columns. Within here, we want to say, we want to extract the variables, right? So sx0, or sx, let's do everything in order. So sx equals, and we're going to say the table of unit test code, we're going to say the base plus 0, and we'll figure out what the base value is, but first let's kind of get this kind of working here. So we know that all the variables are kind of like this, right? It's like a source, the 2 rectangles, and then the destination, and that's kind of what we have, right? So destination x, this is the source dest. Let's copy these and paste them over here, right? So this is what we have here. And then for the destination variables, we have them over here. And then we just want to say add the correct offsets to get into these things here. Okay. So 11, right? Because 0 to 11, because there's 12 columns. And the base value is going to equal the base equals the test index times the number of columns, right? Because that's the stride, right? So the first one, the first test index is 0, right? So just checking your math, right? So this is the base. So int32 base, base address of current test data, right? So it's the base address of the current test data. And then we add these offsets to get all these values. And once we have extracted the values, we just want to, sorry, once we have extracted these values, we want to pipe it through the function and make sure that the gotten matches the expected, right? So we have to, if we look how we're actually writing the code over here, let's throw this over here for a second, right? This conversion function is written in such a way that it can be valid GLSL code, so therefore we're returning a struct rather than returning by reference. So we need to make sure that we do this the same kind of way here. So if we look at our test code, right, so here's our test code, we need to just call this function. And we just got to fill out all the parameters, right? So we can literally just kind of steal all of this if we want. We can just steal it in there, and we can just throw it in here and paste it, right? So we can make some room here, and just paste that in there, and then we can kind of clean this up, right? So just tab, 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 right? So this is literally all we have to do. Is throw this in here like this. We want to make sure that all of the lax commas are correct, and that if we're going to visually space this out, we have to also make that a little bit different. Okay, so right here, let's say you know, 1, 2, 3, 4, just to get a little bit of space. Right, so we got the source location, the source rectangle, the destination rectangle, and then whatever comes out, right? So we could call this, DST. We could call it plenty of things. I guess let's just call it DST, right? So DST equals calling this function. And then we can say, you know, if dst.x is not equal to dx, or dst.y is not equal to dy, then the test failed, right? We didn't get out what we expected. So error. So we'll call the error function. We'll say that this failed, right? So test fail, and then we'll say what the test name is, and that'll be our error message, right? So that's all I want to do is say, hey, if we don't get out what we expected, the test has failed. We also might want to printf the test index, and we're never going to squelch this printf, so we're not going to wrap it in a log message, because if we crash, we kind of want to know this information here. So we want to know what the test index is, right? So the test index, %d\n, and the test index. Okay. So now that we have that, we're kind of ready to give this a run. But before we do that, I want to take like a break and just do my push-ups, maybe drink some water, heat up my coffee, go to the bathroom, all that kind of stuff. I just want to take a break, do kind of that kind of stuff, and then we'll kind of continue on kind of writing this code here. So we can also take number of tests and number of columns, right, because these are const expressions, and just throw that in there. Maybe we want to just start writing something that makes more sense. So what we could do is we could say if it's 0, 0 and it's like 512 or 511, say 511, 511, and this is 511. If we map it to the exact same things, we're going to expect that 0 in, 0 out, right? Now if we take this and we do this again, and instead of this we have like something where it's like a 256 or something, right? 256, 256. Then we're going to expect the output also to be 256, 256 because that's within that range. And we can just kind of like write some basic test case. These are like smoke test case. They're not complicated. We just want to make absolutely sure that, that these basic cases work, right? So once these basic cases work, basic cases with ISO... Three basic cases, isolate X. So now let's paste this, and we don't really want 3 basic cases, we just want 2 basic cases. So this is the smoke test, and this is 2 basic cases. X and Y identical. So we got 2 basic cases, X and Y identical, then we have 2 more basic cases. We're going to isolate X. So anywhere that we see the Y, we're just going to keep the Y to 0, right? So we're going to say for this input here, we're going to say the Y is 0, and then make sure that this maps correctly. And we can also make sure that this is like you know, 111 or something, or 222 or something. Just something that's not a 511, right? And then make this a 222, right? Because we don't really care about this. This is just the upper bound variable, and this is still a 0. So we got this X. And we're going to map it into, here's the lower bounds, the upper bounds. The upper bound on the X is 511. And we're going to map it to the same thing, upper bound of 511. But the first time we're going to use zeros. Oh, I see. Let's put this up here. Because the zeros, we can't really isolate. Well, I guess we could. We could isolate that, right? So we could isolate this. We have these two basic cases. X and Y identical. And then here where we're isolating, we can just set X. We can just set this to 0, 0, right? The Y to zeros. And then over here, we're going to set this to a non-zero value. Upper bound's 511, 222 for here, 256 to here. This is the output. We're expecting that if 256 is the input, 256 is the output, right? So then we're going to take this test here. We want to say two basic cases. We want to isolate this on the Y. And we want to do kind of the same thing we did, right? But we just want to swap it around, right? So Y. And then this is going to be the Y output here. And then for the bounds, we're looking at the upper bound on the Y. We don't care about the upper bound on the X, so we're kind of blanking that out, right? So we're doing the inverse there. And then we'll make this 222, just make it different. So we can just look at that Y. And then that also means we need to make this 222, right? So we just want to look at that upper bound, right? We don't care about these bounds here, right? So we just expect them to be zeroed out, right? So we have these two basic cases. Isolate the X, isolate the Y, and these are all two basic cases, right? So those cases are pretty basic test cases. If those don't work, then we're in complete trouble. We're not even doing any squashing and stretching yet, right? Or none that we think is happening, right? So, so the next thing is, let's do some basic kind of squash stretch. So, or remap using 1x1 rectangles. So let's remap using 1x1 rectangles because I think that's going to be easiest to comprehend, and it's also going to be a very error-prone thing where if we have any off by one things, it's like an edge case kind of thing, right? So if we have a coordinate 0, 0, and it's mapped into a rectangle that is at, you know, the lower bound is at 0, 0, and the upper bound is also at 0, 0, right? Because it's a 1, 1 it's a 1x1 inclusive rectangle, right? This is a 1x1 inclusive rectangle here, and then we want to remap it to, you know, 511, 511, 511, 511. And then we're expecting that the output is going to be 511, 511, right? So if we want to isolate those axes to make sure that we haven't made any stupid mistakes, we might want to, for the upper bounds, for the bounds on the Y, right, we do X's and then Y's. So let's blank out the Y's. And just say, hey, you know what, your upper bound on the Y is the same thing, and therefore it's still going to be at 0. And then do the same thing for the X's, right? So we're going to take this and we're going to blank this out. And if we blank this out, then, oh, that's not quite right. This is the X got remapped here, and the Y got remapped here, right? So we have 0, 0. We got 0, 0 remapping to 511, 511, and we have 0, 0 where the upper bounds are only on the X, and therefore X gets 511, but this stays at 0. Then we have 0, 0 where the upper bound on the X hasn't changed, but the upper bound, but the destination bounds for the Y has changed. This is 511. Okay, so we have a remap using kind of 1x1 rectangles, but we're not doing anything fancy, right? So the next phase would be to remap using 1x1 rectangles, but do something a little bit more complicated, right? So, origin So let's try to do another chunk of remapping using 1x1 rectangles. Unique non-zero rects. Let's call them non-zero rects, and then we'll take kind of this kind of code here, and we'll paste this again. And we're going to take a coordinate that's like, I don't know, let's say 11, 11, 11, 11, 11, 11, or 2, 2, 2. And then that means that the so on the x, it's a 1x1 rectangle, so it's at 11, 11, 11, 11, right? The upper and lower bounds are the same for the inclusive rectangle. And then on the y, the upper and lower bounds are the same, right? So let's make sure this is correct, right? So we're doing x's and y's, x's and y's. Yeah, so the x's and y's are grouped together. And then we're going to take this and we're going to map it to, I don't know, how about 3, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 4. And if that's the case, we're going to expect 3, 3, 3, 4, 4, 4 out, right? And we could just do that a few more times and just slide it over, right? So we could just do this, right? So we could just say 2, 2, 2, 3, 3, 3, or actually 2, 2, 2, 3, 3, 3, 3, 3, 3, and then we could say 4, 4, 4, 4, 4, 4, 5, 5, 5, 5, 5, 5, and then 4, 4, 4, 5, 5, 5, and then we can make this, instead of a 2, we can make this a 3, so 3, 3, 3, and 4, 4, 4, and then 3, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 4, and then we could make this 3, 4, so this is going to be 5, so 555, 555, 666, 66, and then this is going to be 555, 666, right? So non-zero rectangles, so we have some more kind of very basic tests. So once we get that past these basic smoke tests, it's time to try something more thorough where we have so how about squash, stretch, but both rects at 0, 0. Right, so this series of tests, we could say, you know what, we're going to try a squash stretch test for remapping, like being able to squash and stretch the coordinate space, but we're going to keep both of the rectangles at 0, 0 in terms of their lower bounds. So we're going to say that maybe we have 0, 0, and then 100, and then we have like 200, right? So keep the math kind of simple. So we have our, sorry, let's just keep it, we already checked for transposition errors, so I'm not too worried. So let's say 100, and then we can say this is like 200, right? So 200. And this can be 200 over here. And this coordinate is somewhere within this range. So we're going to say that to make it easier, I think let's think about what is the middle of 100, right? I don't know. The middle of 100 isn't 50, it'd be 49, I think, right? Because 0 to 49, and then... So if we do like, so first of all, 0 to 100 is 101 pixels, right? So this is a bit much in terms of we can't really accurately find the center really quick. So we might want to use smaller numbers here. So we might want to say 0, 1, 2, right? 0, 1, and 2, and then we know 2 is the center, right? So let's actually say that, right? So instead of 100, so let's say 2, right? So 0, 1, and 2. And then we know that 1 is in the center. And then when we want to remap, we could say, you know, we go from, you know, 0, 1, 2 like this. And then we want to remap to something like 0, 1, 2, and then 3. 3 will be our new center. Let's try to draw this one. Let's try to draw this in a way where we can kind of see what we're up to. Right, so 3, and then 4, 5, and 6, right? So we want to go from in, and then out will be, and then we want the output here to be out here, right? So 0 and 2 is the range, right? So we got 0 and 2 for this range, 0 and 2. And then for the output range, we go 0 to 6, right? So 0 to 6, and 0 to 6. Make sure these all still line up nicely. Okay, and if we got that correctly, then we're going to expect 3, right? So 1 goes in, and 3 goes out. But the next thing we want to do, to make absolutely sure this is correct, is we want to, oops. So that's all nice and well, but we want to isolate the different axes as well. So let's isolate x first. So let's just set this to 0 here. So anything, so here's x, here's y. So let's set this y to 0. So it's getting kind of hard to see what I'm looking at. So this, and this series of x's and then y's. So let's set this y to 0 here. And that means y here is going to be there. Okay, and let's steal this one more time. And paste it here. And we're going to assume that if it works with these small values, that's good enough, that the logic works correctly. So let's look at this. We want to get rid of the x's now, so 0 out the x's. The origin's always at 0, but this x is going to be... Okay, and then over here, the origin's at 0. Boy, this is just hard to read. So we know that the output, right? So this is destination X, this is destination Y, right? And then let's just keep track of what we have here, because we're losing track of what these variables mean. So we need to relabel this really quick so that we know what the heck we're looking at. Because right now, we're starting to not know what we're looking at. So at some point... Okay. Okay, so... we want to only use the y's here. So we're going to make everything else zeroed out, right? We're going to just zero this out so that we're only looking at the y's. And then on the x's, right, the x goes in, and let's steal these over here. Okay, so these are the inputs over here. And x's need to be zeroed out here. All right, we're just going to, actually, no, we're not going to zero out the x's, but we're going to zero out the y's. We zeroed out the y's here. X's and then y's are zeroed out here. X's and then y's are zeroed out. So over here, we're going to zero out the x's. So zeroed out x, zeroed out x. The y's we can keep the 0 to 2 range. X is zeroed out, X is zeroed out. But the y's are 0 to 6. 0 on the X. Okay, cool. So that looks good to me in terms of that. And then we want a final test where we final test using current use case. 0135. Okay, so we're going to use the current use case that we've been programming into the shader code, and we're going to try to get that to work correctly, right? So we're going to do one more use case down here where we try to input the actual values that we're working with in the shader code. So if we look at this shader code, we have kind of a very specific range of values, and we want to make sure that the values that we've selected for these calculations kind of make sense. So the maximum, right, so this, these output locations here is kind of what we want to use. So we'll have to hard code them somewhere in the test code so that we have that specific case, and then we can double check our math, make sure the math for those coordinates is correct, and that could also help us debug what's going on. But before I do that, I need to take a break, and I'm going to try to bust out like 50 push-ups or something, because we're getting to an intense level of push-ups here, because now we're not on 130 per day, we're on 140 per day because it's a new week. So we're getting to where it's getting to be quite a lot. So if we can do, 50, 50, and 50, that only means like 3 sessions, 3 little short workout sessions to hit our goal per day. So I think that's what we're going to do. And then we have to erase last week. So we got to erase last week here. And we got to, so let's kind of do that. So we're on Monday. Like, we got to zero out everything, and we got to start over. So we hit our requirement for last week. So let's roll back everything. So we're currently at 0. We have absolutely none done today. So I want to... there's a lot of things I want to do. So we're going to do... Let's see. If we keep this simple, if we did like 25 and 25, and then we could start the break, do our 25 push-ups, do everything else we need to do, and then come back, do our other 25 push-ups and stuff. And then we can get to 50 pretty easily, right? Every time we get up, we do 25, do the thing we need to do. Okay, so what we're going to do is we're going to do like a 30-minute break. And if I have more time left over, like after, I'm going to definitely do my at least 50 push-ups, and if I have any time left over, I'm going to use that for doing more exercise, I guess, right? So let's do that. Let's start taking a break here. So okay, so a break screen, we're going to just say, 32 minutes, I think. and then I'll be back after that drains to 0. So I'll see you when I see you. In like about 32 minutes. I don't want to do any push-ups, but we're going here. Okay. Two, 3, 4, 25, 26, 27, 28, 29, 28, 29, 30. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Okay, squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Let's add that to our okay. Okay, we're almost... So let's just throw this. Okay, so unfortunately I took too long of a shower, but when I'm in the shower I write notes about what I kind of need to do, and so I realized that the functionality, the test I'm writing here for this remapping, right, we're going to remap a source rectangle to a destination rectangle, and we're going to remap, hey, how's it going? Is it Erald? I mean, I think I've already asked this before. If I'm pronouncing that correctly. Erald? Is that how you pronounce? So I'm just, I probably asked this before, but I forget things. Yeah, okay, cool, yeah. So I don't know if you were here earlier. Okay, cool. I don't know if you were here earlier, but I was doing, I showed like a quick tech demo of what I'm up to. I think you were here, I'm pretty sure you were here on Sunday. I'm pretty sure you were here on Sunday. I could be wrong, but I think you were here on Sunday. So you already saw kind of like the latest stuff that I have. And now I need to debug why my texture updates, they're not working when I do a partial texture push. Oh, you weren't? Okay, I can show you what I can show you what I'm up to. I will have to get it compiling first before I can show you. Oh, that's fine. Yeah, I mean, stuff happens, man. I totally understand. I'll show you what I'm up to. So, first thing is I actually have to get this mess compiling. So, let me just make a note in my shortcuts because I have a... While I was in the shower, I realized there's something I need to do in terms of code. So, to do, put rectangle mapping code into fragment shader common code. So I need to make like a fragment shader common code thing. Now I realize that because some of the code I'm writing is going to need to be used in other shaders, so I don't want to have to rewrite the same code and retest the same code. I just want to like make one namespace for the code that's going to be reused between multiple shaders. So I'm just making a note of that. And let's go try to get this working. Let's try to make sure that the code will compile, and then once the code can compile, we will show you what's up. So I was writing some test code. This is what this is. This is just a unit test, right? So each one of these rows of data is just inputs and expected outputs. So I need to quickly count how many rows there are here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So 6, 7, 8, 9, 10, 11, 12, 13. Yeah, so we got 13. Oh, wait, I didn't count that. 14, 15, 16. 16. Let me count this. So 3, 3, and 3, so that's 9. And then 10, 11, 12, 13, 14, 15, 16. So 16? Okay. So as long as we don't go over, we won't get a seg fault. So let me count that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, so I think there's at least 16 things here. I could be wrong with my count, but I'm pretty sure there's 16 things here. So the number of tests is 16. The number of columns is 12. So when we number these columns, we have 12 different columns of data for every single test, but there's 16 tests total. So let's try to get this compiling. Hopefully, I don't know if the test will fail, though, because if the tests fail, then I'll have to fix the tests or fix the code that I'm testing before I can show you what I'm doing. So let's try to get this running. And once I get it running, then I can show you what I'm up to. But it will take some time since, when you're coding stuff, you have a whole bunch of broken stuff and all that good stuff. But /AAC2020.sh, that's my build script. So it looks like we forgot to declare some variables in our test. So SX, let's go up here for a second. So we got the source and destination rectangle, but we don't have the input, right? So source coordinate. So let's make it int32 sx, and let's make it int32 sy for source x, source y. And then we might also need a dx, dy as well. So dx and dy, if we highlight this, we may not have declared that either, right? So yeah, we don't have that. So source and so we might just want to, since we have source and dest for both of them, we might as well pack it over here, right? So just copy this. Let's paste this. And then this is D. So chord in or chord sr. That's not correct. Chord x, right? And this is coordinate y. And then these are the rectangles. Rect bounds dot we got left, right, top, and bottom bounds here. Okay, so now let's give that another run. And okay, so DST is undeclared. So I'm just doing a whole bunch of stupid stuff where I'm just forgetting to declare variables. DST, yeah, DST is the output. DX gets packed into the... Okay, DST, got it. So we need a an output. So let's just go over here and say output variable for each test. And that's going to be IVEC2. It's going to be INVEC2, and it's going to be called DST, right? Yeah, DST. DST for destination. DST. And let's not worry about it too much. Okay, let's just get this working. Let's not worry about our formatting and all that picky stuff. INVEC2, unknown type. So let's go over here. And we're going to have to define INVEC2. And it should be AAC 2020 poly OGL, polyfills OpenGL. And then it should be called INVEC2, right? That should be as simple as it is, but also needs to be struct, right? So struct, and this is the struct type. It's a polyfill type, so that the code can work both on the C99 side and the OpenGL GLSL side. So now we got 7 defined, so we want to go down here, and we want to undef IV2 for INVEC2. and then give that another shot, right? So the idea here is that if I'm being consistent enough with my code, then I should just be able to get it working because I know... Okay, implicit declaration of function. I thought this might happen. So in here, we're testing a function, right? We're testing this function. And this function file... Oh, undef, yeah. So in, yeah, I can explain it to you. Have you done, plain code before? So yeah, okay, yeah. So an undef is just removes a define, right? So a define is kind of like a constant in C code, but it can kind of screw you up if you think of a define as a constant variable, like a variable that you can't change, because it's not really that, right? So okay, yeah, if def and if end def. So those are for like conditional blocks of code. So you're kind of familiar, right? Yeah. So we can go over that for a second. Yeah. So okay. So right. So you're familiar with like this, right? So if def, and then if def some macro that might be defined, right? And then some type of conditional code right here, and then end if, right? And then we can do the same thing. We can do, if not defined, right? So I'm just going over the stuff you already know, right? And so some macro that might be defined, and then some conditional code, right? And then an end if, right? So I would usually write my code like this, and then, other people would write the code like this, right? Like with an else, a hashtag else, right? So you could write it this way, or you could write it this way. I prefer this way, just because then I know what the blocks are. But now let's get into the define and undefined thing, right? So if we define, let's say pi and 3.14159, I think. 14159. It's been a while. I think that's about right. It's been a while since I memorized pi. So if we define pi, and we have another variable here where we say, int some calculation equals pi times 2. And then an undef pi right here. What's happening here? And I'm sorry if I'm going to re-explain some things that you're already familiar with. Right, so this code turns into, before this code even gets compiled, the preprocessor does text processing, right? So the source code literally becomes, it takes wherever it sees pi and it replaces it with this. So this is the actual source code that gets compiled. So this pi is not a constant variable. It's literally string replacement. So it goes through the source code and it literally does a text replacement of where it finds that variable. So this is what actually gets compiled. So if I do an undef, then if I try to say, if I did a define and then an undef here, then this would not work, right? So if I define this variable here and then I undefine it, now this variable is no longer recognized, right? So it's like so you could think of this as a declare, and this is a undeclare, right? So and the reason why you would want to do something like that is to avoid polluting other people's code, right? So like, let's say you're making a library, right? You're making this library that you want other people to use, right? And if they, include, your library dot h, if it's a header-only library, or dot h, right? Whatever you want to call your library. And if your library, if inside your library, if you are like defining things that they might want to define, you have like define, for example, there's like an example on Stack Overflow where somebody includes a library where they define a byte as like car or like unsigned care or something like that. And that created a problem for the person including the library because the user of the library would like to define a byte as uint 8 type, right? Or, yeah, uint 8 type. They'd like to define byte as this, but the library they included your library, and inside of your library, you decided to define byte as this, right? So now somebody adds your library, and you've done all these preprocessor things, and now you've kind of screwed them over, because now they can't use all those tokens, right? And there's no reason for you not to clean up after yourself. So after you've done the stuff you want to do with these defines, and you're done using these defines, you want to, you know, do stuff with byte, and then you want to undef byte, so that way, when people include your library code, they don't get stuck with all these crazy macros that are just going to clutter up the code and make it harder for you to use that code. Okay, so let me look at that. A nice explanation, something similar with private and public methods in Java and C++. Okay. So yeah, I mean, if I know the answer, like I don't really consider myself. Oh god, that was the wrong window. Let's move this back over here. But yeah, if I do know the answer, like I'm not gonna say that I'm like a C expert or whatnot. I mean, I write a lot of C code, but I don't really consider myself like a master of like C code. Right? I consider myself a what do you call it? Intermediate, right? I would consider myself intermediate in skill level. But yeah, if I can explain something, I'll explain it to you. That's fine. Okay, so a lot of times when I'm writing sections of code, right, I'll define like all these things at the top of the section, right? This is the unit test section, and then at the end of the unit test section, I get rid of all these things that I define, right? Just so that I can keep these very shorthand variables while I'm writing my code to make it more terse. And then this kind of block of undefines kind of like makes the section divider a little bit thicker. It's just a weird style I have. This is not a normal style of writing C code. It's just the way I like to do it. So yeah, so this variable right here, GPUView, this is not a variable, it's a function. So this function, we're forward referencing a function for some reason. And I think I know why. And we're going to go fix that. So we're going to go into... so it's the fragment shader code that we need to look at here. So let's go open up libchan. And if we look at GPUView, we're going to find something going on here. Data file and the function file. Okay, so what we've done here is we have included the fragment shader code after the function file code, right? And the main function file is what houses our unit test. So if we want this code to kind of work without forward declarations, then we just need to switch the ordering here and say that this order kind of makes more sense. So we could say, you know, before.f. right? And then we could say, you know, after right? We can make a note that this right here, this line comes before this, and conversely, this line right here is going to become after this fragment shader code, right? So we could make a little note of that, change that around, and now if we try to compile, we should be able to get this to compile. Oh, and then, yeah, and once we get this to compile, I'll actually kind of show you what we have here. That's okay. That's cannot remove. Okay, we're compiling. Okay, cool. So we could have a crash though, because we wrote some unit tests. There's the possibility that my unit tests are going to fail on me. Okay, yeah, so test index number 1 is failing, right? So before I can really show you what I'm up to, I am going to have to, well, actually here, we could, for the sake of just getting this to run, I'm going to comment out the test code so I can show you where I currently am. So that, you know, if you have to go do something else, you know, I like to show you right now what I'm up to, so that if you need to go do something else, you can do something else, right? So let's try to get to the point of the interesting stuff. So that way you can see the interesting stuff, and then I can kind of go back to the boring stuff. So let's get rid of this unit test failure so that we can just run the project. And let's put this over here for a second. And let's go into the editor here. So this is the editor now. And let's open up a file in our assets. Let's open up an assets file so we can show you what I'm trying to render. Okay, so I'm trying to render this. And unfortunately, my window code, my Win32 code sucks. So there's something wrong in my Win32 code where if I leave the window idle and I don't do anything in the window for too long, the whole thing crashes. So that really sucks. So I have to just rerun the project, so I apologize. Okay. So right here, you're seeing the, this is what is actually going to be on the GPU for the tile set. So this is the binary data encoded into pixels that encodes how I'm rendering a tile set. So let's go look at what that looks like. So I'm going to do P for pattern to load the pattern into the editor. And then I'm going to scroll through different cross sections, because right now you see it's all white. If I scroll through different cross sections, we can see, oh, hey, all of a sudden we're starting to see something kind of interesting, right? So what you're seeing here on my right screen is the render view of what you see on my left screen, right? So if we want to look at the data, so let's close some things. So this can be closed. We have a lot of things open today. So... Right, it's crashing on me. We can just, let's, so in PAINT5D data, this diagram here corresponds to exactly this image over here. And then this diagram right here that you see in this code here, that is corresponding to this image right here. So this is the data layout. You're seeing an instantiation of the data layout, right? So you're seeing you are actually seeing the data, right? Because I packed all of my data into bitmaps so that it would be really easy just to visualize what the data looks like, right? Because we can just dump the data onto we can dump the GPU data into a PNG file and just look at it and be like, hey, does that look correct, right? So, so this is the data, and this is rendering the data over here. We're gonna have to close this again and run it. This kind of just sucks, but okay. So let's Control-C to close this. I could do Control-Alt-Delete, but unfortunately Control-Alt-Delete will black out my OBS software, so I just have to recompile. And then we'll kind of do some more explanation on what the heck you're seeing, okay? And then after that, I'm gonna get back to kind of my busy work of just writing some tests. Okay, so let's put this over on this side. And let's hit this key to get into this editor. Let's hit P for pattern to load the pattern. And let's scroll to the last tile set. Okay, so you can see kind of 4 distinct patterns here, right? You see this top left here, you see a top right, you see a bottom left, and you see a bottom right. This top left pattern is being rendered by using all of the pixels from over here, this quadrant. This top right is being rendered by using all the pixels from over here. The bottom left is rendered by using all the pixels from here, and the bottom right, all the pixels from here. But there's some other things going on here, okay? So when I say all the pixels, it's not exactly, that's true, but it's a little bit misleading. So this top left image is using 2 bits from every single pixel here, right? And down here, same thing. It's using 2 bits from every single pixel here. So the reason why I can kind of go through different layers here is because I'm only using 2 bits from every single pixel. And every single pixel has 32 bits, right? So if I'm only using 2 bits from every single pixel, well, 32 divided by 2 is 16. So I can store 16 unique tile sets within the data to my left. Now you notice that some of these things aren't really interesting. Like this is a complete white screen, right? And that's actually working as intended because this data set is, I kind of hacked it together, right? So I drew one image in red, and then I drew another image in blue. And then I did an additive blend to kind of hackishly bit pack the 2 images together. But it's a very hackish way to do that, right? So the guarantee we'll have here is that, so this is the alpha channel. And so we got some interesting things going on the alpha channel, but not any guarantees. So 2 bits of the alpha channel, 2 bits of the alpha channel, 2 bits of the alpha channel, and then 2 more bits of the alpha channel, right? So we have 1, 2, 3, 4 alpha channel layers. And then once we go out of the alpha channels, red, green, blue, now we're in blue, 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 and blue. So the most significant bits of the blue are most true to the blue patterns you're seeing here, right? So you see that these tiles are all identical right now, right? This and this and this, all these quadrants are identical. And that's because I was just getting sick of drawing stuff and I just wanted to not draw any more debug stuff. I was just sick of it. And so I pasted the blue graphic, I pasted here, pasted here, pasted here, and pasted here. So that those blue pixels in each quadrant are completely identical, and therefore the rendering, when we look at the blue bits cross-section of the pixel, we get the exact same image 4 times. And then the red image you're seeing was an old test image that I decided to just kind of merge into this image, make this composite image. So when we scroll up all the way to the most significant red bits, this image is completely true to the red pixels that you're seeing, right? So if you can imagine, if you can kind of visually separate the red from the blue, even though they're kind of blended together, you can kind of imagine how the graphic here is completely symmetrical, and this graphic here is completely symmetrical. The graphics here kind of make a bottom left corner, right? Right, we have the different tile sizes, right? So this layer here, the first layer has really not anything in it, except for like some pixels around the edge. The second layer has some interesting details, and the third layer has some interesting details here. And then we draw with larger and larger tile sizes, or you could say larger and larger pixel sizes, but that's kind of confusing to say larger pixels. So these are our smallest tiles because there's more of them, right? So very granular. So we have many little granular tiles that fill this entire quadrant. Then we have tiles that are twice that size, filling, once again, this whole quadrant. And then tiles that are even twice that size, filling this entire quadrant, until we get way down here where we have just one giant tile that fills the entire quadrant. And I know I've gone over that kind of like MIP map quad tree kind of structure that I'm doing, but that's just kind of like a little review, and now you can actually see it in action and see what that looks like. So hopefully that's kind of cool. So that's kind of the quick tech demo of what I'm up to. So that's really all the interesting stuff. That's all the interesting stuff. There is not going to be anything else interesting for today, and it may be like another month to 2 months before I have anything more interesting to show you. And, you know, as long as I'm, so as long as I'm like under 1,000 followers, I'll make sure to like message you personally when I have something cool to show, because like I don't think like to do it every like once every month or once every 2 months, it's not too much of a pain to like personally message every single person. Like, it's a lot of typing, right? Because I don't cut and paste my message. I do personally write it out, even though I'm kind of saying the same thing over and over. So it's like, you could say, well, if you're saying the same thing over and over, what's the utility of not cutting and pasting? But I don't know, I just think there's something about, I don't know, I think that, even if you're saying the same thing to multiple people, the effort of hand typing something out leads to it being more personal. Even if, and that can be kind of tricky, right? Because you say the same thing over and over to a whole bunch of people, it might look like a cut and paste message, even though it wasn't a cut and paste message. But yeah, I message, when I message people, I actually type it all out. So like if it's 1,000 people I have to message, right, I'll listen to like a podcast and I'll just kind of type out messages to people one day, telling them, hey, I got something new to show, right? But you know, because I do understand that, you know, most of the time what I'm doing most of the time is kind of boring, right? It's kind of boring stuff. So, like like with other people's programming streams, like other streamers I know, like yeah, I sometimes will drop by and say, you know, how you're doing, check them out, see what they're up to, right? But besides that, it's kind of like, man, I got other stuff I need to do. So you know, so if I can't even keep up with other people's programming streams, then I'm doing a programming stream. Like, I don't expect anyone to watch any of this stuff all the way through unless I'm doing something very interesting. But anyways, I'm just working on some unit tests for the rest of the day probably. And tomorrow, at some time, I might actually go over some mechanical patents and some actual like video footage of what I'm working on at the shop. So it won't be code, it'll be actually like physical products. So that actually might be interesting, but that's going to be like in almost like 16 hours from now, probably. Okay, so let's try to figure out what the heck is going on here. Let's duplicate this twice and just start creating a printout for what's going in, what's coming out, right? So we're just going to take all this, copy, paste, and figure out why our test is failing. Maybe the test is failing because we just wrote a bad test. Or maybe the test is failing because our test code or the test is at... Right, when a test fails, there's two possibilities usually, right? It's either the test case is wrong or the code is wrong. The code that is being tested is actually broken, right? So we don't know yet what that is. We have to actually look at the values and see if they make sense. Okay, so we have that, and let's actually create like a little section divider. And between each thing, let's just put a printf \n maybe. Or actually, no, just another \n, yeah. But yeah, let's just give some visual space. No need to make these lines any longer than they already are. Let's just kind of put this over here. Okay, cool. Yeah, so let's give that a shot and see what we got, see why it's failing, and then try to get the code working. And then after we get this code working, we're going to put the code that we're testing into another namespace, because this namespace is... The function we're writing is really like a generic utility function for our shader code. Okay, cool. So this is a nice little printout, right? We got this nice little divider. We got a little bit too much space here, though, right? Like, each one of these things, right? This is not as compact as I wanted, and I can see why. So we have to do it only on the last line, right? If we want to write it like that, right? We can... Okay, let's give that a... We can still look at this, though. So... Oh, we're missing something, though. So we got sx, but we don't have dx anywhere, right? So we did everything except for looking at the dx value. So we're pretty close here, and we're missing something anyway. So let's kind of take this, let's paste this, and we want to inspect what that dx value is, right? Dx. Okay, so let's clear this. Let's give it another run, see what this looks like. And okay, cool. So the dx dy is 0, 0. The sx and sy is 0, 0. So that would be 0 to 5, 11, 0 to 5, 11. And we have one more thing that's a problem, though. We want to look at dst, right? So you want to look at what dst is. So let's, we have one more thing that we actually want to look at, is that dst value. So dst.x and dst.y. And we want to try to keep the... We want to be OCD about this and try to keep the formatting to where everything's nicely lined up. We'll have to add a little bit of padding to some of these variables, or to where we're printing things out, and then we can space that out like that. Okay, cool. So everything's still lined up nicely. Let's give it a run and see why they're not equal. What the heck is going on, right? Like, it could be that we just forgot to return the variable. Right, we forgot to like pack it in there when we returned it. We could be doing something stupid, or we could be doing something more, I hate to say sinister, right? Sinister is probably not the right word. Okay, so lower bound x, upper bound y. Lower and upper bound is 0. I think we just didn't write this how we expected to write it, so let's go look at the test cases. If we're going to remap to where the y's are 511, 511, this output actually makes sense. So let's think about what we were trying to do, and then figure out how to fix this. Because this could mean that a lot of test cases are completely broken. So this is test case number 1 right here. So 2 basic cases, x and y are identical, right? Okay, so we got this 0, 0. And we're going from, I think the idea was, we thought of this as the, we're thinking of this as the lower bound and this is the upper bound, I think, is what we made a mistake here with, because it's lower upper for the x and then lower upper for the y. And I think I made that mistake in a lot of places. I mean, I think I made it in so many places that I think it's going to be easier to work with this if we just say, let's just change this. Let's just change what these are, right? So we're actually doing this as in x and y. So we're really doing, you know, this is the lower bound, upper bound. And then same thing, this is lower bound, upper bound. God damn it. Redo. So upper bound. Right, so we want to take something like this, right? This is kind of what we're trying to do. Okay. And so wherever we put this labeling here, we have to change that because that's not exactly what it is anymore. And if that's how we want to roll, it looks like that's what we thought things were. So I think that in terms of these original tests, that's kind of the grouping that kind of made more sense to us for how we write these tests. So that means we're going to have to do the same thing here, where we're going to have to say, you know, lower and then upper. And this is SRC, right? So this is a source. It's the lower or upper. And then it's either X's or Y's. What are we missing here? We got the lower bound, we got the upper bound. But these are identical, so where are we missing? So oh, wait, this is because I didn't get this right. It's X's and Y's. Lower bound XY, upper bound XY, right? Because we're going to change around what these are, right? And then over here, we're going to change how we remap this as well, how we extract these, right? So this is the destination, DST. And now we just want to change this. So source is good, but we want to do the lowers and then the uppers. So zeros and then ones, like this, and then XY, XY, right? So XY, XY like that. All right, so these are still all unique variable names, but we want to extract the lower bounds and then the upper bounds, lower bounds, then the upper bounds, source, then destination, XY, 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 so that we can group in terms of lower bounds and upper bounds. Okay, so now that we realize that, I'm going to guess that this will actually make more of our tests pass, but we may have been confused about what means what in some of our other tests, so I'll have to fix that as well. But we're hoping to get more of our tests to pass, right? So the idea is that it's not going to fail on test number 1. It's going to fail on like maybe test number 6 or something is what we're hoping. Test number 2 it's failing on. So we got a little bit further, so that's cool. So let's go look at what we're doing here. So test 0, test 1, test 2. So we're going in a range 0 to 511, 0 to 511, and then we're mapping it back to 0 to 511, 0 to 511, and then we have the output as 256, 256, which makes absolutely no sense because the output would not be changed, right? So, oh, I see. We're saying that we're saying the input, the source X is 256, the destination. So yeah, just organizing things in terms of lower and upper bounds is actually going to make this easier to look at as well. So let's try to change that as well. So let's change this to the lower bounds and then the upper bounds, right? And do XY, XY. Right, so X, Y, X, Y. And then copy this over. And then let's paste this over here. Actually, let's paste just this. Right, so now all these should match, and they're all unique still. Let's just give that another run and see what that looks like, right? Because I think that this will make the data set a little bit easier to understand, right? We want to organize the printout in the exact same order that we organize the test data, just because then we don't have to shuffle around variables in our brain, right? Let's try to figure that out. Okay, so Sx and Sy is 256, 256, right? Okay, that makes sense. And then the lower bound for x and y is 0, and the upper bound is 511, right? So it's a big rectangle spanning kind of the whole 512 by 512. And then we're going to map it to something where the output rectangle is exactly the same, right? And because the output rectangle is exactly the same, we're going to expect that we're going to have the exact same range. But instead, we're getting 0 and 0, right? So it's just a very horrible screw-up. And I'm going to guess this is our first test where we have something non-zero. Yeah, this is the first test where we have something non-zero. So that's kind of a hint as to what we might be screwing up here. Close anyways. Cancel. So let's keep this open over here. And let's look at the fragment shader code. And let's look at the function we're testing, right? So we wrote a function here. And this function is eventually going to go in the common code, but right now it's kind of like just chilling out here. Okay. So this common code, for some reason, this int vec2, it's just not returning anything, right? So this dx dy dot x equals this dx dy. We got all this kind of crazy stuff. So the first thing we could do is we could add some asserts in here, right? We can do some sanity checks and just make sure that everything looks correct, right? So let's kind of do that. So what are some of the assumptions we want to make? Do we want to break some of these formulas into smaller formulas? What do we want to do? Well, the first thing I'm seeing here this is a scale factor, right? So if the scale factor destination divided by source equals scale factor, right? Do you see any division in here at all? No, we don't, because this should be a division sign, right? And it's not. And the reason why we're screwing up here is because the input and output rectangles are exactly the same size, right? So they're exactly the same size, then this minus that ends up as 0, and so our scale factors end up as 0, and then it just, you know, it's not going to work, right? So we need division, so, right, because here's the multiplication here. So that was one huge mistake. So let's see how far we get after correcting that very blatant, huge mistake, and then kind of see where we're going to go from there. Okay, let's take a look at this. Okay, so now we're on test 8. This is better, right? Because test 8 is pretty far up here, right? Test index 8. So what we're going to do is say... So the test index here is 1 and 2, right? So let's just put some notes here of the test indexes. So we're going to try not to ever insert test cases so that we can kind of manage what these numbers are. So 0, 1, 2, 3, and 4. And this is going to be 5 and 6. 7, 8, 9. Let's just call this org 0. Org 0. It's going to be 7, 8, 9. And we might want to say, you know, org 0. So origin 0 is origin is 0, so 789. And let's kind of do something similar here and say Nosrec. Non-zero recs. Okay. And then we can keep this number kind of thing going here. And we already see that we're failing over here somewhere. So 10, 11, 12. Okay. So now that we have kind of like this test index thing, let's try to fix the formatting here. Okay. That's good. It's good. It's good. Right. So I'm just being kind of OCD here. Commas. More commas. And then this, right? So I'm just trying to keep the 1s and 10s places correct. Okay, so we're failing on the 8th test index. So right here we're failing. And so the question is, if we're failing, is it because we actually screwed up, or is it because we don't know what we're doing? So origin is 0, rec map using 1x1 rectangles. Okay, so we're using a 1x1 rectangle. And so we have the source, min, max all zeroed out here. And then we decide the destination would be 511, 511 for the minimums, and then 0, 0 for the maximum. So already we see a problem here because, right, this is why I thought we got the minimum and maximum screwed up. We kind of screwed up what our variables were. So I kind of know what I meant to say here. I'm sure you meant to say like 0 and 511, right? So, or, no, we meant to say something like 511, 511. Oh, no, we want to isolate on one axis, right? So we're trying to isolate on the x-axis. So we're trying to say that on the x-axis, the min-max on the x is 511. And then we're trying to say, like, on the y, we're just keeping it 0, right? So we're trying to isolate on this axis like that. And then we want the complete inverse over here, right? So to isolate on the y-axis, we want to write the exact same code, but kind of invert this, right? So I think that's what I meant to say. So if we give this another run, I'm going to guess we're going to crash on test number 10 now. So let's give that a run and see if we can make it down to test index 10. Okay, so we're at test index 13. So we actually made it a lot further than I thought, right? Because 10, 11, 12. I didn't think we would actually get that far, but we did. Cool, because min, max, min, max. Okay, I see. So over here, what the heck were we thinking? Why is this wrong? Blah, blah, blah. So we're thinking to take a 13 is... so this test index here is 13, 14, and 15. Okay. So you have this like 1, 1, right? So we're saying we're somewhere in this range here. And that means that the min... Okay, so I see we screwed up our mins, right? So we're saying 0, 2, right? So 0, 2. And then we're saying for the maximums, we're saying 0 to 6. And then we expect that to map to 3, 3, right? And then we want to just take that code and we want to isolate on the x and y. So let's kind of paste this here. And, you know, let's make sure that this actually runs first. Before we even try to build upon that, let's make sure that that runs, that does not crash, right? I think these are the last tests we wrote. So let's make sure that all these tests pass, then we're going to isolate on the X and Y axis, right? Because we want to make sure that we don't have any, like, weird transposition errors. Right, so test 13 failed, right? It's a good thing we didn't try to build upon it, because we don't really want to build upon it unless we know that it's written correctly first. So, test number 13. The output is 2. The input is 1. And we were expecting not 2, but we were expecting 3, right? Because if we're 0 to 6, 0, 1, 2, 3, 4, 5, 6, then we're expecting that if we're in this middle coordinate here, right, 0, 1, 2, then we're going to map to 3. And so the possibility here is that we're just off by 1, right? The mapping is off by 1, right? That is what could be happening. So the min bound, the max bound, 0 to 2 inclusive, to a min bound of 0 to a max bound of 6 inclusive. We're expecting that middle to be a 3, and we're not getting that. Okay, cool. So let's try to figure out why that is. I think that it's actually, I think the logic in our code is probably wrong, right? The logic in our code is wrong, so we're going to have to figure out. And this is why I said, like, when I was, you know, at the beginning of the stream, I was like, you know what? I don't think I can whip out this formula off the top of my head and get it correct, right? I can get it almost correct, where it's like I'm off by 1, right? Because we have to see this 2 here, so we're off by 1. But I almost guarantee that the problem is some type of off by 1 error. So let's go look at this. Let's go look at the code for this. How do we need to do this to make it? Do we just need to add 1, right? Is it that simple? Do we have to rethink our scale factor? Like, what do we have to do here to make sure that this is correct? So I know I've actually done this math before, and I know there are some very careful off by 1 mistakes you can make here. I know I've written this kind of code before. Let's just figure it out. Let's figure out what we're doing wrong. We know we're off by 1. We got to figure out why we're off by 1. We got to think about why our calculation's off by 1. Some more diagrams would help, right? So maybe we should write some more diagrams, right? So let's actually, this is the test case we want, right? So if this is the test case that's failing, and we've already drawn out this test case, what might actually work for us the best is just say, hey, okay, well, this is the test case that's failing. Figure out why. So this is the source, right? And this is the rec DST, and this is the rec source, so rec SRC. And we're going to start here, right? We're going to start it here, right? So this is our, this right here is, this right here is SX, SY, right? And then the output that we're expecting is right here, right? So let's walk through the math. And as we walk through the math, we're going to expect that as the math is currently written, that we're not going to get to where we want to be, but we're going to get to like this 2 instead. And then we got to figure out, well, what is off by 1 and how do we fix it, right? Okay, so the first thing you want to do is figure out the fx, fy, right? So, so fx equals this kind of stuff here, right? So let's take this formula and just fill it out with the correct value. So we got the dx dy, right? And this is the, this is the output x. So this is source input and the destination output. And And then over here is, you know, dx1, dy1. Right, so over here is where we have dx1, dy1. And hey, how's it going? So, I forgot if you saw the little technical demo or not. Oh yeah, you didn't. Yeah, you didn't make it to the demo, right? You were here for when I started to make. You were here when I started to make the data set for the technical demo. You were there for that because I remember you said, "Oh, we're gonna do some fun stuff." So I remember that. So I was also wondering, something in. Well, I don't want to say it out loud, but it was a question about the just chatting because I noticed some interesting patterns with the just chatting category. Maybe I'm just full of crap. Maybe I'm just, you know. But anyways, so let's kind of get this running first. And yes, I pretty much nailed it. Okay, cool. So I know what that's about. Okay, cool. Very cool. It's almost like to make a product that's successful, you have to support. To make products successful, you have to allow for. Okay, got ya. Yeah, so to make a product successful, you have to allow for things like that without being blatant about it. Where like everybody knows, but you can't come out right out and say it, right? Where like kind of like how certain applications might be like for hookups or whatnot, but then you don't want to say it, you don't want to advertise it as being for hookups, right? So the just chatting category, you could say it's for certain things, but everybody knows it's for certain things, but you can't come out and say it because then no one would use it for that thing, right? Because you call people out. It's like that. It's like there's these unspoken rules where everything's okay until you say that unspoken rule out loud, and then, yeah. But anyways, let's, I'm just writing a little diagram here, trying to figure out my remapping logic. My remapping logic, I'm trying to take a source rectangle and a destination rectangle, and I'm just trying to remap a coordinate that's within one selection rectangle to another selection rectangle. You're liking the numbers? Yeah, so we'll go over kind of this math here, but I'll give you the. But before we do that, we're going to kind of get this running again. So to get this running, we're just going to comment out the failure case. So this thing right here, this error message right here, we're just gonna comment out the error message. Or not the error message. Yeah, we're gonna comment out the error message so that we can actually compile, right? And I'll show you the tech demo. It's nothing too fancy. And then after I show you the tech demo, we'll get to writing our test code. Because of so it's like it's really crazy where like very simple math becomes very hard when that math needs to be not off by one, right? Like math and geometry uses like lines where a line is infinitely thin, right? So when you're doing all your math and geometry, like all that math is so easy. Geometry is like easy peasy. But then once it's like, oh god, I have to do discrete mathematics and I can't have floating point and everything needs to be exactly pixel perfect, all of that math that you thought was super easy becomes pretty hard as far as I'm concerned. So let's go look at the editor. So I kind of grayed out, so I think you might have saw this part already. Oh yeah, that's fine. I mean, I don't expect, what do you call it? I don't expect anyone to watch all this stuff all the way through, you know, because some of it's pretty boring, right? Most of what I do is pretty damn boring, right? And that's kind of why I message people when I have something that's kind of interesting to show. Okay, so I grayed out this area, because I know you were talking about hey, what's with those extra tiles? And I said, oh, those extra tiles are out of bounds, right? So now I grayed out the out of bounds area to kind of clean this up a little bit. And let's kind of do P for pattern, load the pattern in. And now we have different cross sections we can look at. Yeah, you were there when I fixed that. Okay. So let's go look at the data set. Let's do a side-by-side comparison of the data set. So this is the data set that I made while you were on stream with me. And unfortunately, we're going to have to like close this. My Win32 code has a problem with it. And I have to fix that eventually because it's not... I cannot... Yeah, one thing at a time though. I'll have to fix this eventually. It's not too big of a deal right now because I just start up the program, run it for a little bit. But yeah, if I stop moving my mouse around the editor, I think it's not stop moving my mouse. Actually, I think it might be. Something about getting my... I don't know. There's something wrong with... I think something is wrong with how I pull events. I think when the window loses focus, it doesn't pull events properly, and the event queue accumulates, and then it overflows. And then I think the event queue, when the window is not in focus, starts to build up, and then Windows thinks that my program is not responding when it is, because I'm not properly handling events when I go out of focus. I think that's what's happening. I don't know if that's the case, but that's my guess. It's just a hypothesis here. So let's go to this editor. Let's do P for pattern. And let's go through this stuff. And let's try to very quickly open that up. Okay, cool. So now we can see that to the left is... Let's move this down a little bit. To the left is the actual data set we worked on. And on my right is how it's rendered, right? So you've seen this image before. This is the image as it's drawn in the red pixels. And then let's go all the way down to the alpha channel. So this is alpha, alpha 1, alpha 2, alpha 3, and alpha 4. Then we have blue 1, blue 2, blue 3, blue 4. Okay, so this blue here is the most accurate cross-section of the blue pixels, where I try to like hackishly bit pack together, right? I try to take the blue image and the red image and just do an additive blend to get like a hackish bit packing where we would know that the most significant bits of the blue and the most significant bits of the red would probably be properly bit packed if we just did a additive blend, right? And so far this looks correct, right? Because remember, I got really sick of drawing this, so it's identical here, 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 and here because I cut and pasted, cut and pasted, cut and pasted, and cut and pasted because I was just sick of drawing, right? I just wanted to get a data set that I could kind of look at. So everything here is designed to be like a top left corner graphic, and indeed we can see that though this looks kind of weird, we can definitely see that it is pretty much a top left corner graphic in the way the edges are kind of designed, right? So that looks good to me. That looks right. And when we scroll up through the different things, we can see that this graphic still looks correct for the blue, the red pixels, so the red bits, and then everything in between is just like I didn't know what it was going to be, right? So in some points we're getting things that are completely uninteresting, and then other times we're getting these hybrids where we're getting a little bit from each design, and those kind of look interesting, right? So we're just get these things. Some of these things look really crazy, where this almost looks like a negative, but it still looks kind of cool, right? It looks cool. So I got some cool stuff, right? So that's the tech demo. That's all the tech demo is right now, right? We're able to, instead of scrolling through kind of some BS data sets, we're now scrolling through a more legitimate data set, but it's not a completely legitimate data set because we don't really have any pattern in this slot, we don't have any pattern in this slot, and what we do have here is a whole bunch of very close to identical patterns, but we're not going to do any more kind of graphic creation until we can actually use a legitimate editor, and that's kind of what we're trying to program. So let's close this. That's the tech demo. So let's do Control-C over here, and let's kind of go into the code that I'm writing. And okay, are you overlapping the 4x4 on the left to a 2x2? Oh, I see what you're talking about. Yeah, let me explain that again. Yeah, I know exactly what you're talking about, and I'll explain. I can explain it again. So I can, so let's go take this image, and let's go rebuild the program. Let's kind of put this over here. Okay. Let's give that a run. So am I overlapping the 4x4 on the left to a 2x2? Oh yeah, no problem, no problem. I will explain that, right? So... Oh, oops, I commented my test code back in. I gotta comment that back out if I'm gonna run this. And then we'll... It's actually a very simple transformation. It's a very simple transformation, and I think you'll get it once I kind of show it to you and point it out. Though the rendering is kind of like wonky, right? It's just a whole bunch of crazy alpha blending that I'm doing to render it, which kind of makes the transformations a little bit hard to notice. But I think you'll get this. I think you can get this. I've seen the code you write. You're smart enough to get this. So let's go P for pattern, and let's load up this pattern here. Okay, so I went over this in the tech demo. This quadrant up here, so what you're seeing up here in this top left quadrant, well, I mean, I guess it's geometrical, right? Like, you might be very, calculus, or I don't know. I don't know your background. But I noticed that some people are very calculus-oriented, and then other people are very geometrically oriented. So, like me, I suck at calculus, but I'm, like, great at geometry, right? Like, in high school, I aced geometry. I didn't get one question wrong. Well, that's not true. The first test I took, I completely failed it, but then every test after that, I completely aced it. And I don't know why I failed the first test. I think it was because I wasn't being careful enough with checking my math. Or, like, I knew the stuff, but, like, you know, if you punch things into your calculator wrong and you're just off by one, you fail the question. And that's what I fucking hate about math class. Like, I really like math class. Math class is, like, one of my favorite classes. The thing I hate about math class is you're, like, off by one, and you just fail the entire question. That's what I really like about programming, right? You can spend all the time getting the equations right, and then you never have to worry about it ever again. And, yeah, so I'm very good with geometrical things. But with, like, calculus, it's like, oh god, area under a curve. Trying to visualize calculus or think about calculus, and calculus just seems more abstract. And I know some people are much more better with, like, algebra and calculus. For me, I'm much more better at geometry, which geometry does have some basic, you know, algebra, right? Some basic formulas, law of sines, law of cosines, Pythagorean theorem. But anyways, I'm ranting here. So let's talk about what the hell we're looking at here. So this upper left corner, this upper left quadrant right here, this entire graphic, right? You can see this completely symmetrical graphic here. That is being rendered by using all of the pixels over here, right? So you see this quadrant here? We're using all of the pixels from here to render this graphic. Now, we're only using, remember how we slice things into pixel cross-sections? So what you're seeing is all of these pixels. All these pixels here are rendered by using all these pixels in this quadrant here. And not only that, but we are only using 2 bits for every single pixel. So in order to create this image, we have to sample every single pixel, but when we sample the pixel, we only take 2 bits out of every single pixel that we look at. So we definitely have to look at every single pixel, but we're only looking at 2 bits of every single pixel. So same thing with this bottom right. This bottom right, same thing. We're taking all these pixels here. So after that, the only other thing I have to clarify here, and it's kind of hard to see in the graphic, right? Because this was not really meant to be a graphic that it's not a debug graphic like one of the other ones we made. well, it's debugging different aspects, right? But this is 3 layers of your most granular tile size, right? So here, here, and here is 3 different layers, and it's the most granular, smallest tile, right? Because if they're very small tiles, you're going to need more of them to cover this entire canvas right here, right? And then down here, you see these 3 sections here. These tiles are twice as big as these tiles, right? And because they're twice as big, you need half as much, and that's why the data allocation is half the size, right? And so, and those pixels, those tiles cover this entire area, right? And then eventually we get all the way down into this area where we have one gigantic tile right over here that covers this entire quadrant here. They are twice as small though. Yeah, so it's kind of confusing. It is, it's, yeah, it still confuses the hell out of me. The data layout size is inversely... Yeah, so it still confuses... It confuses the hell out of me sometimes. Like, I still have to think about it. Right, so... this is the data layout, right? This is the data layout, and you can think of each single pixel on here as a tile, okay? Every single pixel you're looking at, think of it as a tile, and we have tiles that are of different relative sizes, right? And the confusing, yeah, it's very confusing. So the way I think of it, to like elaborate it, is right in this quadrant, we have 256 by 256 grains of sand, right? And since grains of sand are really small, we're going to need a whole bunch of grains of sand to completely cover this rendering area here, right? And then down here we have one tile that is the size of a gigantic boulder. And because we only need, since it's so big, since it's just a gigantic boulder tile down here in the data, then we only need one of them to fill this entire area, right? So the amount of data is inversely proportional to the rendering size, right? So that still confuses me, so don't like feel bad if that confuses you. It still confuses me. So alright, so this crashed on me. Let's just close this. Yeah, so my hope is that I can get a kind of awesome rendering engine working before people kind of catch on to what I'm doing. And now that I've seen that it is kind of hard for people to grasp what I'm doing, even though it's... Oh, the smaller tile is still the same size. Oh, the smaller tile is still the same size as the bigger one. In terms of allocation, yes. In terms of so the smaller so the smaller group of tiles, the smaller grouping of tiles is the same size as the bigger, right? So collectively. Yep. So the render view, it all gets stretched over that same quadrant, right? Everything gets stretched to fit that render view, right? So let's kind of explain it how you explained it over there. Let me move this over. So let's give that one more run. And let's just use some different terminology. So let's use one more elaborative analogy, because I think that you're kind of talking about it in terms of the collective. And so I can say it one more time in a different way. So let's go over here. And... okay. Yeah, I think you're getting it. So over here, you see this quadrant right here? See these layers here? This is a whole bunch of very skinny people, right? This is a whole bunch of very skinny people in town square. And this is just the data for that, right? This is the data for a whole bunch of skinny people in town square. And then over here, we're rendering we're rendering town square right here. This is town square. This quadrant right here is town square, and this is the data for all the skinny people, right? And then there's one real fat person right here in town square, and that's the data for this fat person. And there's only one really fat person, because when we take the data set for the very fat person, when we render him, he takes up the entire town square, and he kind of squashes everyone, right? So we could think of that. We could think of it as people, right? We could think of it as people of different sizes. The really skinny people, we can kind of shove more of them into town square, so we have more of them, right? And the really fat person, we have only one of them, because they just take up this whole area, right? And then maybe it's like maybe we're looking on top of like a glass building, we're looking on top of like a glass skyscraper, right? And so maybe you know, maybe this is like floors, you know, floors 1, 2, and 3. Like floors 1, 2, and 3 are all really skinny people, right? And then floors, you know, 5, 6, and 7 are people that are a little bit fatter. And then 8, 9, and 10 are people that are a little bit fatter than that, etc., etc. And we're going to stack all these cross sections on top of each other to create like this kind of skyscraper, right? This skyscraper of different floors, and you're just seeing everything kind of alpha blended together. So let me read your comment here. So Town Square Hall has the 7 squares blended, multiplied by the 4. Let me think about that. So we got 1, 2, 3, 4, 5, 6, 7. Has all the 7 squares multiplied by the 4. So the way it's rendered is it's not doing a multiplicative blend. I might not understand you correctly. It's taking this area, stretching it over here, taking this area right here, stretching it over here, taking this, so we could think of it as this image right here as being stretched over here, right? Then we could think of this image right here as being stretched over here. Then we could think of this image right here as being stretched over here. This image over here is being stretched over here. And then this little image right here is also being stretched over here. So we could think of it as we're going into MS Paint, and we're cutting this, pasting it, and then stretching it over the entire area, right? And then the way we're blending it together, we're just doing some like alpha blending nonsense. Don't really worry about how we're blending it together, because that doesn't, I'm not really dead set on the rendering algorithm as far as I'm blending stuff together. Right now, I just want to make sure that geometrically it looks correct. Okay, anyways, I think you got like the basic idea of what's going on. So let's continue with our tests, and let's kind of explain what the tests are. And let's while we're explaining what the tests are, let's actually put the explanation for what we're doing. Let's put this back over here. So let's try to explain where we want to put this code. Okay. I don't know, let's just put it over here. Okay. So we have a collection of pixels. And let's try to do like a small case here. Okay. Oops. Yep, little diagrams. Okay. So let's make a section for this so that we can describe what the hell's going on. Okay. So this is the source. So this is the rectangle source, right? So each one of these little squares is kind of pixels. And this rectangle is DST. This is the destination rectangle. So say we have... this is the source coordinate. We'll just say... let's just call it P for point, right? Okay, so if we have a point here, right? If we have a point directly in the middle, right? So we have the rectangle, and we have the coordinates. Then we want to figure out what the output is. So we could say that we want to... So let's say I and O. So you want to take I... yeah, so the reason why we want to make... So I'm intentionally doing odd sizes. Yeah, I'm intentionally doing odd sizes because it makes it easier for this test case, right? We want to make absolutely sure the test, like all of our math that we ever actually use in production, all of our production code is going to be powers of 2, but we have to make absolutely sure that this code works for it needs to work for odd sizes as well. And also when we use odd sizes, it's easier to make tests as far as we can verify that we can do a very basic transformation and we can make sure that it is correct. So we are going to use prime, well not prime, oh I guess they are prime, never mind, they are prime. They're odd, but they're also prime. Now, I did not mean to make it prime, it's just, that's just a coincidence. Right, so the idea was we take this block and we duplicate it here, and we throw a column in the middle, right? So that we have an exact center here, we have an exact center here. So these are only for tests. We are not going to do any of this odd nonsense in our rendering engine, right? So yeah, so I'm just going to paste that in there, so that way I can quote myself in here. All right, yes. All right. Okay. So, I is going to be our input. Input XY coordinate on rec. Okay. And then O is going to be output XY coordinates on rec DST bounds, right? So all we're doing is a mapping, right? So it's pretty damn simple. Like, it's very simple logic. It's just that we have to make sure that we're not off by 1, and right now we are off by 1. Like, most of my tests have already passed, and now we're failing on test number 8, I think it was. I don't know, we'll find out pretty quick. So the idea here is we want to create a... Right now, in the actual code, I have the diagram over here, right? So this is kind of the same thing, right? So this is the rectangle source, rectangle dest. And we want to take the source, XY, and to... right. So we want to map... want to take this... source X, source Y, and we're going to map it to the destination Y and destination X, or, right? And so we labeled the corners, right? So this is the lower corner, right? The lower bounds on the X and lower bounds on the Y makes this upper left corner here. And then the upper bound corner here, right, is the upper bound X and upper bound Y, makes this corner here. And then same thing here, x0, y0 for the destination, D for dest, makes this corner. Right here, this is the destination x1, y1, which is the upper bound corner, right? So we're saying we want to take this rectangle, which is defined by these 4 coordinates, and then we're going to take this rectangle, which is defined by these 4 coordinates, and we want to take a coordinate that is somewhere within the inclusive bounds of the rectangle, and we want to properly map it into here. And right now, we're off by 1, and so we're taking the current test case that's failing, and we're diagramming it out right now, right? So we're diagramming out the test case where the source rectangle is, 0 to 2, inclusive, and then the destination rectangle is 0 to 6, right? And we're just doing a cross-section on one axis, right? Because we don't want to, just to simplify what's going on here. And so far we're failing, so we're going to take this formula here. So this is the formula we're using. And I know the formula is off by 1. And to figure that out, we're just going to start filling out these values, right? So dx and the dx1, dy1, we know this is 6, right? So we're going to throw in a 6 and throw in a 6, right? And these values right here, we want to throw in these values. So let's kind of label this, right? So label this right here. Cool. So these values right here are 3s, right? So let's throw this in. Let's throw a 3 in there. Okay, and then we got this sx, sy right here. Okay, well that is the upper bound for the x and y. So we know that that upper bound for the x and y is over here for the source. So let's make note of that. So here and here, and we know these are 2s, right? So we're going to fill that out. And we should probably make note that, at vid IID, it's 135, it's video 135, and the time is, 6 hours, 46 minutes, and 0 seconds, filling out formula. Filling out formula, that's what we're doing right now. Okay. So, unfortunately, we can kind of go over the filling out the formula since we just made a timestamp. So this 6 right here is coming from the dx, the destination x upper bounds. So the upper bounds minus the lower bounds plus 1, right? For the destination. Divided by the source. So the source, this 2, is coming from the upper bounds on the source. And then we need the lower bounds on the source. So let's take this and kind of paste this over here. Right, and so these are 0s. Okay. Now I feel like I've already screwed something up here. Yeah, I already screwed this up. So this is... Oh, yeah. So this is wrong. So this 3 here is the expected output. So I screwed this up. So this right here, let's copy that. The source and destination rectangles have the same origin. And I will cover what f is. So these are both... So this current test is being written so that we don't have to worry about the math. We want to add on variables as we solve... We want to isolate variables, right? So we want to eliminate the problem of the origin being part of why the calculation is wrong. And if we want to eliminate the origin as being part of why the calculations are wrong, we're just going to make the origin the same, right? Zeroed out for both the source and the destination, right? So that means that what we're currently testing here is only the squashing and stretching remapping, but we're not testing any of the offsetting logic in the formula, right? We're just testing for proper squash and stretch. Okay, so we know that we kind of screwed this up. So it's the upper bound minus the lower bound, upper minus lower. So what we thought was 3 is actually kind of 0 here, right? So this 6 is coming from the destination here, right? And this 2 is coming from the source over here, the upper bound source. So that looks good to me. Okay, so what is f and fx, and now what's fy? So f is the factor, is like the stretch factor. So in order to, we kind of like, so scale factor right here is our f, right? So scale factor equals fx and fy. So we take the destination rectangle divided by the source rectangle, and we get a scale factor. And then so right here, and then we use some basic algebra to solve for this. So if we want to take this source and put it on the other side, we can multiply, right? So destination equals the scale factor multiplied by the source, right? So if we take the source coordinate and multiply it by the scale factor, we're going to get the destination coordinate. Does that make sense? Because I'm honestly not sure if that's completely correct, but I'm pretty sure that is the correct math. So if we look at fx and fy right here, right, we're taking the size of the destination rectangle divided by the size of the source rectangle, and that's giving us a scale factor. And I think this scale factor may be off by 1. But you said you copy source into dest as many times as you can. So this is mapping... well, this is the scale factor right here, right? This is the scale factor logic, right? So scale factor logic, and this right here is the offsetting logic, right? So the new origin plus... so we take the input and we zero it out, make it local to 0, 0, right? And then we apply the stretch factor here, and then we make it relative to the new origin of the destination here with the plus here. And that gives us our output dx and dy. So this is for just 1 pixel worth of transformation. This is just 1 pixel worth of transformation. This is applying scaling and transformation. So there is both scale. This formula here has both scaling and transformation in it, right here. So here is the stretch factor, right? Fx and Fy is the stretch factor or the scale factor, right? The scale factor. And then this is the destination origin, and this is the source origin, right? This is the source input, and this is the output. So this is the input, this is the output. So we take the input and we zero it out. After we zero out the input, we multiply it by the stretch factor. After it's multiplied by the stretch factor, we give it a new origin relative to the destination, and then that's our output variable. So I do believe that this is probably off by 1. These lines here, they are probably off by 1. So we're going to figure it out, right? We're going to walk through the entire formula and make sure that this is correct, right? So we're going to just take this and we're going to just punch it into a calculator, right? We're not even going to try to do math here because we can't do math. Okay, so 2.333. Okay, so here's an obvious problem here, right? 2.333. That is already indicative of a problem. So, you know, fx equals this 2.333. Now, it's the same exact formula for the y, right? So fx and fy are 2.333, right? Okay. And let me put that back up here. Okay. Okay, so then we have this fx and fy. We got to fill out this formula now, right? So the dx, dy, like, how do we figure that out, right? So let's make a note of this. So at vid IID 0135 35, and the time is 6 minutes, 54 minutes, and let's say 23 minutes to keep with conspiracies here. Filling out formula. Right, so we're filling out another formula. So this just makes the int32 value. So we can kind of remove that. And this is just casting to int32. We could say technically that would be a floor. As long as things don't go negative, that would be a floor. Yeah. Okay. Yeah, everything kind of seems right until you're off by 1. And I've done this formula before, so I'm fairly certain I'm off by 1. So we know that these are 0, right? This origin is 0. This SX, this SXY, this is also a 0 origin. The input coordinate for the SX and SY is just 1 and 1, right? So 1 and 1. And then the scale factor here is this 2.3 nonsense, right? So this 2.3 nonsense. And what we really want is a proper truncation. So we'll figure that out as we get to it. But yeah, so let's steal this and see what we get here, right? So let's steal it, see what happens, and then figure out how we might fix it once we pump this into a calculator. Because I'm going to guess... okay, so give that a run. And we get 2.3333, right? So 0 minus 1 times 2.333 plus 0. 1 minus 0 times 2. Yeah, I mean, yeah, duh, right? So, okay, so we know that. And we know that this is going to get... So the problem could be that we just have to seal, right? Like, we're flooring, maybe we just need to seal, right? Because if we sealed this... So we're getting this 2, but if we sealed it, we'd be over here, right? So we may actually be perfectly fine, and the problem is that we need to... The problem might just be that we need to seal, right? That could be the problem. However, let's think about what would happen if we got rid of this plus 1 here, right? So if we did 6 divided by 2, right? What is, if 6 divided by 2, what does that give us, right? So 6 divided by 2. Right, that gives us a perfect 3, right? So I don't know why, but I think that the correct math, I thought plus 1 because we wanted to take the... Oh, I know why. I remember why. We don't want to take the size... So we don't want to take the size of this divided by this to get the scale factor. We want to take the coordinate range, right? So if this is 500 pixels wide, the last coordinate is not 500, it's 499. So if this is a 100 by 100, and this is a 500 by 500, it's going to be 499 divided by 99. And that's why when we're doing the math, we don't want to actually take the number of pixels. We want to take the upper bound in terms of range. We don't want to take the... Yeah, so I'm pretty sure that's what's going to fix it. Now, I could be wrong, but I'm fairly certain. So what we're going to do here is we're going to say... We're going to... so if it starts with the underscore, what is it? It starts with the underscore. It is reserved for the implementation, right? So I don't think I should do it. I would like to just make a macro like this, but I'm pretty sure that would reserve it for the implementation. So actually, let's make zzz, sure, equals, okay. No offset. Okay. And then over here, we're going to undef. Zzz, right? And then right in here. So we're going to write the formula like this because we're going to say, hey, we thought about being off by 1. We thought about the implications about being off by 1, and we realize, turns out, no, right? So we can say at vid IID in 0135, and the time for this, so the time is 6 hours, 59 minutes. Or 7 hours exactly. 7 hours exactly. And we realize that we don't actually need an offset in this formula. Things are pointing to do not use an offset. And so we just want to make a note of that in this formula to explicitly say no offset, because an offset, right? So offset yields off by 1, but no offset oh no, it's right here. So the offset here, offset yields off by 1, whereas if we do no offset, but if we remove the plus 1.0, we get right. So that's what's kind of going on here. Let's kind of indent this so we can kind of see this. Let's not worry that this is, you know, we get the idea. You know, after 3 threes in a row, I think we get the idea that it's repeating forever. Let's just call it 2.333 like that, you know. Yeah, so we think the formula, or I think the formula, to work correctly, we do not want an off by 1 here, because we want to take the maximum, coordinate here and the maximum coordinate here, and want to take the ratio of that. And we could test that out, right? We could test that out. So really quickly, if we would want to map something like 0, 1 to 3. Alright. Well, this is already what we're testing out, right? Never mind. Never mind, let's not redo this. Yeah, let's not, yeah, I think I'm onto it. Let's not try to, we've already diagrammed this out enough. We already diagrammed it right here. I'm fairly certain that that is the problem. Let's give it a roll. Let's give it a roll. See what happens. But yeah, I think that'll fix it. I think that'll fix it. And then I'm gonna have to... Oh, hold on. So this code is fragment shader code, and because it's fragment shader code, I have a preprocessor that means I cannot put quote marks in any of this code. So if any of this code gets quote marks in it, the preprocessing step completely fails on me. And I forgot about that, so let's go look for where we're saying that. And we're just going to use square brackets, remove the 1.0, whatever the heck. Okay, and let's control F through here and look for any place where I'm also using quote marks. Nowhere else. Okay, cool. Okay, let's give it another run, because now the pre-processing should work correctly. And that error is just because the compilation failed, but the pre-processing step went on as usual. So sometimes weird things happen, but not a problem. Okay, moment of truth here. Nope, so we're kind of worse off than we were earlier, weren't we? Because the 0th case is getting us this crazy negative. So all zeros yields like a negative, a very negative number. So what the heck? That looks like an integer underflow, integer overflow, something like that. Doesn't that look like an integer? Ooh, hold on. We have a potential the problem with this is now if we're only adding 0, then if we add 0 here, then if these are identical, we have a division by 0. We have a division by 0. Can we make this? I don't want to have a branch in my code, but maybe I don't have a way to do that. Uh-huh. So we make this a 1 and a 1. So maybe a seal would be more correct, because then we don't have to have this off by 1 error, right? That might be where we want to go here. I gotta do a lot of push-ups before midnight here, so I might have to take a break to start doing some more push-ups and just get most of them out of the way. Like do like 60 or something. Yeah, maybe a seal would be the best way to do this. So what needs to be sealed? We need to seal this scale factor. This scale factor needs to be sealed, I think. Now, I could be wrong with that, but if we could make it branchless, that would be nice, right? Sure. You know what? Let's take a break. Let's take a break because it's almost 7. I don't want to have to do like a whole bunch of push-ups like right before midnight. Yeah, so let's try to keep it branchless. But let's right before I go on break though, define let's make this little face, right? Actually, let's just stack the times together. So it's 7 minutes, 7 hours, 8 minutes, and 23 seconds to keep with the conspiracy. But yeah, I'm pretty sure I was wrong about that. I think we're going to have to just use some sealing. So let's go undef this little face here. And I'm going to try to get 60 push-ups done, and I don't know how long that's going to take, so let's just give it, I'm going to say 23-minute break. I'm going to try to get 60 push-ups done, jump on the trampoline for my 100 jumps, and then maybe heat up my coffee if time allows. 23 minutes. Yeah, 23 minutes. Let's do 23 minutes. Let's go to the break thing, because I only got like 30 done, because yeah. So we're going to try to get all 60 more. And I get 60 more done. And then whatever time is left, I'll just mess around on YouTube or something until the time moves. Yeah, so 23 minutes. So you're going to do some push-ups and stuff, and I'll see you when this is over. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. More. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 7, 8, 9, 10. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Weights. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. For 60. Okay. So, actually, 60, 70, 80, 60, 70, 80, 90. So if we do 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Okay, so now, trampoline. Okay. So 60, 90. Put it set exactly 100. And then we have 40 more to do later. Okay, trampoline, gotta go. Trampoline. Okay, I got a little time to eat. And I'm just gonna try to stay away from anything too incriminating on YouTube here, because I find if I mute myself, I never forget to turn it back on, and then I end up with recordings that have no sound. So let's see what we got on YouTube today.
What's your childhood mystery that you finally solved years later? I met my wife in college, and when we were dating she often mentioned that when she was a kid she had a play doctor's kit that was stolen from her house. She had some surgeries really young, and so her parents bought it for her to demystify the doctor's office. She'd use it all the time on her dad, poking and prodding him. One day I asked her about the robbery. Did they take everything? Jewelry, the TV, other valuables? No, and no. It hit me. I asked, so someone broke into your house and only stole your doctor's kit, leaving anything worth fencing there? Yeah, why? Did you ever consider your folks were tired of you using the kit on them all the time after you got better? Oh, damn. We confirmed it with her dad later, but for 15 years she had believed some thief broke in and only stole her beloved doctor's kit. My dad used to occasionally burst out with this one line of a song. Said Barnacle Bill the Sailor. Only ever that line. When I was 6 or so I asked him why, and he said it was an old drinking song that was absolutely filthy and I was too young to hear the rest of it. This continued once or twice a year until I was 18. I told him I was an adult now and he could tell me the rest of the song. I distinctly remember him looking up from the newspaper, sighing and folding it, then going, "The truth is I can never remember the rest of the song," and then went right back to reading the newspaper. The weird smell that I referred to as a stinky cheese smell were probably a symptom of seizures. I would happen maybe twice a year. It's not really like cheese. It's like a smell that isn't a smell. IDK, how to even describe it. It was so minor parents disregarded it. I can remember it starting in 2nd grade. I suddenly started having it a lot more as an adult when I hit 28 and got diagnosed 2 years later after symptoms became way more extreme. Makes so much sense now. The entire time I lived in my childhood home, my mom hid my Christmas presents in her secret hiding place. She made it sound mystical and mysterious a few months ago, a while after I moved out. She finally told me what the secret hiding place actually was. A Christmas tree box in a cabinet in the garage. She would replace the Christmas tree with my presents when she put the tree up. I remember being about 8, and in the car with my dad. I was in the front seat and we were driving somewhere, and this song came on the radio. He cranked it and said something about it being the best guitar playing ever. He really jammed out, which was really uncharacteristic because he was usually so stoic. It was the only time I heard the song, and he died before I could ever ask him what song it was. When I asked around, no one knew WTF I was talking about or what song I was thinking of, so I had this melody in my head for years. But how do you look up a song that has no lyrics? So for years and years, this song stayed on the back burner in my brain. I was afraid to forget it. Somehow this story pops up when I'm like 26 or so, chatting with my husband, and we searched YouTube for best guitar songs. After about 15 minutes, we find it. Cliffs of Dover was the song that I'd burned into my brain on repeat for 16 years. Now I jam out to it with my kids.
Okay. Let's close that. And let's try to figure out what the hell we're doing. Hold on. I need to clean some stuff up. Hold on, I'm almost here. Just gotta working on another monitor here. Okay, cool. Close that. Yeah, so I think that the best way to do this is probably just have a ceiling command in here. I think that's what I'm... Right, so instead of saying... Right, this formula is pretty close to correct, but we would need a seal. We would need a seal, and if we did a seal, then I think that maybe this would work. Now, I'm not certain, but I think that my hunch is a seal would work. But I also believe that I did a completely overkill Stack Overflow post a long time ago, and I don't even know if it got upvoted, downvoted, or never seen. So let's look for how it's done. Because I feel like... Oh, not how it's done, but how to do it, I think. Hold on. How it's done. Try how to do it. Yeah. So, yeah, I'm pretty sure this is like old Stack Overflow post. Now, don't ask me why I called it how to do it. I think it's because somewhere when the person asked the question, they said, you know, how to do it in the verbiage of the question, so I kind of stuck to that. And let's go look for that. I'm going to go look for that in my shortcuts really quick. And make a synonym with the underscore version. So, how to do it. Yeah, so this question right here, I'm going to take it, put it in my browser, and I know I addressed this formula in the, right, so it's like an old question that has like thousands of views, and my answer is like way at the bottom, and I did some formulas and things, and I kind of did it overkill. Because it was when I was working on the first prototype of my engine in JavaScript, so I was doing like HTML5 stuff, and I got one upvote, so only one person has seen it. That's fine. So yeah, I did this crazy thing, right? This is my whole answer right here. So I got this stuff and this stuff and this stuff, and some nice little diagrams and things. So let's look at this diagram here. So we got this rectangle mapping code, and somewhere in here we have the correct formula. So let's go find out where that formula is. So we need to look for like VP2. So look at this WebGL code. We can probably find it. So let's go look for, you know, FVP2 and see if somewhere in here we can find, yeah, okay, I understand. Why is the zoom seems like out of blown over here. Let's try to do 100% zoom, reset. And the zoom, yeah, so let's just look for VP2 for a second and see if we can find the mapping logic, or my browser's crashing on me? What the literal hell here? Or not literal hell, but okay, so what we're gonna do is we're gonna take this. I have no clue why that's not working. Let's close it. Maybe they're running some malicious ads on Pastebin? I don't know. But that just doesn't seem correct. Okay. So, like, it's not that big. Am I dropping frames here? What are my frame rate? 0.5% dropped frames. I'd say that's not the case. So let's look through here really quick and try to find that diagram. So I got all these diagrams for this first iteration. This is like the first prototype of the engine. This is like a very old first prototype of the engine in JavaScript rather than C code. And yeah, we're gonna have to go back here. There's just too much stuff here. So let's go how it's done again. I want to see how it's done. So I know I solved this formula before, and I want to see how I solved it. So how to do it. So if we look for how to do it, and look at my old answer again, and we try to find that diagram, and other people kind of reference it, but, you know, off by, so I don't do this formula correct, we get off by 1 error. Oh, I even have an explanation for how to use this. VPC-NO. So let's look for VPC-NO. So Control F, VPC-N, and then O. Okay, so we have a formula here. So I got this x-coordinate minus zeroing out the x-coordinate and then dividing by... Oh, I see. So this is completely different. Okay. Mm-hmm. Okay. Okay, here's this diagram. I have no clue what VPC-NO stands for. Let's see if we were friendly enough to ourselves to put that in our commentary. So if I go VPC-NO means... VPC-NO means... Nope. Oh, hey. So VPC-NO means, I guess that also VPC-MO means, so VPC-MO means maverickized output, normalized output. VPC-MI means, so I'm just looking at some old shortcuts where I have definitions, and I'm realizing that one of the ways I typed it, I didn't get what I expected. VPC-NI means... Okay. Normalized inputs, maverickized inputs. Normalized and maverickized. Okay, cool. Okay, so we have normalized outputs, and the normalized outputs are normalized between this, like, 0 to 1 range. Okay, I see. So we're going to turn it into, oh, so I see, we're turning it into percentage and mapping it. So we're turning it into, so rather than using a scale factor, we're using a percentage along path. Okay. And okay, I can roll with it. I can roll that. Now that I realize it's a percentage along path, I think that's all I need, and I can get this working. So this formula, we're going to try something different, right? So this is the original formula. So we tried this formula. Let's try percentage along path remapping. Okay, so okay, so we take the SX, oh, crap. Instead of a +1, we're going to get a -1. Okay. So the range is between, right? Because remember, when we're talking about remapping coordinate, the first coordinate starts at 0, 0. So we take this, so we want to take this range, right? So if this is 1 and this is 1, then we minus these. Well, hold on. 1 minus 1 gives us a 0, 0, right? So actually, no, minus 0, 0. So if we take the upper bound and the lower bound, the only possible coordinate you can be on is 0, 0, right? So then we're going to take the current coordinate, right? So we're going to take the current SX coordinate. So 1 over any possible coordinate we can have, right? And this is going to give us a percentage, right? So a percentage on path. And then what we're going to do is we have to multiply that percentage along path. Input percent along path is this, right? And we need to take that and multiply that percent along path by the maximum possible coordinate. Max possible zeroed out chord in the destination, right? So we take, so if this is like 1 to 1, right, then we just have one coordinate, so at 0, 0, and we multiply by that. So can we still do division by 0? And yes, we can still accidentally do division by 0 here, right? Because we can have this divided by this, which would be 0, right? And so we still kind of have a problem with the division by 0. So another question is, well, do we have any checks for like division by 0? Do we have any cases where it's like, yeah, like right here, this divided by this x1, x0, in fact, if they're on the same exact location, yeah, we have a division by 0 here, right? So we have the possibility of dividing by 0 here. Same thing here. We have the possibility of, if these are both 0, we can accidentally divide by 0 here. Okay, so let's look at this. Let's look at the formula and think about that. So in order to do that, we can say we want to get rid of the ability to divide by 0. I'm thinking we could do SX. Well, first of all, SX needs to be zeroed out, right? So this needs to be zeroed out. So each one of these needs to be SX0. Each one of these needs to be zeroed out. So we zero this out and find its range on this thing that's also zeroed out. But we're also thinking that we can plus 1.0 on both of these. Right? So, we're thinking, you know, 1/5, 2/5, 3/5, 4/5, 5/5, right? Something like this. The problem is that if we add a 1, then the first coordinate is, we could do this if it's 1 indexed, right? So let's pretend that these coordinates, we're going to do 1 indexing, right? So 1 indexed location. So the SX minus the, so if this is 0 and this is 0, right? So it's at 0, 0, plus 1, so 1 indexed. And it's like, you know, 1/5 or something, right? So this is like a 1, and then say this upper bound. Let's say the upper bound is, so let's say there's 4 locations. Let's say there's 4 locations. And usually we would have, usually what we'd want is we want 0/4, 1/4, 2/4, and 3/4, right? But we're saying don't do that, do 1/4, 2/4, 3/4, and 4/4. And then we have the problem here where this coordinate is, so we really want 0/4, 1/4, 2/4, and this was going to be in thirds. So the number of ifs, right, is a -1, right? So the number of ifs here is a -1. So this here, if we have coordinate 0 to 1 to 3, so if it's 0 to 3, 0, 1, 2, 3, then this is the number of ifs. So 3 is the number of ifs, and if we're going between right? So this is for 4, though. If the width is 4, then the ifs is 3, right? If the width is 4, the ifs is 3. So that means we don't need the width, we just need to subtract these. And it cancels itself out, right? Because we want the number of ifs, right? So the number of ifs for 0 to 3, 0 to 3, the width is 4, but the if is 3. So well, here's our if. Okay. Now, this number here, this SX is going to go 0, 1, 2, and 3, right? Because those are the valid coordinates for it, right? We want to zero it out, though. We want to zero it out, but there's nothing here, right? So, that's all we need to do. Okay? So, input percentage along path, and this is zeroed out. And now, the problem with this is that it works, this formula works until we go, until this rectangle. If the source rectangle is 0, if these two coordinates are exactly the same, we're going to have a divide by 0. So it works almost everywhere, except for when the source is so let's say that yeah, because if it's 0, we don't know, is it to the left, is it to the right, or is it in the center? We don't know. There's no relative positioning. There's no relative positioning anymore if it's 0. So, here, you know what? You know, if okay, so unfortunately we're just going to have to put a branch in here. Okay. So if this is completely equal, we're just going to say that it's just in the center, right? So that would mean that dx just equals, right, there's assuming that these are completely the same, so it gets zeroed out. There's only one possible coordinate where the input could be, if it's within the valid range of the bounds, right? So if it's in the valid range of the bounds, it should be exactly this, and therefore dx would be dead center, right? So dead center, and dead center would be just dx1 minus dx0 divided by 2.0, right? Does that give us the dead center? So let's say we have, you know, 0, 1, 2, 3, and 4, right? And that makes the width here. The width here is 5. Okay. The width here is 5. And 5 divided by 2 is 2.5. If that gets truncated, then it's going to turn into 2. Right, so make int32 and just truncate the result of this, right? So we're going to take the upper bound 4 minus 0, it gives us 4. 4 divided by 2 is 2. So it's just going to be dead in the center. And then the same thing for the y, the upper bound minus the lower bound, right? Else, otherwise, if we don't have that edge case, right? So if we have that edge case of it's just like just we can't relatively position it because the viewport is 1 by 1 pixel. Right, so arbitrarily pick center because cannot figure out where you are relatively when viewport is 1 by 1 pixel in size. Right, so that's kind of what's going on here. And for this, we'll do input percentage along path, right? So we kind of zero it out with the SX0, okay? And then we want to take the minimum minus the maximum. So let's say this is like, if it's 4 minus 0, right? So 4 minus 0, then the maximum coordinate is 4. Okay. And but this dx1 dx0, okay, cool. Okay, so we want to take all this, and then we just want to say, we just want to add we want to take dx1 plus, right? We want our dx0. All right, so we want to re-add. We want to re-add this, right? So this is remapped. Hey, how's it going? So I figured out a different formula, and unfortunately I have a condition where if the input rectangle is exactly 1 by 1 pixel, we technically can't know where it relatively lays, right? Because it's just 1 by 1. Is it closer to the right edge or the left edge, or is it closer to the center? We actually don't know, so we're arbitrarily going to pick the exact center of the output if that's the case. And then we're redoing a formula. So we're going to take the input. We're going to take the input and turn it into a percentage along path. So this SX here, we're going to zero it out, right? So we're going to zero it out by subtracting the origin. So just pretend the origin is 0 for now, right? So this is just a minus 0. And so if SX is, this is a maximum inclusive range here. So SX could be 4, right? 4 out of 4. Or it could be 0 out of 4, 1 out of 4, 2 out of 4, 3 out of 4, 4 out of 4, right? So something like this. 0 out of 3, 1 out of 3, 2 out of 3, 3 out of 3, right? And so we have this 0, but it's not a divide by 0 because we got the 0 on the other side. And so, though in this calculation here in this little diagram, even though the width may be 4, the ith is 3 for this kind of calculation. So we convert the input as a normalized percentage along path. And then we calculate what the largest zeroed out coordinate in the destination is. Can you show me how you want to... Can you show me how you... Sorry. Can you show me how do you want to map the copy from source to dest? Yeah, hold on. So let's do a little diagram here. So I just want to take a coordinate. I just want to get it proportionally correct, right? So if this coordinate in the source is completely in the center, then the output should be completely in the center, right? If this point was over here, then it should be mapped completely over here, right? And so when we're looking at the rectangle source, the rectangle is defined by an inclusive rectangle that includes this point and this point. So this whole rectangle in pixels is determined by this point and this point inclusively. And then this output destination rectangle that we want to map onto is determined by this point inclusive and this point inclusive. Okay, so we're going to take the output point. So this would be like, let's say we're going from 0 to 4. So 0, 1, 2, and 4. So so the max possible coordinate times 100% gets the maximum possible coordinate, right? 0% times the max possible coordinate gets 0. But you copy source 4 times, right? Oh. So what I'm doing right now is this remapping is for something else. This remapping is for looking at this is actually a different problem. So that would be confusing if you thought that this was math for that exact same problem. Yeah, that this is for zooming into. Yeah, this is for creating a viewport. This is for creating a viewport to zoom in and out on pixels on the screen. So this is actually not for that cutting, pasting, rendering logic. This is for camera control. So this does not relate to all the tech demo stuff I showed you earlier. That's not what this is. So that could be the reason you're confused. Oh, maybe I'm not. Maybe I'm confused. Like if source is 1, 2, 3. Oh, okay. Well, let's say. Okay. Well, let's kind of roll with this for a second. Okay. So if this is the source set, okay. The output is going to depend on. Let's say this is the output, right? So, well, first of all, dest will be 1, 2, 3 x. So I need more. Need more input, right? There's different variables, right? So we need the input xy. We need the input rectangle. We need the output. We need the output rectangle. We need these three. Or we could say source. We need a source xy. We need a source rectangle that xy is on, and then we need a destination, right? So we need these three inputs for our mapping. So source is 3 by 3. Okay. So let's look at that. So okay, so destination size is 7 by 7. Okay, so you're running off of that diagram I did earlier, right? So, cool. Okay. Okay, so we got source, we got dest. Source is 3 by 3, dest is 7. You need \n each 3 for source and n 7 for each, divided by n for each 3 source, and divided by n for each 7 for dest. So see what I meant. See, 1, 2, 3. Not sure what's going on here. Let me try to finish this thought so I can like try this algorithm out and see if possibly I may have already have it solved, but let me see if I can finish this thought, and then I'm going to come back to that. So this is the x. And these are floats, so Okay, let me try to run this and see. I'm going to try to get this compiling because I think this might pass my tests. I don't know yet, but I think it might. So let me try this and see if it doesn't completely screw up on me. Fix some compile. Okay, let me go look at that. Oh, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. And dest is in size 7. The mapping will. Oh, okay. Oh, yeah, you are, yeah, this is... I see what you're doing. Okay, so I see what you're doing, and that's a different problem. That's not the... This is not the problem I'm working on. I see what you're doing, right? Because, I was... So, no, this is... the technical demo I showed you earlier has nothing to do with what I'm writing right now. It's a totally different problem. So that would be very confusing. And now I kind of see why you're looking at this and seeing, oh, it's not a complete, why would I be using a prime when everything kind of fits in a quad tree-like thing? And if all my textures are powers of 2, why the heck would I be using an odd number? That's because it's not for this. So yeah, this, I know what you're talking about, right? I can see you, you're looking at this and you're, trying to take those 4 different quadrants that I was rendering, right? And you're thinking of, like, remapping logic for that. Yeah, this is a different problem. It's not this problem. It's not this problem. That problem is, this problem that you're talking about, I already have that problem solved. This is a different problem. So, I'll try to describe it again, but it's just, you could think of me as trying to, yeah, it's just range mapping. I'm doing very simple range mapping. It's not as what you're doing is much more complicated than what I'm doing. So ifs error 209, okay, so I screwed up here again. Let's look for a double quote. I keep on doing this. So number of ifs. Okay. So let's just try to get this rolling. Because I think I have the correct formula. I think my initial, oh, that is simple? Maybe, yeah. Maybe if I understood what you're doing. Unused variable sy. Okay, well that's a big problem. Let's go look at our math here. So we got this sx, and then this should be y. So all these things that say x in here should now be y's, right? So this is a y, this is a y, this is a y. So this, we did a crappy refactor, right? So, okay. Let's give that a... So the cool thing about compiling is both C99 code and GLSL code is that when I screw something up royally, the compiler tells me about what I screwed up. So we're going to get rid of the scale factor thing. We're going to get rid of the scale factor thing. Because we're going to actually solve this completely. All these diagrams for how I was doing it, I realized that we need a different formula. So I'm going to hope that my tests at least get further. Not further, in fact, less far. I'm getting a negative. God damn it. Okay, let's look at this. Who can't math? I can't math. So let's look at this third test case here. 1, 2. So this third test case, we're just getting this negative. We're getting this negative underflow. It looks like. So the third test case, yeah, third test case. Yeah, test index 3. Whatever we think we're doing, we are screwing it over quite a lot. So 0, 1, 2, and 3. So the X... Oh, hold on. This isn't quite right. So let's break this apart. So if 0.0 equals sy1 minus sy0, right? Else, okay, it's the same deal here, so let's break this apart and just say this is the y version. So here's our y's, here's the x version. So dx is either set here or it's set here. Okay, let's run that again because that is a big change. Right, so if the source y location is... Yeah, so let's give that a shot. So in some cases we can... we don't care about the destination being 0, 0, only the source, right? Because we can convert in a direction where we lose information, but we can't... Well, once we lose information, we can't go back the other way. So we can map to a viewport that's 1 by 1 pixel, but we can't, once we're at a viewport that's 1 by 1 pixel, we can't effectively roll the conversion back in the other direction because we've lost too much information to get any relative positioning. Okay, so let's give this a shot and see if we can get further. I can't believe this is taking me like 8 hours to do this simple thing. I mean, I have test code, right? I have test code, so it's like, okay, so now we're at test index 7, so we're a little bit further, right? So we got to test index 7. So let's go look at 7 and say, okay, well, what's wrong with 7? I think last time I failed on 8. So let's go look at that and see what we have. So on test index 7, we're saying that if you are at 0, 0 within a viewport that's 1 by 1 pixel, right, that we do not know where you're located, right? So this is saying, you know what, we don't know where you're located. And if we don't know where you're located, lower bounds are all 0, upper bounds are all 511s. Now the problem here is that for whatever reason we're getting a 0. This is the 8th test. Oh, here's the 8th test here. No, this is the 7th test. So does that all look right? 511s and 0s, and we're getting 0s out. So let's go look at that, why that would be. Why is that test case giving us 0s output? It could help with your problem. I think I'm onto it. I'm not completely stuck. I'm not completely stuck, but I will... Hold on, do I still have that open? I don't have your thing open here. Let me open your thingy. Hold on. Where is that thing you sent me? Oh, this thing. Let's go take that. Copy that. Okay, move that up. Let's go paste this. Okay, we got that open. And we're getting 0, 0 out. We're getting a whole bunch of zeros. So it's looking at this and saying, okay, this is 0, 0. So it's triggering the 0, 0 case. And then, oh crap, this doesn't make any sense, that's why. So once we do this math here, right, so we're going to take this math doesn't account for re-adding the origin, right? So we minus divide by 2, but then we have to add the origin back on. So dy0 plus this nonsense is how we want to do it. Same thing with over here. We want to go dx0 plus these calculations over here. All right, so we want to, after we want to zero it out, divide it by 2, and then we want to add the origin back on, right? Yeah, I think that's correct. Okay, let's give that a roll again, because we're passing some tests. Like I'm not completely stuck because I'm passing these tests. So let's I'm not completely stuck. I think I know what's going on. Now I could be wrong. I could be completely full of BS, right? Like I don't know yet. Well, that passed. That passed all the tests. So I'd say the remapping logic works there, but my diagrams, my original diagrams are completely wrong though. So the original way I wanted to solve this is complete BS. Like it's a good idea. These original formulas are okay, so here's what we're gonna do. Yeah, this formula, I can't believe I mean, there's more than one way. What's that saying? There's more than one way to skin a cat. So, I mean, there's probably more than one proper way to solve this. So, formula. Okay. So we're just gonna take that and we can archive it into our documentation because we were kind of off in the way we solved that. So all this stuff here is not quite what I want. Okay, so this original attempt with the original diagram, yeah, I don't think that, I think that was misguided. I think I think I didn't know what I was doing. I think that my approach, maybe my approach was slightly correct, but it was off by 1 somehow. So we're just gonna tuck that away somewhere. And then we're gonna take this little stamp here, and we're going to tag this, right? So we're gonna tag this so that we can say, you know, we have it in the documentation. Like if we want to see what we were originally writing, we can see it if we want to take a look at it. But I don't think this formula is good. Because I looked at old source code I wrote, and that's not how I wrote the formula. Then I walked through the new formula. It made sense. So, and now all my tests are passing. So all my tests are passing, which is a sign that that's proper. We do, however, need to make sure that everything is indented a little bit better. So if we look at this, I'll just say M for mapping, you know. And let's go over here. So right, this is turned into shader code, so we're trying to get, yeah, I mean, do your thing, man. Oh, sorry, I kind of missed that. I kind of was scanning over what you wrote, so I missed that you're doing the toy logic, but yeah, let me, when you finish, I'll, take a look at it and maybe compile. Yeah, do your thing, and I'll take a look at it and try to see what you're talking about. But I think you're doing a different transformation than what I was trying to do. So let's try percentage. Okay, so I'm just kind of cleaning some stuff up here. And I'm trying to condense this logic a bit, so it's not so... So that it's not so, what do you call it? Alright, I'm gonna check that out. Okay, that looks good. And... Okay. Okay, so, don't take too much... Yeah, okay, we'll take a quick look at it, see if I can understand what the hell you're doing. But reading code is always hard, right? So, like, Oh, cool. So we got a nice little kind of run thing. So let's hit run, see what happens. Okay, and let's scroll up here. Okay, we got source, we got destination, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you're taking a set of. Are you taking a set of values? I'm gonna read the code, but it looks like you're taking a set of values and you're stamping it 4 times. I'll read this though. Okay, so let's see. Print matrix. So we have a pointer, an int pointer to a matrix, and then we have a size, so a size of the matrix. So we're going through every single element in the matrix. %d. Hold on, let me put this up here for a second so I can see what you're saying while I'm reading through this. Did 2 versions. One of them, it's the main, the simpler one. Probably skip to main, which has the simpler version. Okay. Copy matrix. Okay, do the thing, the simpler version on main first. Okay. Okay, main. Okay, so we got a 2-dimensional array, which I don't really use 2-dimensional arrays, so I don't know what the hell I'm doing here in terms of how you. I thought only Java could do that. I didn't know that C could do this, the 2-dimensional array kind of thing. But well, I guess it's not a. Well, I guess it's not a feature, right? It's just like an extension of the syntax, right? Like how you can do a double. You can technically do a double pointer, right? So if you can do a double pointer or a triple pointer to your heart's content, then you could just stack on array accessors as well, right? So what you're saying here is this is a pointer to a pointer, right? Or does that make sense? Or I might be reading that totally wrong because I never really use this syntax, so I might not understand that correctly. Okay, but we have, you know, this, right? So we have a width and a height, right? So I do understand this is width and height. I just don't understand the mechanics of how that works. Okay, the do the thing function does the same thing, treating them as 1D arrays. Okay, got ya. Yeah, I might prefer the flat logic, but let's look at this, because maybe this is easier to understand. So assert the size is less than or equal to... The source location is going to be less than or equal to the destination, right? So that's fine. That's usually what we're doing. Okay, spacing equals the destination size modulus the source size. Okay, so destination size... source size. So we're taking what's left over. Okay, spacing. Okay, yeah, I see. Okay, I think I see. Yeah, how many times it goes in evenly, and then whatever's left over is the spacing. Okay, got ya. Copies is the destination size divided by the source size. Got it. Yeah, so I think you're clone stamping. Like I think I know what you're doing, but it's not the problem I was trying to solve. But I see what you're doing. I think I see what you're doing. You're doing like a clone stamp. Okay, so for size, I equals 0. I is less than or equal to copies. Okay, so we got I and J, right? So I am assuming is going to be X, and then J is going to be Y, right? I DST, J DST for a distance. Okay, J times the source size plus the spacing, and then copy the matrix. So we have the destination. So we have an XY of the destination. We have a source pointer to the source, and we have destination size. We got source size. This source pointer is getting dereferenced. I really wish I could color code this really quick and see where that's coming from. Source. Okay, here's the source. Okay, so we're taking from the source. Are we doing any fancy pointer math here? Are we just dereferencing it? Are we just so copy matrix first, second. So the second parameter of copy matrix is just an int pointer, huh? Oh, it's an int pointer, but over here we're dereferencing because it's a double pointer here, so we have to dereference to get a single pointer. Yeah, because this is a double pointer, yeah. Are we doing anything in here with the source besides that? Okay, right. Okay, got it. So yeah, so we're just dereferencing. We're just dereferencing it once to get a pointer, like a flat. We're getting a flat pointer to turn it into a 2D array down there. And when we get that pointer, right, we're just gonna get the base address, right? Because with C code, right, we're guaranteed to get the base address of things, right? So right, the 0th index is always the base of the array. The 0th address is always the base of a struct, etc., etc. Okay, okay, I see what's going on there. Yeah, I think that... Yeah, I think what you're doing is kind of like a... I and j... I times... Okay, so we got, like, I times the, so we got x-axis times a stride plus the leftovers, mapping to an x times a stride plus the leftovers. Kind of like a nice little, you got like a nice little xy to index formula here and an xy to index formula here. Yeah, so I think what you're doing is you're doing like a Photoshop clone stamp kind of a thing. But this is a different problem. This absolutely is a different problem than what I was doing. But it's but I might need this in the future. You never know. Like this is definitely like in the realm of what I might end up doing something like this in the future. Like this is like having like a clone stamp. Yeah, doing like a clones. I might be doing something in the future with like a clone stamp or whatever. So as far as I'm concerned, this is like I think this is clone stamping. This is like a evenly spaced clone stamping. That's what I think you have. That's what I would call what you have here. Evenly spaced clone stamping. So I'm gonna paste that in there because that is what I think is going on. Maybe right, like in Photoshop, how they have a clone stamp. So that's what I'm gonna call this. And then I'm also going to make some shorter shortcuts for that so that I can find it later. So like clone stamp. Try evenly spaced and then obviously this is kind of long, so let's make a shorthand one and call it ESCS. ESCS, right? And then right here, I'll do ESCS and ESCS like that. And let's actually make it a URL, right? Just so that it's a little bit less terse. So ESCS URL. And then down here, what we'll do is we'll say, you know, ESCS means, like, what the hell does that mean, right? Okay. And then we also have another problem, which is I do dyslexic things. So ECSS, or something like that. Or ECSC means so I just foresee myself typing this incorrectly in the future, so I just want to make a note of that. So ECSC, probably typo of ESCS. Okay, so like, right, I'm gonna absolutely, like, I'm gonna read this here. I'm going to read this like a little prompt here, and then I'm automatically going to type it the wrong way. So, ESCS. Or... Yeah, okay, yeah. So that's the ways that I'm probably going to type it wrong. So... Let's, also put this like RBSRBS clone stamp. Okay. And what about stamp? I think stamp already has some choices here. Stamp, let's say pick stamp kanji or pick stamp clone. And if that happens, then we have to create something like, you know, instead of clone stamp, stamp clone, right? So stamp clone, clone stamp. And let's go and find that. So if we look for the stamp kanji, we're going to have to change around how we named that. So, looks like you used it more than one place. So right here, stamp. STA is a very terse shortcut, so I'm going to, now that I'm here and I realize there's this 3-letter shortcut, I'm going to put this here so I can find that later, because I don't want to have to write a regex to find that in the future. And we're just going to rename this to stamp kanji or stamp kanji or stamp kanji, right? So that way we've kind of renamed that, because I don't really code in Japanese anymore. That's just a thing that I found was fun. So now when we type stamp, we'll be prompted with stamp kanji or stamp clone, and then we can kind of find our way back to this piece of code in the future. If I'm like, hey, there was this clone stamp thing, or maybe like mirroring. Let's try mirroring for a second. Don't got that, but try RBS clone stamp. So it's not really mirroring, but I do anticipate that as time passes by, right? So we're gonna play telephone with our own brain, right? So when you think about how gossip spreads and people slowly, as a message passes from person to person, that message kind of degrades. The same thing can happen with your own recollection of events. So there's the possibility that cloning will kind of degrade into mirroring in my brain later, when months and months pass by. So we'll have like mirroring as well as a way to kind of try to find this, right? And then we can also keep the date, say 2021 0215, right? So that way we can find that when we're looking for it. And let's kind of see, I equals y equals vertical, j equals x, yeah, I, okay, yep, so I had that correctly, right? Yeah, okay, yeah, I see what you typed about the code you wrote. Yeah, I got that, yep. Okay, cool. So, let's go put that back over there. And let's close this. Let's readjust our windows because they don't snap perfectly to our monitor the first time for whatever reason. And let's give this a run because we kind of like threw in a whole bunch of comments to try to like clean this up and make it a little bit nicer. And we just want to make sure it still runs properly. And then we also want to make a snippet. I mean, this is a ridiculous snippet. But if it works, it works, right? So if it works, yeah, if it works, we're good. So now I want to press the U key for a second and see if I can get this to work. So U key, 0 key. Okay, so we still got some problems here. I'm gonna work on that. So let's take this snippet here, percentage along path, whatever the heckness. We're gonna just steal this, and we're going to put it into a snippet because I had ICR. Where is this? Let's see if we have it open in one of our other editors. What the hell? Put this over here. Okay, so... Nope, not there. Okay. So we're just gonna have to open it back up. Okay, so I can see it. I can see it in my notes here. There's a thing called inclusive chord remap, and it's in the CXX folder. We gotta go open that up. Okay, so CXX. That's not what I wanted. So this formula, yeah, that's not quite correct. So we're gonna trash that. Now this is kind of ridiculous, right? Because it's like, look how, like, large this is. It's very fluffy. And we may want to, like, think about our decision to write it like this. But we can... Anywhere where the indentation is messed up, I want to fix that. And... I don't know why... Oh, I see. Just try to align that to... Okay, so we have this little snippet. This snippet seems to be working all right. It's not the best snippet because look how, like, ridiculously big this is. But it's nice to, like... I was digging around for this code because I knew I had written this code before somewhere and I couldn't find it. So we're making another snippet just because I don't want to have to look for it again. So so it's also viewport mapping. So if we try to use the formula, we want to use so we're gonna try this, right? So if I type this, I'll make a note of this in the comments right here. ICR C99 paste. Right. So if we want to use this, we can find it right here. And there's also a lowercase version, yeah. And then we'll put the date. So this is 2021 0215. And now we have viewport mapping. Or, you know, port mapping. Port mapping. Port mapping. If we do port map, or port map, try viewport mapping. Right, so if we get something kind of nailed, if we have something kind of close, we're gonna have a suggestion for something to try out. And then same thing if we type this backwards. So if we do map port, or if we do map port, or we do map port, try viewport mapping, and this will be the second suggestion. Okay, cool. So now we have... The idea here is just to hope that next time we have to do this, that we can find that kind of logic and not be like, blah, I don't know what we're doing, right? That's the hope, right? Okay, so we have this function here, and I'm not seeing what I want to see in the viewport, though. Like, it's like the logic seems kind of correct, but then we use it in the renderer, And we're not getting anything. We're not getting what I would expect. So, we gotta see, like, oh, well, I see why we did this wrong. So I'm not calling this correctly, first of all. Right, so I tried to group the mins and maxes together. That's not even correct, right? So that's, X's then Y's, zeros and ones. It really makes more sense. It honestly makes more sense, this formula here. I really like the formula more in terms of... Like, usually this is how I order things, right? I do general to specific, so generally is X, and then specifically it's 0 or 1, 0 or 1. However, grouping things in terms of min and maxes, min boundaries and max boundaries, kind of like is more intuitive here, I think. And we're already kind of using it improperly, right? So, because then over here, down here, right, we're grouping this as a min and a max, and that's not the correct parameter order. Now here's the correct parameter order here, right? The X's and then the Y's, right? But this is XY, XY ordering. So so this is completely wrong, right? This is, no matter which way we organize things, that would be wrong no matter what. So we have to, it's like, I don't really want to break convention and throw it in the other way, but it really makes more sense. Yeah, like we could put it into a, like this might be one of those cases where we just want to throw it into a, right? Like if we put it into a vec type, or even a rectangle type, right? We could have a rectangle type. If we used a rectangle type, then we wouldn't have to worry about it. But then we have to create structs for that, and the structs make it like, yeah, but I think if we're gonna screw it up, yeah, I've been trying to not make too many container structs for things, just so that I can kind of see, I can see it kind of out there, kind of laid out there for me to look at. I'm gonna keep on doing it that way for now. But yeah, making container structs is a good way to do things, is a good way to pass things around, so you don't end up with this kind of parameter hell that I'm kind of experiencing right now. But yeah, I'm gonna change this. I'm gonna say XY, XYs, and we're gonna do the lower bounds, and then the upper bounds. And then we're going to do the same thing for this. We're going to change this, and hey, the cool thing is, hey, we have tests, right? We have tests, so after we change around these parameters, we can make sure that it still works, because we can run our tests, and if it crashes, then we've screwed something up. So that's cool. For instance, since we've already messed this up, we're going to expect that the tests fail, right? Let's close this. I'm gonna put that diagram you showed me in here as well. RBS, clone stamp diagram. Okay. Let me go back over here. So yeah, so if we run this, we'll expect it to fail, right? So we change the parameter orders, so we expect it to completely blow up in our face, right? And if it doesn't blow up in our face, then we're gonna have to be kind of concerned as to, you know, why did it actually work, right? So let's give this a roll and see if it crashes. Okay, so yeah, we failed. Cool, very cool. So let's fix that though. Okay. But yeah, I'm gonna refactor this a bit. So up here, I think the more sensible way is to do this kind of a thing, right? So we got the rectangle. We have a conceptual object here, right? So instead of passing in a rectangle, I just make a rectangle. Right, so we could write this like, you know, we could write it like this, like, source, like we could say, vec2, right, vec2 src, right, and then we could say, rec, right, we could have a rec pointer. We could have a vec2, we could have a, well, let's just do everything on the stack for now. We could have a rectangle pointer, we could have a rectangle, and then we could say rec src, right? And then we could do something like, you know, we could have another rec, which is rec dest, right? Rec dst, and then some stuff in here, some logic, and then the output right here could be another rec, right? So we could do something like that. Now, I just wanted to see if I know what you're talking about before I look at the URL you gave me, right? But yes, we could probably do something like this, right? So vec2, the source, and then, oh, no, this should be a vec2, right? So vec2, the output, right? So here's the source, here's the output, 2 rectangles for the mapping regions. But yeah, let's go see what you're throwing together here. Type def struct vec2 union. So we got a struct with an x and a y, and then we also can use it as an array. Okay, that's some fanciness. So this is, you used a union because technically, let me see if I understand this correctly. To be proper C code, if you were not using a union, you would be, would you be violating strict aliasing rules? If you did not use a union. Old type punning, right? So, because I mean, because technically, we could just, right, because technically we don't even need a union, right? We could just say it's, well, I guess, well, then it wouldn't really work properly. Okay. Okay, yeah, but I do get what's going on here. I do understand what's going on here. So you have like a little you have like kind of a variety of ways you can use it, right? So you can use it as an array, or you can use it as .x.y. Because with the memory layout, here's the first 32 bits, here's the next 32 bits, and then right. So this struct right here and this struct take the same exact memory. Yeah, theoretically this. Well, actually no. Unions are an I think that unions are allowed to yeah, I think I don't know, maybe I didn't, from what I've read around, and my understanding was that like unions are like, were specifically, that's not correct. Okay, fair enough. Yeah. So don't trust everything you read on Stack Overflow, right? All right, fair enough. So next time I think I want to do something proper and use a union, I'll be like, screw it, because it's not proper either way. Okay, got ya. But well, I guess a union might be a safer way to do it because, like you said, it's a technical violation, but no compiler's actually gonna, you know, call you out on it, right? So we got the lower bounds, we got these upper bounds. And let's rerun this, right? So let's, oh goddamn. Okay, let's rerun this and make sure that our tests pass. And then we're going to look at how we are calling it within the shader code and make sure that that is proper as well. So hopefully we didn't completely screw ourselves. Like, hopefully this is not a difficult problem to fix, right? Okay, cool. So our tests are passing. Very cool. So now the next thing is to just go into the shader code where we're calling this and hope that we finally figured this BS out. So we got 0 to max. So this is the bounds of the source. And then we want to do the lower bounds. So we're going to do the lower bounds, XY, lower bounds, and the XY upper bounds. So, right, so this is, right, so we got lower bounds and then the upper bounds, or the lower bounds and the high bounds. Low bounds, high bounds, whatever you want to call it, but that's what's going on there. Let's give that a run and see if the shader that I'm trying to get working, it will actually kind of do things. Standard says there's no guarantee. It's like a big misconception because every single compiler handles it like you intend. Got ya. Okay, so let's go look at this. So let's go press the 1 key. Let's press U to set some debug variables. Let's go back to this shader and say, okay, I think that mapping looks correct. So right here, we can see these little pixels right here. That is the region where, that's the region of the Tau Depot memory, the Tau Depot bitmap. We're storing variables for the PAINT5D system. So all of our uniform variables are being stored in this little chunk of this texture right here, this little tiny 32 by 32. And that's good and all, but the next step is that we want to actually zoom in on that properly. So we want to, rather than kind of having, you know, taking this entire area, we want to zoom in on it, and we were thinking that to zoom in on it, that these are the proper bounds, right? So we're thinking that, well, somewhere in here we have the proper math. Oh, right here. This is... Uh-huh. Oh. It's, because it's hard-coded to 0 to 512 right now. And we want to actually use these values. So we're hoping that these are the correct calculations. Now, they may not be. Let's keep these old values that we kind of hard-coded in here. Let's just throw them in here somewhere. And 0 and 512, 0 and 512. And so we're thinking that we can just throw this in here. We're thinking that these are the formulas to correctly kind of hone in on the memory that we want to render. Okay. So I'll try to explain that after we get it running, because I don't even know if that's going to work correctly. I'm zooming in. I'm doing like a viewport zoom. Like I'm zooming in. I'm doing a camera zoom. I'm doing a camera zoom by kind of like, yeah, I'm doing a camera zoom is what I'm doing. Let's go look at this. So let's go U and set something. Let's go over here. Okay, so that camera zoom isn't quite correct, but we were thinking that the mapping code was correct, so the assumption here is that this is off by 1. So the lower bound looks correct, but then the upper bound seems kind of off. And same thing with over here. Okay, so let's go look at that for a second. So we got this x0. I think this gets the upper left corner. Okay, I just think I need to... I could be wrong about that, but I'm gonna give that a run. See what that happens. So I'm trying to do a camera mapping, and also it's like 8:47, so pretty soon I have to take drugs at like 9, and then it's already like 9-hour stream. So what I might do is like immediately reset the stream, go into like break, take a break, and then do like the rest of my push-ups, take my drug, and all that good stuff. So let's type a U over here, and then let's go over here. Okay, so now the mapping on the x-axis looks correct, but now the mapping on the y is not quite correct. So why the heck is the mapping on the y not correct? So the y, we got this 32 times 12 here. I'm gonna move this over here. Okay, so the y-axis is not correct now. It's specifically that upper bound on the y-axis is not correct. So let's go look at Tau Depot and look at the data. And we're inside so I'm thinking 15, 14, 13, 12. So I'm thinking that's the 12th cell on the y-axis, hence 32 times 12, because each cell is 32 by 32 pixels. Forgot align, ignore first link. Okay, I'll take a look at that. So this looks correct, but then it seems off by 1. And I don't know why that is. Max is 512 minus 1. Right, because 0 to 512. And even if this was off by a little bit, this is the pixels, so... Hold on here. So let's look at I want to take a look at this. So 512 divided by 32, right? So 512 divided by 32, what does that give us? That gives us 16. That gives us 16 different cells. And if there's 16 different cells, that means the maximum cell on the maximum 32 by 32 cell that we could possibly looking at, if there's 16 of them, is number 15. Number 15, number 14, number 13, and then number 12. So number 12 right here. And if we're looking at number 12, we want to look at the last pixel, the last cluster of pixels in the last cell. Oh, got it. Okay. Well, yeah. Last cluster of pixels in that cell. So, okay. So I see what I'm doing here. So 0 and now if that's true, then why did it work on the X and not on the Y? So 15, 14, 13. I don't even know why the heck it would... I don't even know why it's working on the X then, because that doesn't even make sense. Possibly I got my math wrong on the X. And I'm thinking that the value I'm storing on the X is actually wrong. because this formula is wrong, and the math where I'm setting a pixel on the y-axis, that's actually correct, but this math is wrong. Okay, so I think I have like two errors canceling each other out, but but isn't that what this is for in the first place, right? Plus 0, because it's the top left corner. Plus 31 to get to... It's a 32 by 32 cell. So this gives us the first pixel of the cell. And the cell is... If we add 31, we actually get the last pixel of the cell. So I think it would actually be this. I don't think we actually add anything there. Right? Because then, if it's the 0th, the 31st would be the last pixel of the cell. And I'm going to take a look at your link. Hold on. So I think that's actually the correct math. And if that's actually the correct math, something is off. I think there's something off with... So I'm using these identical formulas. I think there's something off with, like, how I... Right. So let's press U, then let's go over here and say, WTFs. That's not quite correct. So this is right. This is good here. This is not good here, though. Let me go look at where I'm setting this for a second. So in Tau Depot data, Tau Depot data here, we created some debug variables somewhere. So these indexes, so 512 divided by 32 is like 16, right? Yeah, 16. So if we want to go over on the X, we end up at the 15th cell, and this is the top. So this is the top left corner. This is the top right corner. I'm thinking that this math is not correct, but the 255th cell location should be the top. If we minus the stride and plus 1, so we do 255 minus a stride of 16, and then we plus 1, we have 240. So this looks correct. This all looks correct. Right? So are we using these variables correctly? Are we actually assigning them? D1, D2, D3, D4. Okay, cool. And where are we actually using them now? So we have those here. Are we using them? So this is the variable location. see how we're using that function call. Maybe we're not, maybe we're not. So x is then y, zeros and ones, that's the order. D1, D2, D3, and D4. D1, D2, D3, D4. And this is the tau, sub, and var. And the inputs, that all looks correct. That all looks right. Why the hell am I off by 1? Let me go look at your Imgur here. I'm off by 1. I don't know why I'm off by 1. It's kind of infuriating right now. Oh, so this is the... Oh, so I'm going to put this in my shortcuts, huh? Then the size is 7. The mapping will be 1, 2, 3, 1, 1, 2, 2, 3, 3. Okay. Yeah, I see what you're doing here. Okay. So you're trying to stretch this over. So this kind of mapping actually looks like more kind of the mapping I'm doing. Yeah, this is more the kind of mapping I'm doing, right? Kind of. Like the value mapping. Yeah, this is more similar to what I'm doing. I'll put that in my notes. Okay. Now, what the hell? Okay. Why is this not correct? Is it because... Oh, wait. 32 times... No. So this math doesn't account for all the transformations. This math accounts for here, what's going on here. But doesn't account for the fact that we're over here. Oh, I see. I'm just being completely stupid. I'm being completely stupid. We have to actually... That would drastically change things. No. I think my math is more correct. My math is coincidentally working better than it should. I think I'm like completely off, but there's just these happy little coincidences that are throwing me off. So let's just write this exactly how it needs to be written, and this is just going to suck, but we just have to write it out exactly because this math is not quite correct. So we're in this cell right here, right? This cell right here. And it's 0, 1, 2, and 3, right? So we take, these are 128 cells. So we say a 128 cell times the third coordinate. Okay. Let's just start off with a 0 here. Okay, then over here, yeah, we're just not doing this correctly. We tried to hack it together, and it's improper. So then over here, we're trying to look at this cell here. And on the X, we're at 0, 1. So these are 32 by 32 cells. So this should be like a 32 times this coordinate, which is 1. Let's make sure that these cells are all 128. So 128 by 128, yeah, because 128, 128, 256. Yeah, so these are all these cells are 128 in size. But why is this not 64? Well, because it's 1/4. 32, 32, 64. Yeah, it's 1/4 the size, hence a 32. Okay, yeah, so we have 0, 1, 2, 3 on the X for this subdivision. Then when we go down a little bit deeper, we go 0, 1 times 32. And then to get to the final location, we want to, for the X0, we just want this here. So we're already there, so we just say, you know, plus, plus 0, because we're in the top left corner. And that's it for that. Oh god, this is... Okay, so let's just steal that, and for the... We're going... I know this is kind of wasteful the way I'm writing it, but we just want to get it working properly. Before we even try to fix up the code, we just want the code to be correct, right? We want if the code's not correct, nothing else matters, right? So, and then it's 9:03, so I do have to go take drugs. So let's just steal all of this and paste it and rewrite it to y, right? So this is y, and this is y, and the coordinates are a little bit different. So on the y here, it's the same here, right? Because it's diagonal, so the y is the same for this level. But over here on the y, it's actually a 0 instead of a 1. So this is a 32 times 0 here, and a 32 times 0 here. And then over here, right, we want to do a +1 here and a +1 here. And that is actually the correct math for God. So I'm pretty sure. 128 times 3 for everything because it's diagonal. 32 times 1 on the x because we're getting over here 1 on the x. But on the y it's zeroed out, so it's just a 32 times 0 on the y. Then 0, 1, 0, 1 because we're either getting up here for that first one, or we're getting down here for that last one. And that's not quite correct yet, is it? It's close. We want the first cell here, right? So this gives us the base of, this gives us a cluster. It gives us the first pixel of the cluster that's over here, and then we want the last pixel of the cluster that's already at the end. So in order to get that, we need to add, we don't want to add 1. We're at the 0th index, right? And this is a 32 by 32, so we want to just add 32. Or not 32, but 31. And I screwed that up. So the upper bound right here gets a 31. The upper bounds get a 31. And a multiplication by 0, right? Then why is this one a 1 and that one's a 0? Because that's the coordinate. 3, 1. 3, 0, 3 and 0. Okay, yeah, I think that's right. I think that's right. Let's give this a run, and then I gotta go do drugs, do some more push-ups. So that is ridiculous. But I think that's correct. So let's go see if that's correct. Okay, so let's go over here. Let's press U. Let's go over here. So no, we're still kind of like... We're still kind of like not... God damn. This is... So something's wrong with my math somewhere. I don't know where it is. But we're almost at 10 hours, right? We cannot upload to YouTube if we go past 10 hours. So we're going to stop the stream. We're going to restart the stream later. But I'm going to stop the stream. Oh, actually, I'm going to immediately restart the stream and just go on break. Right? So I got to change the stream number as well. So this is 135. So we got to change to 136. So I'm going to stop the stream, restart it, and then I'll be right back.